So the Spark cluster has multiple workers. Each worker can run multiple executors, and each executor can run multiple tasks. So we're looking at multiplicity from 1 to n and from 1 to n, sort of multiplicities. So how these executors and tasks are set up is going to depend obviously on the environment, and we do have some kind of control over that we can exert to a certain point, but very often we want to take advantage of any kind of built-in optimizations that are actually there. So the executors run processes that basically are the tasks. Each application we're running gets its own executors, and they run for the duration of the application. So the JVM containers are the underlying storage and execution boxes or containers, and tasks run in the various threads. So there is a bit of multiplexing going on here, which is managed quite well. So again, the task, smallest execution unit, and it also works with local data because it doesn't require reshuffling, and each task then runs as a thread in the executor JVM. Means that certain tasks can even be run in parallel. So because of this, we have the improvement over over the standard MapReduce model. We're not going to again get into benchmarking it or degrading the MapReduce section, but so in MapReduce, and this is perhaps one of the architectural differences that maybe it's just important to note, is that for MapReduce, each job has its own JVM container, and once it's done, the container's terminated, then new containers get started. So what we're really looking at here is a constant creation deletion cycle of JVM containers. Now in Spark, the executors are long-lived. Now that to me says there might be some interesting things there with the issue that you just mentioned, and that gives me an idea to where to look for the solution. So they're not terminated between jobs when not running tasks. And that suggests to me that based on your question that there may be a setting there we want to take a look at. So because these things are sitting in an idling mode, the new task startup is very fast, and it's task switching too, because we're not going through all of the boot up and shutdown procedures involved in the older MapReduce model. So and somebody's put a joke in there, live long and prosper on this. So so again, I'm suspecting based on what you said that there may be something here that we want to take a look at. So here's the excuse me, MapReduce task management. Very straightforward. Is that we have job one, we create our JVM containers, and we do job two, we create some new containers. Whereas in Spark, what happens is that these same containers are running from job one to job two to job three, but what we're doing is we're executing the various tasks in different threads in the containers. And when I stop and I think about it, there's a little bit of complex programming going on there, which I think I'm really kind of impressed about when I think about what they're doing here under the hood. So this is something I'm always fascinated by how people solve problems. So I'm kind of dying to actually think about how that actually works in a little bit more detail. So driver memory versus executor memory. The driver memory is on the driver program, which is often on a separate machine or node from the executor memory. So the driver memory is generally ratio-wise small compared to the executor memory. Executor memory is where the memory caching is taking place, and it can be gigabytes and gigabytes maybe even terabytes of memory that are sitting there, probably nowadays terabytes of memory that are sitting there being available. The collect command sends data to the driver. Generally, the standard rule of thumb is don't, unless you're doing a small run for debugging or development purposes. When you're using a limited set of data, this will basically overwhelm the driver and not end in a good way. So Spark and Yarn are the managers, and that are, or I'm sorry, Yarn is the manager that Spark is often run on top of. And if in the absence of Yarn, Spark also runs in a native mode, which does cluster management itself. But generally, the preferred approach apparently seems to be to run with Yarn. So because of this, there's two modes that run. The client mode is similar, is what you would use when we're actually running Spark in the interactive mode, and we're doing debugging and running jobs to do our various kinds of tests and QA on our work and doing development work. And then Yarn cluster is where we're now in a production node. The difference is the architecture on how this is working. Where we're now, remember, the Spark driver is where a lot of the graphing and everything else and management is taking place. In a client mode, what we're actually doing is taking all the Spark command and delivering the commands into the Spark master, which is running now on the node manager, which then of course manages the resources. So the driver is running in our client. That's our interactive component. But when we put it into cluster mode, you'll notice the difference here is that the Spark driver, which contains all of the various management commands, is now being used and being pushed down into the node manager. When you stop and you think about it, this is obviously the way you'd want it to work, because if you do not want to have a running job being dependent on something in your client machine where you're launching the job from, you basically want to launch it and let it be managed by the operational environment instead of being in the client environment. And there's no need in this place for you to actually have to interact with the job. So the run mode is going to be determined when you submit the job. So in the run mode, we're going to be running in the client mode, which again depends on where the driver is, and the cluster mode is going to be in the running it where the where the driver is going to be located. So again, why would you want to do it in client mode sometimes? Well, depending on the particular needs that you have at the point, or at that point in development, you may choose one or another. In other words, there's use cases where you might want to use one or the other, but you have that fine-grained control over it. So the difference in the two modes are where does the driver run. So in a standalone mode, where you're not using a Yarn client, the driver runs in the client. Who requests the resources? The client. Who starts the process is the Spark slave, which is the Spark built-in Spark manager, because Spark can run without having to use one of these managers, depending again, since we may be using some other kind of underlying distributed mechanism. Remember that the whole point of Spark is that you can build it on top of multiple resource managers, Mesos and Yarn. We're using Yarn here as the example, but we can also run it in sort of a native mode. And then there are persistent, the Spark master, and the Spark workers are the persistent services, and it supports an interactive shell. When we're using a Yarn client, Okay, this is again our interactive. The driver runs in the client because it's interactive, but now the master is being moved over to the Yarn client, so it's now taking care of that. The starting of the processes and all of the management of the resources are now being delegated here from this point down into the whoops. I hope you get one column here. Is being all delegated over to the Yarn node manager, but because we're keeping the Spark driver still inside the client machine, we still have an interactive session. The final thing is when we're basically running in production mode, the driver now has been moved down into the Yarn cluster, and everything is being run independently of the actual client. So because of that, there's no ability now to do any sort of any interaction with the job. It's running in more or less a batch mode. Okay, so one of the other things we have here is that when we're running Spark under HDFS, the HDFS, because it is very good at managing the distributed data, it can provide what we call location hints. So this gives us faster processing because we're not hunting around the network system. We're able to take a look at or able to utilize some of the information that's available through the HDFS interface. Okay, so again, this is where those slides seem to be really weird and confusing. So here's the driver code. We're building a test application here in a Scala format. Now we're looking at this in a generally interactive, not interactive, we're looking at this in a production mode. So again, from Scala, our test app is a single instance class. Our entry point is the main method, and we're creating a Spark session builder, which is equivalent to us opening up a shell. An actual Spark object is created. We're giving it an app name test, and then we're going to do get or create, which is either going to get the existing, getting an existing session or create a new one. And so in this particular case, we're now reading a text file from our file, and we're just printing the number of lines, and then we're stopping. Obviously, this production here is just a placeholder for what we want to do, but what we're doing here is we're basically creating the actual Spark session that we would normally utilize through the SC dot or the Spark dot interface context. And then once we've got that, we can now use that context that we've defined here. So now we're actually manually creating the Spark context that we're actually going to be using. So now we apply a Spark command, and then we stop the session. Okay, so the builder also allows you to start setting some of the parameters. So here are some of the parameters that can be set. And so we've got a number of properties that we can set, like the app name. We saw that up here. There's the app name right there. So this is unfortunately formatted not too well, but it's builder.appname. And then we can have a number of other options in here. So app name is the one we've got here. Then we've got master, mater URL. That's very Freudian, but very Freudian typo. And this is grabbing our local, which means that it's in the local machine, and we can set some properties here as what the various hosts are. So here is the option I was just mentioning before, local, which you're running on a single CPU core, local N with N cores. I think you all have 4 cores on your machine, so you can, I think some of you have already experimented that or you can run on a local host with all cores. So choosing the variety of cores to run on. If you're distributed, then you can look where the Spark master is running on. If you've got a Mesos, you can having the Spark running on Mesos, and you also can have this running on Yarn. So it's in this configuration URL that you're actually building all the properties. You can also, again, use the name properties in the configuration startup. So these are these hyphen configs. So now we're actually doing a Spark submit and using the double hyphen config to be able to specify some of these options as well. So this is the kind of thing you would do if you wanted to not have to specify that when writing code, but wanted to specify these things at actual implementation time, deferring it to execution time. So Spark master is the URL, app name as before, so now you can see it in there. Spark.master equals Spark, and then you've got the URL of the master. So you can also set the configure operations in the file. Actually, from my perspective, I always like to use the idea of configuration files, because then I do not encode or hard code various parameters inside the code. This is just true as a general principle, not just necessarily for Spark, but I also don't have to re-enter them at command line, but I can basically develop different configuration files for different scenarios that I want to run, and I'm able to reuse configurations and choose from multiple configurations. So a key value pair, standard kind of YAML / JSON format. And those can always be overrun. So the precedence is the property set directly on the Spark session, which would be the ones that are actually in the code, set right on the session. The properties passed to the Spark submit, which would we override at the command line, and then also the Spark defaults.conf file, which we can keep multiple versions of and make the changes. So again, standard kind of overriding the principle. The closer you are to the object when you set the properties, the higher the precedence of the options. All right, the builder creates one.
Sorry, quick question.
Yep.
Quick question regarding the master URL property. What is the default value whenever there's nothing set? In the Spark session. I mean, there must be some default coming by Spark itself, right?
I'm not sure what the actual default is, but I suspect it is the local machine.
It is local. The Spark default, the Spark master is local.
Also,
yeah.
Whenever running it in data,
it doesn't really care actually. Yeah, it doesn't use the cluster mode. Yeah, it will work on one machine.
I mean, Dataproc is using Yarn.
Yeah, but you have to specify Yarn when you write your code. Otherwise,
in the Spark session.
Yeah, otherwise it will use the local. So we had this issue. We had this issue. I thought it was handled by Dataproc.
Okay.
For 3 weeks we run our service, and there was like 8 nodes. Only one machine used. What's wrong? And they realized that you have to specify Yarn. And if you specify Yarn, basically it uses all the resources from the cluster. So whatever is able to be allocated.
Yeah. So the default.
8 workers, only one was used.
Well, only the driver where the Spark application master was running was used.
Ah, okay. So
because you have two things. You have the master, what you use, and then the mode.
Yeah.
Then the what?
Then the mode that you are using, which is cluster or client.
Yeah.
And basically, so if you use the master local, it will use only the machine where the job has been submitted to.
Yeah.
You were using client.
Because
you submit the job through Dataproc, through the interface, it's actually the master machine that submits the job to the cluster. So the job was just running on the master with local. And then we switched it to Yarn. with client, which basically uses still the master as holding the driver because it's client mode, but using all the worker node to compute. Okay. And then if you use cluster and yarn, your application master and driver can be whatever node. It could be random, it's chosen by yarn itself, which means that if you have 3 different Spark jobs, they could have 3 different nodes holding the driver, basically. That's how it works, like 2 different services, I mean. Whereas in client mode, if you submit to Dataproc, they will all run on the master node. It's not very optimized, yeah, I reckon, but that's the way it works.
Well, go ahead.
We talk about it.
Okay, yeah, thanks.
Yeah, and when you stop and you think about it, if you don't have anything specified and it's going to default, what is it going to default to? It's going to default to what it knows, and what it knows is the local machine. So it's going to take that as the default, which I believe is exactly sounds like what you were experiencing there, right?
Yeah, we had this, but like it was a long time ago, like 2 years ago. But yeah, it was basically we assumed that if you specify the mode, which like client or driver or cluster, that it should basically pick up the configuration from the cluster. But no, you have to define the master and the mode in accordance with what you have as an architecture. Otherwise, you conflict there. If basically your master, you don't define anything, even though you will use cluster mode, you will still use only one machine because the job will run on your machine a random, like whatever, one of your nodes, and it will just run on the node with local.
Yeah. All right. Does that help answer that question? Whoever asked it.
Yeah, definitely. But I need to check the configuration of the application that we're having. So yeah, I'm talking about a different application than than where the problem occurred. So yeah.
Okay.
I need to check.
Okay. Well, when you check, if there's any more questions, let me know. All right. Okay.
Thanks.
Okay. So building a session, creating data set. Okay, so now this would be basically the code that you would have creating the Spark session itself. Building and creating this would be setting our parameters. Creating a data set would be an operation we perform through that interface. We'd read Parquet, and then we would access the underlying Spark context. And that would be generally assign it to that would basically display the underlying Spark context, and then you would use the SQL, we call it the interface into that context, and perform the execution, and then we would now stop the active process before creating a new one. So we don't need to do anything more. So again, coming back to this locks, we may want to come back and explore some of this a little bit later. Okay, I'm not going to have you do this. We'll come back and take a look at this latest docs later, and we might want to take a look at some of that. Code building tools. SBT is the Scala build tool, which is modeled after, actually kind of modeled after Maven, uses the same kind of architecture. We can use Maven to build the Spark dependencies. Remember, all this stuff is running as bytecode on JVMs, so, and it is basically all built on top of Java, so we can use that kind of build tools that are effective. There's a Scala IDE, Eclipse-based Scala IDE. I have not used that. I've gotten away from using Eclipse. IntelliJ, I think we've got a copy on the VMs, and also Sublime, which is the standard thing. I've never used Sublime. I use Visual Studio Code, which is sort of the enhanced version of that, and that seems to work fairly well. It's particularly when I'm doing Scala. Application layout. And there's the build files for the Scala build. logging sections. We have the, since again, can utilize a lot of Java code, we have a Java section, Scala section, and then a number of the packages down to the Spark package, and then our tests. So this is a fairly standard layout, which is, again, a Maven layout. If you're unfamiliar with Maven, that's sort of the de facto build tool for the Java world, although I think people using Grindel and some of the other ones might argue that. So the build file for the SBT sets a number of the parameters for the application names, version numbers, and then then it configures the dependencies, and again, this is for the actual compilation process. So the build SBT is the same as the project object model XML for Maven, which automatically downloads the dependencies and has a couple of different options: compiling, packaging, assembly, and clean. We'll look at those differences in a moment. And of course, to rebuild completely, SBT clean, which cleans up all the generated artifacts, and then package goes back and rebuilds the jar. So this was the example of the Spark submit. You've got the class, the master, the deploy mode, and the configuration now submitting that particular job. And this is what we were just talking about here. The Spark submit launches apps on the cluster, and we just had that discussion about launching it in various modes. The Spark submit now gives us, once we built it, we can when we submit it, we specify all of the various options that are needed to actually run it. So for example, the memory for the driver app, and we can set that if we wanted, let's set that parameter however we want. The executor memory to be important. And I'm not sure what sort of defaults, again, for some of these things might actually be. I think it's going to become very dependent on how you've configured the system, but we can check into that. And then the Spark configure properties, so we can actually set certain properties, key value pairs. So there's examples of all. This is going to be fairly standard in terms of how we submit jobs, giving it all the appropriate parameters it needs to run. Here's one of the differences between the lean and fat jars. So the lean jars typically contain our code, no dependencies. The dependencies are introduced at runtime, and or if we don't have any dependencies at all. But if we do have dependencies from some other kind of code base, which may be customized, then an assembly will package the code along with those dependencies. And this is there to resolve this versioning problem we have. Once we get into a system where we're constantly downloading dependencies, if we're using a customized version of a particular dependency, we want to ensure that new versions of that dependency are not going to overwrite our customizations or break our new code. So we produce a fat jar which has the dependencies built into it. So here's an example that we're actually building here. So we're have our import. We're setting our name to the test app, the version, the Scala version. So all of that code is implemented, and then we create our library dependencies, which are the sequence of the dependencies that we need for the various that we need. Then we can add more to the library dependencies for the S3 or HDFS. Then we have our assembly settings, and the various options that we can set on here. So log4j properties, and we can look at the various properties that are going to be set up there. So the we don't need to worry about Python. So the so with the Python dependencies, we don't need to worry about those. So the driver gives a web UI with the application. So now we can actually see the jobs, the stages, and everything else. I think you guys are familiar with this already, accessing it through 4040. And the editing files in the VM is, and I think you've got the new machines there if you want them, and if you don't want them, and then you can use the VNC desktop. You can use the various different approaches or editing tools that are available to you there. And so now we're going to actually do a little Spark job submission. So we'll let you guys work on that. Now, as you're doing this, first of all, we'll say, is there any questions so far?
Not from Berlin, I think we're good.
Yep.
You're good? Okay, do you guys want to give this a shot then?
Yep.
Okay, good. I was hoping you would say, if he said no, I'd be
concerned.
Yeah,
sure, yeah.
You know, nah, we'd rather go for coffee.
Very concentrated.
Pardon?
Everyone is very focused on their machine. I think they were all like waiting for this.
Okay, well, that's, you know, I think people in our industry, we don't really feel alive sometimes unless we're actually working on our machines. Okay, so what I'm going to do is, if you want to let me know which machine you're working on, and as we get towards into the break in another hour, I'm going to shut down some of the machines that aren't going to be in use, but I'll let you guys still have the option until we get to that point, okay? So I will check with you in 15 minutes, all right? All right, another check-in. How are we doing for time, guys? Are we good?
I'm good.
Yeah, I think everyone is...
Good. All right. Well, I'm glad that no one felt. Well, I better turn on my alarm here before it goes off. And hold on. There we go.
Yeah, I think this lab generally takes a bit longer because SBT is downloading the internet.
Yeah. Well, anyway, I do apologize for the setup screw up. What I'd like you all to do is, I'm going to delete the old machines, except for anybody who wants me to leave their old machine up, and I'll do that after class today. So if you want me to leave your old machine up, just leave me a message in the Slack channel, and I'll make sure I leave your old machine up. Or if you don't want to use the new machine, let me know, and same thing, I guess. But what I'll do is I'll delete the old machines unless you tell me you want them up. And I think I've already got one person indicating they're using the old machines, so that's fine. Okay, yeah, and I'll remind. Okay.
Sorry, but I'm still using the old machine.
Pardon?
So this was Mike. I'm still using the old machine. It's
okay.
I don't need the VNC. So I'll just Slack you to keep the old one up.
Yeah, just Slack me, because otherwise my brain will probably not remember if you just tell me. I need it in the Slack so I can not make any mistakes on that. Okay. All right. Thank you very much.
Sorry, just to clarify. So by the old machines, you mean the machines created before today, right?
That's right. The machines you did earlier.
Okay.
Okay.
Please don't use the machines that you created today.
Yeah, we won't. Like I said, I'm only going to delete the old machines if the ones if you tell me you don't want them anymore. Okay, so each person will be specific on that, and we'll be fine. Okay. Okay, good, Robert. I got your message. Excellent. Okay. Thank you. Problem is, I'm teaching two courses with two different Slack channels, and I'd have to make sure I'm looking at the right one. Okay, thank you all, gentlemen. I appreciate that. Now, talk a little bit about logging and debugging, and then we're going to get into some more of the topics. Hopefully, will be of interest here. There are very large sections on AI and other stuff, which we will just give a very, very quick peek into, because I know that you gentlemen had said that that may be something that you're not keen on, but we'll make that discussion and you'll get a chance to give some direction as we go. Okay, so so now we're sort of getting into the idea of monitoring what's going on with the some of the oops, did I do that? Okay, all right. With the monitoring and some debugging, and we'll be dealing with this topic at a number of points during the rest of the course. So we want to figure out what's going on. So we're going to take a look at this toDebugString and some of the web-based VI and UI and logging. So the RDD.toDebugString gives a description of the RDD and its recursive dependencies. And so it gives you a bit of a window into what's going on in the underlying application when it's executing. So if we take a look at the actual code, we could create this string, and then what we're doing is parallelizing this by using a split into a number of words, and then we're reducing it by key to count the number of words. So there's our fairly simplistic RDD, and now when we actually take this word pairs to debug string, then we can see what actually goes through our mapping partitions. We're doing a map partitions at the console, so that we're at the parallelize at console 23. So that would be the line number we're coming at, and then so that would be the words pair. There we go. So that's would be describing what's going on at that RDD. Then what we do is we do counts to debug, do the toDebugString. The string is saying there's a shuffle taking place at reduce by key, which is of course the kind of information we want to take a look at. And then there's a mapped taking RDD taking place at a particular console, then a parallel collection at parallelize. So what we're from a parallel, I'm not going to say that word anymore. Parallel collection RDD. So what we're looking at here is the sort of sequence of steps, and the thing that's what we're often looking for is to figure out where our shuffles are taking place. So we're getting this kind of sequence of steps. So the parallel collection, the mapped RDD, and the shuffle that's taking place as a result of our reduction by key. The web UI is the one that's available. I think you guys have already got this thing up and running a few times. At least from the discussion I've been listening to, it sounds like you've been looking at this as well, which gives you some insight into what's actually going on under the hood in terms of collected statistics. So here's our total duration is 16 minutes for whatever job this was working on, the scheduling mode, FIFO, the number of stages, completed stages, failed stages. Remember, the stages are the parts of the job that are executed without having to do a shuffle. So we execute the counts RDD collect, and now we have a completed job, and we can take a look at what's actually going on in the completed job. So there's one job, which is the collect. Notice that we're looking here is that the action that's actually caused the job to execute. There were 2 stages. Remember, we had a shuffle. The number of tasks for all stages is 16. Remember, the tasks are the number of individual jobs that are executed across the various worker nodes and executors in order to get the job done. So we got a breakdown by stages and tasks. And when we take a look at a stage, there are 2. One for the map and one for the reduce, and because it required a shuffle to do the reduce, we wound up having to do a shuffle. certain operations are inherently going to imply a shuffle may be necessary. And if you click on the stage description, you can look and see what the stages are. Sorry, I said tasks instead of stages. So we've got the task of the collect task and the number of tasks that were involved in that stage. So if you initially go back and you look at this, if there's, I think it looks like we're probably running on four nodes here. I'm just making a guess at this point. So theoretically, if you're saying, well, you know, without a shuffle, there should be eight tasks. But because we've got 2 stages, we wind up running 8 in 2 stages. So there's a number of tasks there. I'm not sure exactly of what the environment was running. So, but so just speculating there. But now you can look at, we've got 8 tasks. 8 out of 8 succeeded. We also have the stage IDs. So we had the map and then the collect. So we wind up having a breakdown of the actual time that was spent in each stage, and the and also the amount of time, the shuffle rate that actually took place, the number of bytes in this case that were actually shuffled around, so we can actually see what was actually done in order to do that. Okay, so now we can take a look at the details for stage 1. And I don't think this is for that actual 2, oh, maybe it was. So we've got, by the way, the one thing to notice here is that Spark does not scale down well for very small tasks in terms of performance, because it was not intended to do that. So there's not a linear relationship here. The duration that we're having in terms of the tasks and some statistical numbers, medians, percentiles, and the maximum that we've actually got in terms of the task durations. Garbage collection time, since we're not actually, it looks like we're not using any garbage collection here, then none of that is relevant. And of course, if we're using various kinds of off-heap modes for storage, then that garbage collection time could be 0. If you do see it having a number there, it may suggest that you're not managing memory the way you think you're managing it. Aggregated metrics by executor, how each executor managed each task, and the number of succeeded tasks, and the general amount of statistics for that executor. In this particular case, excuse me, some of the stuff that's also of interest to us is the amount of spill that takes place during that particular stage. And now, so we can also then break down each task and look at how each task is working, how well it's performing, duration, garbage collection time, errors in that particular task. So being able to analyze this is important. Now, one of the things this is useful for, and it comes back to this idea of sampling. If we can sample a fairly representative sample of the data and run a task, and then take a look at unusual skews in this data, we may suggest some optimizations. And I'll just take a kind of jump away from the slide for a moment and say, out of everything I'm aware of in the Spark community and listening to all the experts that I've listened to, the theme that's stressed over and over again is that the first line of optimization in Spark is to know your data. And if you understand that your data is going to be structured in a particular way, then you can look at optimizations based on knowing that data and taking samples of that data and running the Spark Spark program that you've designed with that sample of data, then analyzing the results to see if there's any unusual skewing. And I think one of the examples I was looking at was in a join, where you had a very, very large data set, which was all the people in the United States, and you wanted to join that with their state of residence, which was a relatively small data set with about 50 entries in it. And of course, what happens is you wound up with a very, very large number of people or records that corresponded to people who lived in California, which was what, 20 million or 30 million, as opposed to the number of people that lived in a place like Wisconsin, which was probably a couple of 100,000. And so the data after the join would have been heavily skewed. And so you might want to look at doing some other kind of operation on the data to make it a little bit more useful, like generally doing some kind of pre-processing. And that's the kind of optimization we'll be talking about. Maybe I'll take a look at that little case tomorrow as an example of some of the tricks that we can use in Spark to do that kind of optimization. But the idea here again is that this is the kind of statistics that you can use to get you to give you feedback on how well your data is working in the particular application, how well a set of data is working in a particular application, or how well an application has been running. So here now we're now looking at the overall running applications and the workers. So we have the workers in this particular case. It's just looks like it's just the same. We're running on the local machine with 8 cores, using 15 gigabytes of memory per worker, in this case, one of them, and we're running in the Spark shell at 8 cores, and so we've got information again on the workers and shells. So okay, so that was the number that came from. There were 2 stages, 8 cores, so that gave us the 16 tasks. Okay, application detail gives you the ability to access the standard error and standard out, so the logs, so you can also access those logs directly. The master logs are named after the user and computer name, so Spark student org. Apache Spark deploy master. Well, you get the idea. I'm not just going to read out the name there, but you'll be able to see it whenever you run the log. If you go and look in the Spark logs, you'll be able to see it. So those are the master logs, and then you have the application logs, which are in a separate directory for when that application starts. So for each app, you've got a standard output and standard error logging, and you can also look at that through the user interface. And of course, by having the raw logs, then you can also run an analysis tool on them and do some sort of analysis on the logs. One of the more interesting things I think that is possible to do is as you may encounter situations where you've designed an application for a particular type of data that's coming in. That data may change over time in response to whatever it is that you're measuring. There may be changes in the data sources, patterns of behavior, and as a result, the data that you're getting in now is no longer actually as structured in the same way that the data that you were originally using to base the application on. And by looking at the comparisons as to what the differential rates of performance are over time, you may start to see trends that your application may be starting to show less and less performance, and may require at some point a bit of refactoring to say, well, if my data has been changing that much in terms of what's coming in and what I'm looking at, I may want to look at saying, is that degradation performance sufficient to think about refactoring some of the things that I'm doing performance-wise, and so I can get better performance, or is the degradation acceptable to the parameters that I need this stuff, they need Spark to perform on. We can also create some customized logging and using the log4j properties. Of course, log4j is the standardized Java logging environment of facility. And so we can set up a template, and it looks like that's in the in that configuration directory, and you can do a number of different customizations on that. So you may want to reduce the amount of logging that Spark produces. One of the things I have noticed is there's a tendency nowadays not to actually read log files, but to develop some kind of automated summary tool if you are going to keep them to manage all of the information in the log files, and those can be ranging anything from very simple grepping type of tools to some things that are a little bit more sophisticated. But if you just want to do manually and visually examine the logs, you may want to tweak what's actually being logged. So the files, this file will be detected and used automatically, so you have much finer grained control over the logs, and you can also use the files option to send this logging template with the app jar. So there's a couple of different things to keep in mind, or a couple of different options to be able to use some custom logging. And of course, the standardized warning is to make sure that this file does actually get distributed to all the nodes, so the nodes can actually use it for the logging. So here's some examples down here is that you are logging all of the info messages to the console, and here's where you're logging the warning messages to the console. So everything else is ignored at the information level on the second option. You can also again, because of the distributed nature, modifying the file may not have any effect on the driver logging. So you may want to you want to enable that as well. So you need to explicitly specify that log4j location. So now when we are submitting it here, we're doing the submission, there's the master, there's the driver class path, and then we're also doing the logging, specifying the logging there. So there's our class that we're using, and there's our target, our various other parameters, but we may need to specify the logging location there as well. Okay. Okay, so at this point, we'll ask any specific questions about that.
Yes, I do have a question. Okay, so regarding these logs that we see out of Spark, including the ones from the driver, they seem quite cryptic a priori. So then I'm wondering, is there any value in these logs whenever we are, let's say, troubleshooting, I don't know, performance issues with a job, or are they just garbage and we should focus on other signals?
I would say that the standard sort of protocol that you look at is that a lot of the information that tends to be your first line of defense is to look at the summary information that you see in things like the UI. Okay, so in other words, you get an opportunity to go there and see, okay, like what were my statistics? You know, how did the tasks execute? Where were the tasks? How many shuffles? That often is what you really need to look at. Where the logs in almost any environment start to come in useful is when something is not working and you have no idea where it's not working. Very often you'll get a log with all this information, and I understand what you're saying, because I find logs in almost every application to be often somewhat cryptic. But at least you can kind of grep through a log, or you can kind of look through a log, looking for something that seems to be problematic. So you might run the log, again setting the logging level to error, so that you're at least getting a log of any specific error that's occurring. And if there seems to be no error, then put it up to warn. Or if you want to just keep records of historical records as data, you can keep info. But I think you've got a good point there. I think logs in almost every one of these applications tend to dump information that is highly, we'll say, compact, but also very, very voluminous. So there's a lot of it, and it's a very difficult and tedious process to do it. So one of the things that I would suggest maybe as a best practice is that you look at logging as a diagnostic tool, so that if you're running it and you want to, if everything seems to be running the way it appears to, from the statistics or the way you expect it to, there's probably no need to go and look at the logs. But if you're seeing unusual behavior, then you might want to start looking at the logs. And I would suggest, again, a best practice would be to get the smallest amount of information that might be useful, like error levels and then warning levels, to see what's going on. And if you're not seeing anything there, then you may want to go to an info level. But again, the problem is hunting through the logs. So I would say that the logs themselves, that's the only time I've ever actually found logs useful, is when I'm really involved in a really peculiar kind of debugging situation and I really have to go back and figure out what's wrong. And I've run into this over and over again, where something doesn't seem to be working properly, and then when I get into when I finally start looking at the logs, I realized there was a out of memory error that occurred at some place, and I found it in the logs, and oh, that was it. So does that answer your question?
Yes, thank you.
Yeah. Some people are going to want to insist on having everything in the logs, but they're not going to read it anyway. Okay, so map reduction application, we'll let you guys take a jump into this one. A little bit, another thing to use a MapReduce by submitting it with Spark Submit. So this one, I can give you another 15 minutes to do this. You've done a lot of the preliminary setup, so I'll let you guys go with this. And then that'll be it for this particular section. And then,
does it really make sense for us to run MapReduce applications?
I don't know. Do you think so? I'll let you guys make that decision. It's the what do you choose as a group? Do you think this is really useful for you?
I can live without.
You can live without it. All right.
I can, but I'm not the whole group, so you guys decide as well.
Okay.
Guys, what do you think, Georgios?
I can live without it as well.
Let's check what's ahead.
Yeah, if we don't do this bonus, what's going to be the next slide, please?
Then we're just going to get into the next section. Okay. Yeah, it's a bonus, so, it's up to you guys. I mean, the only reason I'm offering this is because sometimes people just want to get a little more opportunity just to play in the environment, particularly people who are new to it. But I'm getting a sense that the general consensus of the group is, we'd rather not. Is that correct?
Yeah, it's a little bit of a I think, for this one.
All right, so let's take a pass on this one then. And if everybody wants to try it on their own, they're welcome to it. Instead, it's 10 o'clock, or 10 o'clock here, so I think it's about 4 o'clock where you are, if I'm right. So I think this is an opportunity for us to take a 15-minute break to grab a beverage and take care of any other issues. And we'll come back into, I think we're going to start looking at a bit of optimizations right after the break, okay?
That's good.
See you in 15. All right, well, while we're waiting, I'll look at if there's any questions that anybody has.
So far, so good.
All right, okay, good. Well, I don't want to wait too much longer, guys. So how is your workaround coming? I think we've had an extra 10 minutes there or so to work around.
We're missing one person at the moment, but we're expecting him to be here within a minute or two, I guess.
Well, you never know. He may have gotten a better job offer while I was getting for coffee, and he's currently in the going through the hiring process from another company. You never know. All right. Well, we'll start, and we'll for just one person, we'll start and get moving on the rest of this, so we don't keep you guys just sitting there twiddling your thumbs. All right. Okay. Sounds good.
Yeah.
All right, excellent. Okay, so we got a small section here called Spark and production. Then we're going to get into, then we're going to really start drilling down into optimization, and we'll deal with a couple of the other topics as well. So up until now, we've been kind of looking at Spark from just generally an architectural point of view, looking at some of the features, some of the, even we're doing look at the monitoring, running Spark jobs in production, kind of general stuff. But now we're starting to get into okay, so again, come back to this idea that Spark really has two components, two conceptual components to it. One of them is the Spark program design, which is what we're doing in Scala, the writing of the Spark program and all of the features and the interfaces. Excuse me for a second. And the features we can access and the functionality they represent. And then we have the other component, which is the executable side of the house, where we want to start looking at where we optimize some of those executions. We've touched on a couple of those concepts as we've gone on so far. So the idea here is we're looking at monitoring and debugging. So what are we actually monitoring? And in this particular case, it looks like this slide, maybe the diagram didn't get in there correctly. So we're monitoring the Spark applications and the jobs, and that's kind of what we've been looking at so far when we looked in the last module at the UI and other things. We can also monitor at the JVM level to see what's going on in the individual Java virtual machines, monitoring at the OS machine level, so at the operating system that's running the JVMs, and then also monitoring at the cluster management level. So all those different components are essential for the running of a Spark job, so we can monitor each of them individually and look for errors that can occur everywhere. So when to begin monitoring? Generally, we are going to start monitoring mostly because we want to figure out why something is not working the way we think it should. That's generally the use case, not the only use case, but generally the use case. Sometimes we also want to monitor if we want to see how well an optimization we've introduced is working. We also maybe want to understand how an application is executing so that we can think about optimizations that would be effective. One of the worst optimizations that we can do is something that takes us a long time to plan and optimize, but winds up having no ultimate effect on the on the execution of the application itself. So what to monitor? Well, we've already looked at a couple of these, the Spark UI and Spark logs, and they report information on the applications currently running. And why is that line repeated twice? That's really strange. And as RDDs and his query plans, I think maybe that those two lines were not supposed to be in quite that order. I think maybe they meant to say the report information of the applications currently running as RDDs and the report information with the applications currently running as query plans. I think that's what was probably meant in that slide. Okay, so what about some of the other stuff we're monitoring? Well, this is, of course, because this is the actual execution bytecode environment. Spark runs the executors in the JVMs, which of course is the architecture that means we can deploy Spark into any environment that supports JVMs. But we all want to understand how those JVMs are actually working. So there are, and so now we can look at standard Java virtual machine environment, tools to actually take a look at what's going on inside of JVMs. So we can look at stack traces, heap dumps. Again, this is getting really, really down into the weeds. And this is one of those things where you suspect that something really strange is going on within the JVM. So you want to take a look at the time series statistics, looking at the various JVM properties. And we've got JVisual VM to profiling Spark jobs. So now we're at a much lower level than the Spark UI. The Spark UI is treating the JVMs as sort of black boxes. We've got to look into the various JVMs. We use the JVM tools. Okay, this is not Spark specific. This is utilizing the JVM tools that are available. So we can monitor at that particular level. The other thing we could wind up having troubles with is at the operating system level of the that are running the JVMs under. And we may be looking at some of the issues involved in CPU, network, and I/O profiles and performances on those particular areas. And again, we'd be using standard monitoring tools, dstat, iostat, iotop that could be used to do that. There are various kinds of standard off-the-shelf monitoring tools that can monitor cluster health, because this is not just a Spark concern. This is a concern for many other kinds of applications that run in clustered environments and on OS environments. So there are other tools like Ganglia is suggested here as a cluster level monitoring tool. So there's a number of other similar kinds of tools. A couple of the ones I've seen, but I don't know if they've been used in a Spark environment, are things like Nagios. But those require some installation, so that might not be appropriate. But again, there's enough tools out there that you can generally choose. You'll probably, if you take a look into the Spark community, you'll find that people will be out there making all kinds of recommendations about maybe what it is that they're using in response to questions. So we can also monitor the cluster. So the individual, we can monitor the individual JVM level, then monitor at the machine level that's the JVMs are running on, and then we can also monitor at the cluster level to see what's going on in the cluster. So we've got Yarn, Mesos, and also we have our standalone, which is our out-of-the-box Spark. If the cluster is not working, I think somebody just gave us an example of realizing the cluster wasn't working when they were investigating a job at the beginning of class today. So we can, but again, because cluster monitoring is a generic problem, there's a number of generic tools. So Spark is saying essentially that there is no Spark solution for monitoring JVMs, operating systems, and clusters, because those solutions already exist in the larger context. And so those things can be utilized to do a full monitoring of the environment. Now, again, when are you monitoring? I'm just going to put a couple of opinions in here. So first of all, when is it useful to monitor? Well, generally, it's often useful to monitor at relatively random intervals, because the one situation I used to get caught by a number of times was, well, I didn't know it was doing that. Where I would think that something was happening, but when I looked at the monitoring, I would realize, oh, it's not doing what I think it's doing. And then that would suggest to me that we would have what we could subtly call a, what would be the word here? I would call these semantic bugs. I often differentiate between syntactic bugs and semantic bugs. Syntactic bugs are things that you can just look at, and generally you'll get some kind of error because what you've done just doesn't work. But semantic bugs are when you've written some code or put together a program and it works, but it doesn't do what you think it's doing. And so occasionally what you want to do is monitor and just see if the actual performance is in line with your expectations. And that is also de rigueur, more or less, after you make a significant change to the program, or if there's been significant changes to the kind of data that you're working with, or there's been changes to the actual environment in that you're running the code. You want to try to run some monitoring every now and then as a proactive measure to ensure that if there are issues going on, you're picking them up early in the process. And of course, also, if you're running into very unusual situations like slowdowns, bottlenecks, you often want to take a look at that. So problems and solutions. So again, this is where we're looking at summary metrics for completed tasks. And again, we can go and look at the kinds of stats here to see if they're in fact in line with what we're looking at here. So in terms of the tasks and the drivers, what sort of failure tasks do we have, kind of succeeded tasks? One of the more common things is where we have Spark jobs that just don't seem to start. That's often indicative of some kind of configuration error at some point that we need to investigate. So we've taken a look at this already. This is a bit of a rehash. Spark tabs UI and RESTful API. We can get information out of that. So, oh, here it is. Spark jobs not starting. I knew I'd seen this here somewhere. Signs and symptoms. The jobs don't start. Well, that's actually pretty much a sign and symptom all of itself. Spark UI doesn't show any nodes in the cluster except the driver. The Spark UI seems to be reporting incorrect information. So generally, there's some kind of configuration error in how it has been set up. That's a general first place to look. How do you debug a configuration error? Well, one of the when the error is not immediately obvious, one of the simpler solutions is to start with as a simple a configuration as you can. Get a set of test data, because you don't want to waste a lot of time with massive data sets. Get a set of test data, run it, see if it works on the simple configuration. Add more configuration elements to it until you get back up to the original configuration that you were running with, and see at what point the configuration breaks and this job doesn't start. And if it starts when you get up to the original configuration that you had, then it suggests that there's something about what's happening with the data. So then you try it with several different increasing amounts of data. So you see at what point the amount of data tends to not start it. Then you suggest, then there's something interesting here, that the configuration I've got is not, there's something wrong with that, matching up with the amount of data that's expected to be used here. So there could be a couple of different, those are a couple of just kind of generic approaches to solving the problem, to identifying the configuration error. The other couple of points is that in addition to the wrong configuration, maybe your cluster is just not communicating with each other. So we may have some issues involved in networking, down machines, some other kind of situation that is causing the job to not start because it's not getting distributed properly. And one of the diagnostics to that is, are we sure that we're using the right ports? Are there any kind of porting errors that we need to take a look at? So commands don't run at all. And then we have large output messages. There's no jobs, stages, or tasks. Okay, in other words, it just ain't happening. And again, we take a look at the error codes, check for the error in the code, and we also want to double check to make sure that we have that network connectivity. And the other thing is we may not be able to load dependencies. So we made sure that all the dependencies are both exist and are findable by the program itself. So this one is not quite as difficult to diagnose as some of the more subtle ones, but again, look for the error message. Remember again that we don't often, one of the ways that you can actually do this again is to in our development, run it with a very small set of data and do some very simple kind of action like take one to cause it to start and see what happens to the to debug see what happens in order to start debugging where that error is possibly occurring. So we've got some signs and symptoms here. A Spark job runs successfully on the entire cluster, but the next one fails, or a step in a multi-step query fails, or a schedule job that ran yesterday is failing today. And we get really strange error messages. What are some of the things we want to look at? A couple of things you want to look at is, does the file exist? Is it in the right format? So if we're expecting our data to be in one format and it's another format, we can get some very strange operations. If the error pops up fast, the field of the table or field doesn't exist, we can read the stack trace. And then we can also look at the problem that we might have nulls in the data where that might cause some transformations to fail. And again, error in the code. So this is a little bit more difficult to look at, but if we go back and look at it a little bit more here, is that so if we have one Spark job run successfully, but on an entire cluster, but the next one fails, suggests the cluster is okay, but there's something about that specific job that's creating the problem, and that could be either an error in the code or a data issue, the errors we just looked at earlier. A step in a multi-step query fails. This could be because, hold on. This again could be because of things like nulls. We maybe want to take a look and see what actually is the result of the first step in the query to see what's actually being put into that would actually be the result of that. We might be surprised to see what the result of the query is, even if the query itself may be structured in such a way that it's not producing what we think is being produced. A scheduled job that ran yesterday is failing today. A couple of things that might be worth looking at is, was there some kind of change in the operational environment from yesterday to today? So if it worked yesterday, that means that the job itself is probably fine, but is the data the same yesterday as it was the same yesterday as today? And the other point of failure is, has something changed in the operational environment? Maybe the cluster is rebooted and one of the machines didn't come up, or we've got some other kinds of issue that took place. So this is some of the issues that we want to take a look at. Okay, so how do I differentiate where the error is taking place? Well, one of the very simple ways to do this is, if I want to know where the source of the error might actually be, one simple diagnosis is to run your program with a limited amount of data on locally in the client mode interactively without a cluster, and see if the error persists. If the error persists, then it's probably not a cluster management issue. If the error doesn't persist, or if the error persists, it's probably not a cluster management issue. It's a problem with the program or the data. And if you really simplify the data, it's definitely some kind of programming issue. If it runs fine on your local machine, then it's probably some sort of cluster communication OS error that you want to take a look. So it's a matter of just isolating out the various components and seeing what happens. So one of the things that we can do is to always test, as Boris Beiser, the great software testing guru, used to say, if you can't test it, don't write it, and if you don't test it, rip it out. Generally, just having to think about what should happen forces you often to look at the problem in a particular way, which often kind of gives you a different perspective in seeing where potential bugs may lie. One of the things that we always have to keep in mind is that the very things that produce the optimization are the various things that can blind us to certain kinds of errors that take place. This, again, our lazy evaluation. We do a parallelization of a list, and then we do the data transform where we divide each number by 0, and then we map that into plus by 1. And then when we actually, even if we do this interactively, it's only when we get to the collect that we wind up getting an error, because that's the point at which the map is actually executed. So that is certainly something that's going to show up that way. Okay, all right. So now, let me see. Yeah, look in the, if we are getting errors, to remember what stack trace we want to look at, and that is the, in the worker stack trace, as opposed where the code is actually executing versus the driver, which also means that if you are looking at trying to debug this, one thing you might do is actually execute it in the driver with a small amount of data using a take one or something, and see if you can replicate the error in that environment. Okay. Look at the errors reported from the executor, find the line number associated with the function, and then see how that is stacking up in terms of, there we go, in terms of how many times it's reported. Once it's a warning, then it's an error, multiple partition errors. So you get a sense of how this thing is being distributed as an error. Okay, so now it says that we have a lab here we can do, but I'll let you guys take a look at that, lab 9.2, to do some monitoring. So before we do that, any questions? I think this has been a fairly straightforward chunk. Anybody have any questions about this?
Seems clear from our side.
Good. I would have expected that. Okay. I am not familiar with lab 9.2. If you guys want to give it a try, that would be cool. And we'll give you a 15-minute head start on this.
I have a question. I
Yeah.
don't see I don't see the lab number 9.2 in.
It's 09. It's ops. It's called ops.
Okay, you know what? I have a suspicion this is for this slide was taken from a different.
No, but
There is
it is. It exists. Yeah, no, it is.
You got it?
Yeah, I see it now.
Okay, good. All right. Well, I'll check in with you guys in 15. Okay. Or if you finish earlier, let me know. Just give me a shout.
all right. Probably takes maybe 5 minutes.
I guess I should unmute myself. There we go. Sorry.
Yeah. Well, so my question is how to read the output of JMap, because all I see here is some list of libraries, sizes, and that's all. What's useful in it?
I don't know. Let me check onto that. That's not a tool that I'm familiar with. So I'll see if I can find a reference to JMap for you. Okay.
Yeah, because JStack, I understand some other tools also, but this one, not really.
Yeah. Yeah. Okay. Well, let me check into that for you. Okay. I will give you an answer at the start of the next session. Okay.
Yeah. So thanks.
Okay. Do we need any more time, or are we good? How are we doing, guys?
To be honest, I completely don't understand how to make use of those tools because like half of them just simply don't work for me, or maybe I'm doing something wrong, or maybe I'm too stupid to use them. I don't know. And the other half are just providing for me, very useless pieces of information, like the dumps or something like that. So I don't see how can I make use of that lab for me personally.
Okay, and I can kind of empathize with that because I find often these kind of low-level tools, unless you're looking for something really, really specific that kind of jumps out at you, generally they're not particularly good diagnostic tools. You want to really kind of have things narrowed down to looking at a specific JVM. Because now we're looking at something that's really, shall we say, specific. So yeah, I would tend to say that that's a pretty valid argument. But at least the point is, you know that they're there, and we can take a look at that. Okay. So anyway, I think we've probably, shall we say, we've kind of gotten to the point where that we've gotten the any of the value that you're going to get out of that lab. Would we agree that that is probably our point here? We can move on?
I think so.
Yep.
Oh, excellent. Good. I'm glad. To tell you the truth, I really don't like working at that level of doing stack traces and trying to figure out maps. And I know some people love it, but I like to think a little bit higher level. Okay, so now we're going to get into a more interesting part, which is our optimization areas, and we can break this down into a number of specific pain points that we have to deal with in Scala. I'm sorry. I often tend to slip up and call Spark Scala. I don't know why. It's like a mental block I have. So we have a number of traditional pain points. The first thing to optimize, which is just a high-level design decision, is the choice of data representation. And the idea here is that generally, when given the options, we get much better efficiency with structured data. And we always want to try to go with data sets / data frames, which give us the ability to use Catalyst Optimizer. The data at rest, to know the data, to get some understanding of the data, is often it's often very efficient to run samples to test things out before you commit to a major job. Make sure that you understand how the data looks at rest, how it profiles. You get some sense of the data quality that's coming through. Joins are going to be a bit of an issue too, because we can often do things like we do a theta join. We often wind up doing a Cartesian join and then reducing it, and we can get some really bizarre kinds of blow-ups. So if you take, say, a couple of tables, if you do a theta join on a table with a couple 100,000 rows, you wind up getting billions of rows, and it just explodes on you for unnecessary intermediate steps. You want to rethink about how you do joins, and when joins should be done, and what sort of joins should be done. Aggregations, anytime you're aggregating data, it may require things like shuffles. A join certainly probably requiring shuffles, aggregations and shuffles. Data in flight, how the data is being modified and transformed as we go through order of operation, sequencing, individual application properties. What's going on now, we're getting down to a lower level, JVMs, executor, and this is where we're going to get into optimizations like tungsten, memory management, the use of worker nodes, and also the tuning and tuning the parameters of the cluster and deployment nodes. So the design choices are not always good, because are not always obvious, because the choice of how to do your application design is going to allow better performance by optimizers. Choice of the data format and that sort of thing allows you to take advantage of all the optimizations. So so let's take a look here. A couple of other things just from the application side. This is your what language to use, and we're not going to spend too much time on this because I think we come down to the idea that there is a case for R if you want to use R, but generally the rule of thumb is that you are generally going to get better code when you work within a Scala interface, simply because it is more reflective of what's actually going on. In Spark, it's easier to actually look at how the code that you're writing translates into sort of equivalent Spark kinds of operations. So you can use R and a couple of other languages, Python and Java for this. I would avoid Java simply because of the verbosity. Python doesn't take advantage of all of the features that you can use with data sets, and R is limited in some ways, but since I don't use R at all in this environment, I can't recall offhand exactly what those limitations are. Data frames and RDDs. There are some times when you need to use RDDs when you're doing very customized transformations that just don't work within a structured API. But again, if you're doing this, you're going back to Scala. You want to restrict the surface area of RDDs. You want to keep that window between your code and the RDDs as relatively direct as possible. So there's again, good options for avoiding Python. So other factors you want to consider, and we'll get into some of these in more detail in the next section. Cluster configuration, but again, you're going to have to do some monitoring to ensure that your cluster configuration is dynamic allocation, so you might want to experiment with that. Scheduling, data at rest, storage system, how we're going to lay it out, what's the appropriate, based on the appropriate structure of the data. Splittable file types, looking for files that are easy to split and parallelize, and table partitioning and bucketing. And we'll talk about bucketing a little bit later on when we get into more of the optimizations. Other storage factors are the use of small files. In other words, file size itself, and we saw that there was some implications for performance if you're doing raw versus serialized in terms of size or performance. So we can also get around that by using some kind of compressed formats, and we looked at the serialization parameters the other day. Data locality, the ability to access the various storage locations for the files. The other thing we want to look at, which is particularly important, is the shuffle configurations. How to set it up so our shuffles occur as few times as possible, and also to ensure that our shuffles are, when they're absolutely necessary, are as economical as possible. Garbage collection tuning, generally something we don't tend to worry about too much with Tungsten and some of the off-heap systems. How we share data with things like broadcast variables. Broadcast variables are when we need to put data that needs to be accessed by every worker in our system, every executor, but what we can do is transmit in a very, very efficient manner a read-only copy of that data as a broadcast variable to make it accessible to everybody in the cluster. This is something that can then be referred to as a reference data that may be necessary for some operations, but you can use it across a number of different Spark actions. There's no need to continually resend it. So it's a special kind of data transmission that is intended for reference data that's going to be reused. It's not going to be changed. It's immutable, so it doesn't require any special considerations. Accumulators are another form of shared variable, which depending on what we're doing with it can become expensive or fairly cheap depending on how we've decided to structure the code. And it's where we're basically pulling together data from all the tasks into a shared result. So counters are an example, doing a count is an example of having a distributed shared variable. So broadcast variables are the normal way to use a variable. We could reference it as a free variable in a function closure. I'm assuming everybody here knows what a closure is, right? Anybody not know what a closure is?
In Berlin, we know, I think, yeah.
Okay, good. So that would be a way to do it, but that tends to be inefficient because it's now encapsulated within a particular function. It doesn't allow for a lot of reuse. So it's just doesn't have the efficiency. So what we do is we use broadcasting as another way of transmitting that data around to make sure the data gets out to all of the executors that are going to be requiring the data. Caching can be useful if we are going to, we saw this earlier, so we have a very, very expensive operations. We could cache the result at various points, and that allows us to not have to repeat expensive operations. Another example is joins. We'll get into that in a little bit more detail later. It's a very large topic. Aggregations, some aggregations like reduce by key are more efficient than group by key, because group by key is going to force a shuffle, whereas reduce by key is a little bit more efficient in that respect. So broadcasting variable is it's a large piece of broadcasting. So if we have a large piece of data, it's going to be used across multiple calls in a program. We're basically saving that single read-only copy. So what we're doing here is basically pulling some data out that would normally go with each job, sending it out once, and then having each job refer to it. What it does is it cuts down on the amount of transmission, it cuts down on the amount of moving data around the network. So by doing that, we're speeding up a lot of the, we're speeding up by avoiding a lot of unnecessary overheads. So here's an example of going and broadcasting the data. We now have our thing called supplemental data. It is going to be a map where we're creating of some data. So, and then we create a broadcast variable. And then we broadcast out that to the we broadcast that out to the executors, and then to actually use it wherever we need to, we just refer to that as on the executor, as we just refer to that as the getting the value of that broadcast variable. Okay, so behind the scenes, that's been pushed out, and so that data is available everywhere. It's read-only, so it's going to doesn't have to be serialized. It's generally going to be handled so that it's going to be accessible easily and quickly to whoever needs that data. After you do broadcast something, you can clean it up. So we can destroy the cleanup. We can write it. We can destroy the variable. We can unpersist it, which is to delete the cached copies, and we can unpersist it with delete the cached copies, get the value of the broadcast variable, get a string version of it, get the ID. So there's a number of things we can do on cleanup to get it to actually manage it efficiently. So we send it out and then we clean it up after we don't need it. And I think this unpersist Boolean blocking, I think this actually, I have to check and see what that's supposed to do there. I didn't see it. So the, couldn't read the whole thing. So the accumulators are pulling the data back to the driver through the accumulator, it updates values in a from the actual transformations back to the driver node. We've always seen that, so that's fairly straightforward. It does it in a particularly efficient, fault-tolerant way, so it's designed to bring that data back in a way that reduces risk to any kind of corruption that takes place. It's an immutable. It is a mutable variable, so it is obviously everybody's going to be able to write it, write to it in that sense. It can be updated. We can also use it for various kinds of bugging and tracking. We want to make sure that we've gotten the right results of something. So we might want to, for example, go and get a count of how many rows we've got after a join or something to make sure that things are working the way we think we should have them. So we can use this to double check to make sure that our results are in fact what we think they should be. Hold on here. Okay. Let me see. Okay. Oh, and of course, we also implement them is to bring back counts and sums. Okay. So memory management. We're going to get into that in a little bit more detail when we get into Tungsten. So we're going to talk more about that, but there's a variety of different memory managements and other things that we've got for memory management, or the use of in-memory file systems, and the use of caching and other kinds of things in order to improve our overall memory management. The other thing that we can look at here is the choosing the appropriate cluster size through the Hadoop administration. Then we can also take a look at the memory management that takes place in each one of the executors. So by default, another kind of distinction we make here in terms of performance is that when we've got RDDs, we're still using Java serialization. And that's because we don't have that typing taking place that can be used with Tungsten-based. So we're kind of doing a Java serialization, which is not necessarily effective. And there can be a lot of overhead involved in the, or not overhead, but a lot of inefficiencies that take place in Java serialization. So as we move into data sets, I think that should be data frames and data sets. What we really need to be able to do is to indicate that those two underlying formats allow us to take advantage of that Tungsten serialization that gives us the much better performance. So if you want some kind of similar operation with RDDs, then we use the Creo serialization, and I think we'll touch on that a little bit later. So those are some of the operations that we've got. Now Creo is it does not do everything that Java serialization does in terms of Java data types, but what it does do is it may do enough that it meets your needs that are adequate. So it does tend to work similar to Tungsten. Depending on what you're using it for, there are times when it can be somewhat faster, but you have to set into an unsafe mode, and we'll talk about what unsafe means, which is basically bypassing a lot of the JVM memory management. So we'll grab some notes on Creo as we go along. Okay, so this is just kind of a high-level overview of where the different optimizations are. And one of the kind of overall messages that come away from here is that optimization is a multifaceted approach, starting with thinking through the data sequence of operations, where you're likely to encounter shuffles, what kind of data representation to use, making sure you've got adequate cluster size, taking a look at the size of the data, look at the kinds of computations, but then also experiment with sample data in interactive mode to ensure that your assumptions about what Spark is actually going to do are in fact correct. Okay, so that's primarily that, and a couple of final points is use the UI to always monitor what's going on, and also minimize shuffles. That can often be done through a couple of techniques. For example, it's surprising, but using bucketing of data can often eliminate a shuffle by virtue of how the data winds up getting distributed across partitions. So we want to keep all of those things in mind. Now, we're going to go into more detail on a number of these things as we go through. But what we'll do is ask at this point any questions before we go on to the actual performance tuning section. How are we doing, guys?
Great, I think.
Yeah. Everything working for you so far, making sense?
So far makes sense, yeah.
Okay, good. Thank you. Okay. All right. So now we get under the hood of Spark. Okay. So here are, and I don't know who came up with this, there's 10 Spark 10 commandments. Okay, so let's go over them quickly. Use the Spark UI. Constant feedback always helps. Understand Spark internals. That's what we've been doing, trying to figure out exactly what's going on in Spark, how things move around. Filter early. The more you can reduce data before you work on it, obviously, the better it's going to be. Minimize shuffles. Again, fairly obvious at this point. Effective joins. Make sure that the joins we're working with are not going to blow up in our face. Caching. To avoid repeating expensive operations. Broadcast variables, so that data gets out, and so that common data that's going to be referenced by all of the executors gets out in a very efficient way. Use data frames wherever possible in order to optimize through Catalyst. Use a good distributed file system that gives location hints and is able to provide information that's usable by Spark. Monitoring is, again, always monitor to ensure that what you think is going on is in fact going on. And number 11 of the 10 commandments, get involved in the community, which actually was a bad idea because you tend to see a lot of interesting things coming up, hints that are often very useful. It's hard to figure out exactly where the community is sometimes, but that's part of the risk that we run with these lovely open source projects. Spark UI, again, we've taken a look at this where we can take a look at the jobs, event timeline. You can generally tend to get a pretty good overall picture of what's actually going on in your Spark environment. And again, that's the UI we've been looking at 40/40, task execution time. So we can always go and double check to make sure that things have done exactly what they were supposed to, or what we thought that they were doing. Now, there's another thing we want to take in that we haven't really mentioned up to now. This is the notion between wide and narrow dependencies. When we break a task down into when we look at a step in an operation, like a transformation, if the transformation does not require a data reshuffling, it's generally a narrow dependency. So something like a map operation, or even a flat map operation would be an example of a narrow dependency because it doesn't require referencing more than one item of data. in order to perform its operation. Why dependencies are where you have often a necessity to reference data that may be in other partitions, and it's going to generally force some kind of shuffle to take place. So map, for example, is a narrow dependency, and we can pipeline the operations, because we don't have to transfer data, reshuffle data in order to perform the operation. So the output of a map operation on a single data item only depends on the data item, so we can basically proceed in parallel. If we have a series of maps, all of them can be pipelined, and they can execute without us having to move any data around. So the reason why it tends to be particularly useful is that if this child partition here only depends on this one parent, this child depends on this one parent. So now we've got a sequence of operations that require no contact with any other data. It is now pipelined. So now, once we've got a pipeline task, then we have very efficient tolerance. It's very, very cheap to recompute or to calculate the outputs of that. Okay, now a Y dependency is where each one of the each one of the children has a dependency on potentially multiple parents. So one parent partition is used by multiple child partitions, and so because of that, we need to shuffle the data across the nodes in order for the parent partitions to become available, and that's where we start to get into expense costs. It is involving network activity. It may involve some kind of disk activity in worst cases, and so suddenly we're taking a performance hit. And the other problem is that if we do have to do a recovery here, so we're no longer working within a single node, so we need a multiple node recovery, and that itself can also incur some additional overhead costs. So so we have various kinds of dependencies here. So we have a narrow dependency for a map and a filter. A union's also a narrow dependency. Again, simply because you have to look at the where we determine this is the number of the partitions. So we have inputs join with our inputs co-partition, so that we don't have to reshuffle on the data, and then we can actually do a very nice join just by without having to do reshuffle to actually execute it. And we'll take a look at a little bit more about joins later. If we have inputs that are not co-partitioned, or in other words, pre-partitioned in a way to make the join work, you can see just by the multitude of crossing lines there, group by key and a joins can result in some incredible inefficiencies. Okay, what Spark will try and do is try to use a number of strategies to make the operations as efficient as possible. So it tries to, number one is to pipeline narrow operations so that it can process them very efficiently and do that effectively in one node. Ideally, you want that stage each stage is going to be as big as possible, where you can pipeline a lot of this stuff without having to do any kind of reshuffling. So it's also uses some partition awareness, so that by using some kind of prior processing, what it can do is avoid some shuffling on joins. And again, we're going to come back to joins here. So again, being aware of where the data is located with various kinds of partitioning strategies, you can get a little better performance on joins So there's another strategy to go on there. And the ability to reuse cache data is also going to allow us to get some better efficiencies. So Spark will attempt to use these kinds of efficiencies to try to get something's worked here. So in this particular case, if we are doing some kind of stage one, getting some partitions out here, and then we are able to actually use this pre-computed to simplify the input into this process here. Whereas down here, we get another stage two. We've got some streamlining here, and we've got some nice things here, so we can get some better usage here in stage three. So in other words, Spark is going to try to utilize what it's got before to get where to get the data organized in the right spot. And that's a topic I believe we're going to touch in a little bit later on as well. So again, we're going to come back, and I'm not sure how much is in the notes on joins, so I'll probably add some material on joins. So I'll try and find some references that we can utilize as class material to do that. The filtering process, filter out invalid data. Again, the idea here is less is always more when it comes to Spark. The more data we can throw away earlier, the better it is. Filters are really cheap in the sense that they don't require any kind of reshuffling of data. They're generally a very memory-focused operation. They work really, really well. So and again, an optimization is always to push filters close to the data. We can also wind up with uneven filtering. And again, there's a couple of strategies we can take on the data to try to get a bit of a balance. Coalescing is where we wind up with a filtering, and we wind up with unbalanced partitions because of the filtering. We can coalesce to balance them out, but we have to make sure that we've got an actual rationale for doing that. So there's our example here. This goes back to the first day. We're filtering through a log file. We get all the error files, and we wind up getting an unbalanced partition. So we've got, and again, very small set of data. So we can coalesce and get back some even partitions. So the question is here, is that really worth the cost? So that is going to produce a shuffle. Okay, so the other optimization is to minimize our shuffles. So we want to design so our part of this is design the transformation to minimize the shuffles. So we take a look here at the two operations here. So I think this first one here, I can't really see it quite that well. So we have our serialized little word list. We split it into words, and then it says this looks like a reduce by key operation there, as opposed to a group by key and then doing an operation. So the pairs on the first partition are combined first, which produces data is shuffled after this. So we're doing a reduction here, and we're getting a reduction in size. And the group by key is the data shuffled, or actually go back to this one. So we're reducing the amount of data that has to be shuffled here. So that is going to give us a little bit of a performance benefit, whereas we do the grouping first, we get a lot of data that's going to be moved around before it's reduced. So in this particular case, we do a reduce by key before you do anything. Because we are going to have a shuffle, it's going to be inevitable. So the question is, what operation do we do to reduce the amount of data that has to be shuffled around? We also have a shuffling on a join example. So we have an RDD here. We've got some kind of URLs with visits. We winds up getting a visit of visits, and we've got an RDD of URLs with names. And what we want to do is produce a join so that we can get a list of let me see, visits. What are we joining on here? So we're going to, about the HTMLs, we're going to join visits with page names. So we're going to be adding the page names onto the into the table. So visits can be really, really large. So there's a lot of data to reshuffle when joined, especially if you join it more than once. This notion of hash partitioning is bucketing. And what hash partitioning does is basically redistribute the data in a way that makes it easier to execute the join. So in this particular example, we're taking the visits partitioned, and we're actually going and partitioning it by a hash partitioner, which is the essentially bucketing. And then we're creating the new variable, and then we're doing the join on the visits. Okay, so what's actually happening?
Sorry.
Yeah, go ahead.
Quick question about the hash partitioner. We have that magic number there, 2. What is it referring to, and how should it be selected at best?
You know what? I'm not exactly sure on this one, because as it stands right now, this is by default in the latest version of Spark. This is done by default. Okay. And I think you can tune it there. And I don't know, I can't remember exactly what the tuning parameter is. I think that is
partition.
Yeah, the number of partitions, I believe. But generally what happens is if you just turn on, you should be able just to check to see, by default, this is from, I think, Apache 2 something on. I believe it's on by default, but generally there's a default that is normal. You can often let Spark determine the appropriate parameters based on things like cluster size and executor size. Okay? But that's a good point. We'll come back and look at that later. But yeah, but basically what it does is it creates, this is particularly useful when you have, and you can tell in advance that there's going to be an unbalanced join here when you've got one huge table and one sort of medium-sized table. So
I actually have one more question about this. Sorry.
Oh, sure. Go ahead.
So we want to avoid a join because this join implies a shuffle of a potentially huge table, right? Mm-hmm. But doesn't this partitioning or repartitioning somehow trigger a shuffle as well?
Yeah, well, it does, but the idea is that this is handled much more efficiently because we're basically shuffling the data as we load it. Okay, so in other words, instead of loading the data and then shuffling it, what we're doing is we're kind of pre-shuffling the data, then loading it. So there's where the efficiency takes place. Does that make sense?
Okay, so yeah, so this partition by is something that you apply on the boundary, on the input boundary then.
Yeah, exactly.
Okay.
So by doing that, we're avoiding both a read and a write stage in the shuffle. Okay, so technically this is called a pre-shuffle. So it's shuffling as the data is being loaded. So it's more like almost a random, it's a hash distribution into the partitions, which tends to be more efficient from a processing point of view. Well, that's a good point. So the other okay, so the other thing we've got here is the share the data from the application. In this particular case, what we're doing is we've got our visits. We're putting out the visits, page names into there. And then what we can do is collect the page names into the map. And then we can utilize that. So what we're doing is if we're getting a small amount of data that we are going to be using, we can send it in with all of the send it in with the request. So copy to the master and then send it out to all of the tasks. Then we don't need to actually do a join. There's an optimization that can take place there, because now we can actually don't have to do any shuffling, because we can do the various join on the various partitions and then coalesce them, not coalesce them, but then combine them in a nice reduction. Because when we can do this, because then we can broadcast this across the network or the cluster. So the idea here is that our example now that we did is we create our visits, create our page names, and then we convert the page names to a lovely map, and then we go and we broadcast that across the nodes, and now we have are able to go and reference this in the as we saw before. Okay, so we've got the that particular piece of value here. And again, because it's a pair, we're referencing with the pair notation. So what we're actually doing here is we're able to actually think about in terms of sharing the data, and then instead of having to an actual join, the use of the broadcast variables enables us to avoid having to do a join at all, and then we're just able to actually do some kind of map reduction here. So the idea here is that what we're doing is we get a better kind of performance efficiency. This is a workaround, again, when we've got one set of data that's relatively small, and this works effectively when we can do this. When we get into very, very large data sets that we're looking at joining or self-joins, then this is no longer an effective strategy. So we'll take a look at that what we do in those cases starting tomorrow. Okay, so the broadcast variable, you can see, now starts to become really useful. So let's build up that use case for the broadcast variable. It is when we want to get the same piece of data across multiple nodes. So the so if we stop and we think about what our join is going to be, if we had loaded all of these, if we'd loaded these two data sets and all of the nodes, then we are going to, when we do a join, it's actually going to trigger some kind of shuffle mechanism, do some kind of join, because now we've got to join across all the partitions. But if we can take some of the data out and put it into a broadcast variable and send it out to the different nodes using a broadcast, and then avoid triggering a shuffle through a join, we can still achieve the same effect by using some other kind of transformation. So this is kind of a strategy for optimization by avoiding doing a join at all and triggering the whole process. Obviously not a solution you can apply in every particular case, but certainly something that does tend to work. Accumulators kind of add in
Can I ask a
parallel.
question?
Yes, go right ahead, please.
So if I'm understanding this correctly, avoiding joins is basically what we want to do in every single case.
No.
Correct? No?
Well, if there is a way to avoid a join, that's probably a good strategy to take, but it's not going to be practical in many cases. There are going to be sort of special cases where, oh, I don't have to do it. I think that the time you really want to look at avoiding the join is where you've got two sets of data. One is very large and one is very small. Then you really
definitely
have to wonder.
So in those cases, it's always beneficial to look at getting rid of the join.
Exactly.
Okay.
Yeah. A join is overkill in some of these cases. You know, like if I'm looking at, again, the population of Europe joined with a list of countries of residence, you know, a join on that is a little bit of overkill. I mean, I'm just doing way too much work. There's another way to do that kind of association without having to go into a join. So, I mean, I've got, I know, tens of millions of records on one table, and I've got, a small handful of records on the other table. So, this is going to blow up in my face and create massive problems.
So if Spark is already doing pre-partitioning for me, it also should know about the cardinality of both data sets. So in principle, it could do these optimizations by itself, no?
No,
just a theoretical question.
Somebody else is adding in there?
Yeah, the default partitioner, it doesn't take out the cardinality and doesn't distribute, for example, data equally. So you might end up with like big partitions, small partitions, depending if you let Spark figuring it out.
Yeah, Spark isn't really able to make a lot of really good inferences about the shape and structure of the data, but what it can do is it can kind of randomize partitioning and distribute things into different partitions, but one of the problems is that it's not smart in some of these things. So what we actually wind up with bucketing is not so much a nice dealing with cardinality as more dealing with different kinds of groupings of data that could take place. And I think we'll come back. We're running out a bit of time today, but we can talk about bucketing and what that actually does tomorrow, for example. Okay, so yeah, the primary strategy that we want to look at is there a reasonable and efficient way to avoid doing a join? Is a join really what I need to do at this particular point? What is going to be the intermediate effect of that join? Am I going to get a really, really big data set as an intermediate step in the join process? Or when I look at the nature of the problem, is there a simpler way to work with that? Rather than doing a join across all of the partitions. Okay, does that make sense?
Yeah, it makes sense. I would actually like to see an example where, well, I have a Spark SQL query, and I want to avoid a join, but at the same time, I would like to keep that high level. So, like, how do I make it such that it's not that I'm dropping into the low level of, okay, I'm obviously going to have to distribute that variable.
Yeah.
But at the same time, I would still like to keep that high level flow. I would like to see an example of that, but yeah.
Yeah, and what we're really, what I'm really talking about here are sort of like edge cases, okay? Where, and I'm kind of mentioning this is where even, if you could look at the data, you could think that join is actually a bit of overkill. So this is not going to be the approach you want to take with generally everything in this sense. But again, we've got these edge cases where we've got these really disparate. So, for example, if you're doing some kind of self join, obviously this approach is not going to really work all that well because it's kind of counterproductive and doesn't even make sense. But for those edge cases, we're looking at places to do efficiencies. And we sometimes, when we have this really disparate cardinality in the sets we're joining, then we might say, well, do I really need to do a join in this particular situation? So it's just one optimization. But again, the other thing we have to keep in mind too is that very often, if you are working with an SQL-based kind of query environment, you like you said, you want to keep that structure, and then we'll have to look at a couple of the other optimizations that we can do that would accomplish something of the similar effect. Okay, so one of the points that you've made here, which is true, is that we've got this interesting dichotomy between what we're seeing and visualizing at the conceptual level, which is a nice join, versus the reality of the cost that's going to incur at an operational level. So sometimes when we want to do optimization, what we want to do is, or sometimes we're forced to make a decision between keeping our conceptual model intact or going and trying to optimize our model so that it gives us the best performance. A lot of this you don't have to worry about in great detail, because most of the standard use cases or most of the standard kinds of problems we encounter in kind of that, within a couple couple standard deviations of the typical use case, are going to be able to be handled by the Catalyst optimizer and some of the other tools that are available, because again, it's looking at fairly standardized types of operations. But things like the edge case or using an RDD, you may not be able to do that. So you might have to come down to these kinds of operations. Does that make sense?
Yeah, makes sense.
Okay.
Thanks.
All right. Well, it is now actually time for, wow, I don't know about you. I found that went really fast today. So it's 6 o'clock. So that means it's dinner time for you guys. So I think I don't want to hold you back. So I'll answer a couple of those questions you posed tomorrow. And what we'll do is we'll also start talking about Catalyst and some of the other things. All right?
Yep.
Thank you.
How did you have a good day today? Did this session work well for you?
Long day then.
Yes.
Yes, good. I hope you guys learned see that was useful. Okay.
See you tomorrow.
Have a good. See you tomorrow.
Bye.
Bye.
Yeah.
All right. So I am going to continue. Oh, by the way, first of all, in the Slack channel is the, I fired up the machines this morning and got the new IP assignments on them. The ones in blue are the ones that I got the note for that you wanted the old machine, not the new one that I'd set up. So if you wanted the old machine and it's not in blue there, then just let me know. And I still got the image, so I can just fire it up again for you. So I didn't delete, I only deleted the images, the ones that you specifically told me you didn't want the new ones. So it doesn't really cost anything just to keep the stock instances around. I'll just keep them there for safekeeping. So there's that. And hopefully I didn't make any mistakes copying that up. What I am planning to do today was that I am obligated to at least go through the material cursorily, which we will do very quickly. But I want to spend a focus into a deep dive into Catalyst today, and to look at a couple of issues that I know are not in the material. So what I am going to be doing is I am going to be making some notes as we go along on the major points, which I will then save into the Slack channel at the end of the day. Or I may flesh them out a little bit and save them in later on today for me, which would be tonight for you, so that you have a record of what we looked at. Plus, I'll try to bring in specific references, so you're not rooting around on the internet trying to find things. And I tell you, the more I've gone into the deep dive on this, the more I am really impressed by the capabilities of being able to combine multiple sorts of optimizations, and hopefully we'll get into all of that. Now, tomorrow, I want to really be able to focus on the memory optimization with tungsten, and sort of how to tune the tungsten parameters. But I want to spend today mostly looking at the Catalyst in terms of the optimizations, and I will be trying to create some examples as we go of what these optimizations mean, and the kind of the underlying strategy for them. Some of these optimizations are as of Spark 2.2, so a lot of the material that's out there that you find is in Spark 2.1 sort of, or earlier, so it might not have quite the same level of detail that some more of the current material has. Okay, so we're going to, does that sound like a good objective there? So,
Sure.
Sound
Sounds
like a
good.
plan? Okay, good. All right, so well, I'm just gonna very quickly catch up to where we were. So we did a number of these things. We looked at the Spark UI and the internals. We talked about the wide narrow dependencies and how what that meant in sort of the planning stage in terms of pipelining tasks and making sure the tasks get pipelined. The thing we started to get into was this notion of the shuffling. And the more I thought about it after class yesterday, the more I realized I may not have articulated this in the best possible manner. So I will go over a couple of these points again, this time trying to be clear and convey my ideas in an understandable manner. So we looked at the kinds of dependencies that we have here. And again, what we're always trying to look for is to structure the storage of the data in this distributed format to minimize the number of wide dependencies. And there's a couple of various strategies that we do that. So the Spark optimizations, this is a kind of just a general idea. We've looked at a number of these things as to cache previous computations. There's a number of things that we can do from an operational point of view. And one of the ideas, so the idea is that what the current version, what Spark 2.2 done is actually try to incorporate a lot of the ideas about know your data into the optimization plans. So the optimizations themselves are going to actually make any kind of planning that you do earlier that you can do from an obvious point of view more effective, because it just cuts down on the computation that the Catalyst will do. But theoretically, although I always hesitate to believe that theory translates directly into practice, it should be able to optimize almost anything that's kind of generated as a query. But again, I'm going on the basis of the claims of some of the people who've designed it, and I know that it's their baby, so I would take that with a bit of a grain of salt. But it is still a very, very impressive piece of work. So one of the things we want to try to do is narrow the pipelines, and that is again trying to limit operations so that we're trying to avoid shuffling in general, and particularly on joins. So any kind of grouping operation, any kind of reorganization of the data is going to be something that could induce a shuffle, and we want to try and avoid that. And one of the more interesting things I came across a while ago was a presentation by somebody from, I think it may have been IBM, who pointed out that when they were looking at one of their large projects, the amount of cumulative I/O that they had over the network was about 18 years when you added up all of the I/O operations. So they realized there was these really significant bottlenecks. So because shuffling invokes that kind of I/O overhead, then you have to try and avoid it. When we're talking about memory access in nanoseconds and disk access in milliseconds and I/O access in necessary of tens of milliseconds, this sort of adds up quite a lot. But again, we'll get into some of the tuning of the caching tomorrow in particular. But the underlying concept here is that by profiling your data, you get a general sense of kind of what that data is going to be looking like. So so filter early, that's going to be one of the optimizations. We did that already. We discussed that. Here's an example of doing a shuffle from coalescence. We did that already, so we can skip through that. A notion of minimizing shuffles. Okay, so the excuse me, for, there we go. So the standard way of distributing data in the absence of any structural information is to basically try to develop nice balanced partitions by doing sort of a random distribution of the data to the partition, so we get a nice even distribution. And of course, when you do that, if you've got structured data, you may wind up with data with the keys appearing in different partitions, which is going to force a shuffle. So the hash shuffle is going to bucket the data by hashing on the key value, although it can be hashed on any column. The most typical column is going to be the key column, because that's the one that you're going to want to use, and that's going to produce an unbalanced distribution, but you are going to be guaranteed that your keys are going to be distributed so that the same keys are going to appear in the same partition. And the problem with that is that you may get very, very unbalanced partitions, which then produce performance bottlenecks, because you may have, no matter how fast or how many nodes you've got, if you've got one node that has a significant amount of data compared to the others, parallelism really can't proceed, because that node is the bottleneck. And so there is a certain cost to that, depending on the actual size of the imbalance. So when we get into the catalyst, we're going to say we're going to try and find a way to actually reduce that kind of negative outcome from this. So one of the things that we can do, of course, is we can also just designate the number of bins, which was that number we saw in one of the operations the other day, to actually do that. So reduce by key, and we went through that example. Group by key, shuffling on join. So here's the idea, is that if we're just doing a straight join in the normal way, we wind up producing a shuffle at some point, because we've got to organize the data into a join. So this is where we get into this hash partitioning, where we're basically shuffling the data around using this hash value. In this case, we're shuffling it into two partitions. So I think there's another option there we can use to also specify other sort of inputs into the hashing. But like I said, generally it's going to be the key value that you're going to use. If you don't have a key designated, I think you could just designate a column. But excuse me, this is so annoying. So rude to cough into your microphone. There are kind of like manual optimizations that we can do here. And this even alone can save significant data. But again, there's edge cases where we might run into problems. The other thing that we can do is share the data from the application, so we can basically say the data. That's what we were looking at before. And so now we have the opportunity to look in certain cases where one of the tables in the join is small enough to fit into memory. Then what we can do is, instead of having to reshuffle, we can basically distribute the data in the various partitions, then broadcast out the table, and do a hash join on the various partitions. So we don't need to reshuffle anything in that particular value. So that broadcast join, and do some kind of hash join on it, is going to keep the amount of shuffling down. So broadcast variables, to do a broadcast is going to improve considerably the performance by reducing the amount of shuffling. So if you've already got the data load it into partitions. Again, you don't have to reshuffle in order to do the broadcast join. So the broadcast variable here is a very effective way to work on that, because then you can just do your merge afterwards, and it looks quite well, or quite efficient. So we talked about accumulators. Using data frames. This brings up, I went back and looked at, because I was really, like I said, curious about some of this stuff. There we go. I think it's this one here. And I'm not going to go into this, but I'd mentioned this yesterday. I wanted to look at it. This was the diagram that I thought was fairly impressive. Is the fact that these Parquet files in particular are, as they said, both encoded and compressed, so that the encoding gives speed of serialization, and the compression also gives reduction in time. And the file has sufficient amounts of metadata that you can optimize the various retrieve serialization and deserialization techniques. So one of the optimizations we've got at that point, which is useful, is again choosing a file format so that we can actually serialize the data properly. So again, the performance we're seeing here is mostly because of the improvement of the introduction of the catalyst. So we couple that with a really powerful serialized file format, and we've already got some fairly useful optimizations, particularly when that file read IO may actually involve moving large amounts of data. It's going to be take less time to actually set it up in memory. So the two ones I'm seeing more and more that people are really pushing are the Parquet, which and the other one, of course, is the ORC. So that's the good file system. We talked about that. We're not going to get over that. We're looking at monitoring again. We mentioned that, so I'm not going to beat that one to death again. And now this is sort of where we kind of left off yesterday. And one of the points about tungsten is that we are not going to really want to utilize garbage collection. One of the reasons why is that in order to enable garbage collection, the Java serialization or the Java memory management uses up far too much memory. So I think, as somebody pointed out, it was like an 8-byte Java string gets converted into a 48-byte memory representation. So we get really weird kind of explosions in memory, particularly using a lot of textual data. And then, of course, we get the problem whenever the garbage collector is running. It's freezing everything, and so this is just not the model that we actually use at in this particular case. So we're going to come back to some of these options tomorrow, which is what we want to take a look at. So again, we're going to be using memory management that avoids that kind of garbage collection. So this is the other option here we're going to deal with. So I think the concepts we want are in here. If not, then I'll basically mention them. So Creo serialization, because we're going to be dealing with that in memory, we'll touch on that briefly tomorrow in a little bit more technical detail. Excuse me. But there's also some good best practices that I'll link up to at some point as well. Okay, so tuning for memory is something we're going to really focus more on tomorrow. one of the interesting comments I came across by somebody was that we've reached a point in this technology where the actual physical distance from one location of memory to another location of memory seems to have an impact on performance. So there's also interesting work being done at the hardware level to introduce more efficient layouts of actual physical silicon on chips to improve that. It's just a side note. It's really nothing that we can have any control over, but it just means that the hardware is getting better and we want to be able to utilize it. So tuning for CPU. So there are a number of ways to tune the CPU. So, and I'm really not familiar with a lot of these, but I will go over them anyway, just to mention that you can tune up various kinds of performances on on the various kinds of processors that we're using. This might be a little bit more than you actually want to accomplish. But what happens is that you can go and use various kinds of I'm not sure if these are hardware accelerators or just options on the hardware you can use, but there are. But at this point, we'll just note, if you're really looking at this, if you're looking at the hardware, you're going to be able to tune some of the CPUs. Obviously, also doing things like using GPUs and other kinds of more powerful processing hardware is also going to improve overall performance. But there's always going to be an actual cost associated with that. Now, storing data and Alluxio, this is where you're looking at cloud-based solutions, where Alluxio is my understanding that Alluxio is sort of like an intermediate file system. Let's see if we can just find a picture of it. I would find that useful. Alluxio, and let's look at images. To see how we're doing here. Alluxio approach. It's just showing relationship with all the products. This might be what we're looking for here. Spark Data Alluxio. So it's a unified storage interface, and my understanding is that primarily it's designed to be used with cloud-based big data solutions. So it is again another way of putting an intermediate fast caching layer that you can use. So what you're doing is really using this to cache data, cache it in Parquet format, and you've got another optimization at that level. So now what the optimizations we're looking at here are really kind of very simple and straightforward, which is do anything possible to avoid caching things onto disk, to avoid actual disk I/O, and this includes things like putting Ignite, Alluxio, and other kind of in-memory file systems where you have them to be able to do that. And we'll come back again to this a bit later on. So we took a look at that as well, and so that was our notion on that. We talked about the deployment models, so we're not going to I think get back into this. Oh, maybe we didn't. This looks similar to what we did before. Use cases development, standalone manager, local file system. Don't need to incur the overhead of using operational resources. Production with Hadoop, cluster manager Yarn. With a file system, HDFS. Again, these are sort of the things that work nicely together. No Hadoop, well, then you use Mesos file system, then like S3. And if you've got streaming, Yarn or Mesos over NoSQL like Cassandra or HBase. So there's different kinds of combinations. Depending on the use case, for different kinds of calculations. Okay. So the Spark file system choices, the ranked on a number of various kinds of features. Data locality, so NoSQL and HDFS come up that because they're actually being stored locally. Obviously S3 is none, it's up in the cloud. Network file system, yeah, okay, kind of a compromise. It's somewhere there. Throughput, again, you're looking at the localities you would expect and the design of the underlying data structure to be highest for things like HDFS and NoSQL. NoSQL shards very nicely as well, so it has the ability to scale horizontally quite nicely. Throughput for S3 is going to be obviously low because of latency issues and other sorts of things. NFS, same thing. Latency, again, it looks like the local ones, NoSQL, HDFS, because of their structure, are going to come up best. Latency, again, Amazon is in the cloud, it's high, so it's going to show up on that issue. For readability, this is the interesting one because reliability, I said readability. HDFS is the best, and Amazon is also very high because of its built-in redundancy and automatic backing up of data and fault failover design. And NFS is obviously very low. And the cost, of course, is going to be variable. So again, the only thing that you can say about costing here is that as far as Amazon goes, it's a cost on usage model. The others employ some kind of also capital expenditure in order to be used. Okay, so Spark and Hadoop. The idea here is that Spark can sort of leverage off a lot of the things we've already got. So a lot of the deep, the big data infrastructure can be leveraged by Spark. So there can be some efficiencies here in terms of not having to do a lot of data moving around and shuffling, and not having to reformat or transform a whole bunch of data that already exists. It already is accessible to Spark in these multiple sorts of systems. So the other thing we had was this notion of the tuning, where we can get HDFS to provide as hints, location hints, so we're better able to actually pipeline and do look-aheads in terms of reads and writes, or actually more in terms of reads. And we have the various kinds of cluster managers that can be used from the Spark driver. We looked at the model of how that gets deployed out when we're using a cluster manager versus when we're using a client mode earlier. So again, using a good cluster manager speeds up the overall efficiency, because now the actual delegation of work and monitoring on the actual cluster is being managed by a specialized and optimized by the cluster manager. So the cluster manager, Spark standalone, and Spark standalone, again, cluster manager is generally one we're going to use for development environments a lot. Apache Yarn is generally what we're going to be using when we're sitting on top of a Hadoop cluster. And Mesos is a more general one, another cluster manager that comes out of the Spark family of developers, and also supports multiple frameworks in addition to Hadoop. So on the standalone architecture, the JVMs, again, we saw this before. Workers create executors which contain tasks, and there is a so the driver goes to the standalone resource manager, and Zookeeper is the manages the fault tolerance on the system. So we're leveraging or we're delegating off the fault tolerance into the general cluster management overhead rather than having to worry about it. So that's the standalone architecture. Zookeeper is still there. The Yarn, again, manages it. Zookeeper is still there through fault tolerance. We're still seeing the difference here on the cluster nodes are the workers for the standalone as the worker JVMs. Now it's a Yarn node manager that's managing the clusters on the Yarn distribution, and again, Spark is designed to work on top of it, so there's some easy configuration. We set the various environment variables, and we have a number of Yarn specific properties that can be set. We're not, this isn't really a place to get into the depths of Yarn, but we do note that when we have Hadoop and Yarn, we can set the configuration that we want in order to utilize the Yarn resources effectively. And let me see. Oh, the deploy modes. So that's what we saw before. We saw the cluster node where the Spark driver is running inside the master application process, and the Yarn client is running outside it, and generally on the client machine. Spark on the Mesos architecture, it looks pretty much the same. You see this, the pattern is starting to emerge similarly here, is that the cluster is managed by the particular worker, slave, or representative of that cluster manager. So the executor part stays the same. The node manager is going to vary depending on the cluster manager we're using. And again, working through the same cluster manager. Zookeeper is still doing fault tolerance, the same architecture. So it's pretty much the same all the way across in terms of how the architecture is being used. That's really nice because we can migrate from platform to platform without really worrying too much about what's going to happen in the underlying architecture. So the Mesos does require that the Spark binary be on the worker nodes, and we again set some configuration variables. And the only difference here is that it's supporting a client mode only, so that may be a drawback to the use of Mesos. So Mesos runs in, lets Spark run in two modes, fine-grained. So each Spark task is a separate Mesos task. So we're referring back to task as being a single executable step within a stage from Spark that can be done without referencing any other partitions. So in the fine grain, the instances and the framework share this fine granularity. So the executors scale as they execute the task. So we've got a kind of a dynamic scale set working there. In the coarse grained, we've got one long running Spark task, and then we schedule mini tasks within it. So the problem is that now we're looking ahead and saving resources. So I can't actually tell you offhand which one of them is going to give you better performance. I think that's going to come down to a use case issue. And if anybody wants to pursue that, we can delve into that a little bit further and do a bit of research on that. So how do you choose which one to use? All of these different modes all work similarly. They all have slight variations. Which is the one to go for if we're talking about tuning and optimizing? So what we want to do is do fast data access. We're again looking at optimization of kind of parallelization of data nodes, HDFS with any of the node managers gives fast data access. If we're doing deployment standalone in development, again, we don't need the overhead. If you're already running on Hadoop, Yarn, if you want fine-grained resource allocation, Mesos. The idea here is that what Mesos is actually doing is giving you the ability to scale up and scale down, which the other ones don't do. They work at a more level. So like I said, what is that decision point or cost point that you want to make where you want to go fine grain? And I honestly couldn't tell you, but I think we can find that out if we want to take a look around. I'm not going to go too much with this, even though we're actually using it in the labs, simply because I don't think you guys are running in stuff in the cloud, are you? You guys doing anything in the cloud?
We have Dataproc architecture, so we have several clusters running. Spark jobs. Most of them are long-running jobs, which means that they are never or rarely terminated, except when we update the service code, the core. Okay. Otherwise, they run forever, and they are basically using Kafka as like a notification provider, so they know what to process and when, and they orchestrate their work based on the Kafka orchestration itself. So we don't have to. Does that give you a little bit of answer to this question?
Yeah, I just wasn't sure if you were even using up there. So basically you're taking Kafka to bring a lot of streaming events in and you're processing these things on a continuous basis.
Yeah, let's say it's more or less this. So yeah, basically upstream Kafka is propagating some notifications when a certain kind of events arrive, and these events holding conditions for the processing to start. So whenever we have the required conditions, then you can process file A or B or report A or B or C, whatever. Okay. And basically it goes all along, and there is several components doing several different transformations on different level of aggregation, and not all the transformations are the same. So it really depends on what the stakeholders require.
Okay. All right. So it sounds to me like what you're doing is that you're assembling data up until it reaches a certain point to say you've got enough data for this particular threshold to be reached. So now we go ahead and we process into the rest of the system. Is that right?
Yes.
So you're kind of keeping in a data accumulator somewhere, and when that data accumulator reaches reaches some kind of, I'm full, whatever that means in terms of whatever threshold, then it gets processed through. And the route it takes to get processing goes through different transformations depending on which end stakeholder the data it wants out of that data.
Pardon? Sorry, can you repeat, please?
I said, and then once you're processing the data, my understanding of what you said was that it gets transformed along different possible routes depending on what the end result is wanted by the various stakeholders. Each route.
Yeah, well, basically, yeah. So we apply some transformations up to a certain point for some of the data that does not need, for example, to appear on the data warehouse, but that just for some external processing or other third-party services. And we also have data that is ending in our data warehouse in the cloud, which is something that is built on top of Hive. And also we can use Presto to query those tables. And for these data, basically what we do is we receive CSV or JSON. We first do some cleansing, then we apply some slight aggregation on top of it, and then we transform this into a view or tables, depending on how big the data is. And then we add some historization, like timestamp, stuff like that. So we can basically sort out the data with queries in a much more efficient way than just having the raw data. And then this ends up, as I said, in a data lake, data warehouse, where you can query tables with Hive or with Presto. And again, along those transformations, some of the data are only queryable on the final form. Some data is queryable in the intermediate state, even though it's not usually meant to be that way, but we can provide for some data, some like intermediate view. I don't know if it's really kind of correct to say this, but some people like just require very early on version of data, so we provide them some entry points in our pipeline on the early component.
Okay. Mainly this early entry point is meant to be a queryable format of the rawest possible data.
Okay, yeah, exactly.
Different formats, and we try to make it easily queryable by getting on a common level, normalizing column names and data types, including data types, and then they can basically already do aggregations on the rawest possible format of the data. Okay. And then the further transformations kick in that are transferring data into something that looks like our current data warehouse, because of course we are migrating from an existing warehouse to this solution. So we also have to fit in this historical data at some point and mix in the data from the new pipeline and have both available in a data lake-based data warehouse.
Okay, it sounds to me like that early query point is that a place where people would do things like data profiling and that sort of thing, just to get sort of big pictures of patterns of data, like just doing some data profiling.
Well, the idea was that they can, from time to time, special departments could look into do some analysis on old data. So it was not meant for regular access. Regular access, the data warehouse data should be used, and that should fulfill all the 98% of the needs. But since we are still building it, right now everybody wants to access whatever is available.
Yeah, everybody. That's always the way, you know. Yeah, that in fact, that's one of the big questions I always hear with data warehouses. Well, can we just like access the data before it goes into the data warehouse? Then we have to explain the whole point of this exercise. Okay. All right. Okay. Well, thank you very much. That's very illuminating. It gives me a nice kind of mental picture of sort of what's going on. We'll just, I think we're almost just done this section anyway, just got a couple of pages. And then I have to do one really fast run through of one section, and then we're going to jump over to Catalyst. Because I really want to look forward to getting into a good deep dive into Catalyst. Okay, so launching Spark and EC2. And the model they're taking here is that this is a nice, just like we're doing in the labs, nice convenient way to kind of do throwaways. There's a number, and of course, Spark is managed nicely by the infrastructure platform. So you can start Spark scripts with, of course, your keys and launch a particular cluster. And you have Cassandra is can be used here very effectively. You get an emulation of the actual physical environment in the cloud. You have your Spark master or the Spark driver creates a Spark master, which is then creates a connection to the Cassandra, and it all works quite nicely together in the same architectural pattern that we saw before. So the idea here is that, again, similar, I guess, what you're doing is that the streaming data goes into Spark, it's saved in Cassandra. Cassandra also allows lookups, and then you can also access through the Cassandra data through various kinds of dashboard operations. Okay, so the idea here is that it enables something like the streaming Lambda architecture. There's a Kafka cluster that you guys are mentioned, goes into Spark streaming, and then goes into the gets routed into the appropriate data sets. HDFS generally referring to that kind of batch data up to that point. NoSQL being used to store the immediate streaming data. And then the standard batch queries into a data warehouse being executed on here, with the real-time queries on the real-time data being executed on there. So that's that Lambda architecture that we looked at earlier, where you want to be able to query the real-time data in the same sense that you're, but also want to be able to query the existing archive data as well. Okay, so. This finally gives us a chance to do something. So we'll take just a kind of a conceptual break, so you don't have to listen to me talking right now. We'll kind of close off this section with doing a lab. So you guys want to jump in and do this lab? As feel like getting your fingers dirty, doing a distributed Spark cluster on a standalone manager. Shall we give it a try?
Yes.
Okay, good. They say 20 minutes. I'll check with you guys. Yeah, I suspect you guys will do it much shorter time than that. So we'll take 15 minutes, and if you finish up earlier, give me a shout, okay? And then we'll do one more section, and then we'll jump into Catalyst.
I have a question. Okay.
Yes.
So is one Amazon EC2 instance is enough for this lab, or do we need more than one?
I think you should need just one, because I believe that. Why are you having problems with that?
Well, I'm checking the source of this script copy files. And apparently there we are logging into these machines and copying some Spark binaries for some stuff there.
Yeah, just ignore that. So the idea is that you have multiple machines, but you can just say, okay, all three are localhost. And you can just we'll just spin up multiple.
Oh, I see what you were asking. Yeah, no, yeah. You remember you have that you can use that local option with the number of cores.
Yeah, I guess so.
Yeah.
So we don't have to run the script then?
No, don't run it. So like the idea of the exercise.
Yeah, okay, thanks.
I just went through it. So the idea of the exercise is that you have multiple machines running your worker processes, right? But what you can do is just tell Spark, hey, in its configuration, hey, my slave 1 is localhost, my slave 2 is localhost. You can do that up to, I don't know, slave 42, doesn't matter. And when you say start all, that startup script, it'll just start up as many worker processes as you say you want slaves. And you can just imagine that those are machines that you copied that configuration into. Make sense?
Then I think it also maybe a bit incorrect in the lab description, because it states there that in file named slaves, you specify first master, then slave 1 and slave 2. So I have specified one IP address 3 times there, and it booted up 3 workers. So.
Well, the instructions also start with step 1. Instructor will provide additional nodes for setup. So it is meant to be on separate machines. If they take step 1.
Yeah.
It's the same though. So it is
but
meant to be
it's not necessary for the exercise, to be honest.
Yeah, part of the problem you'll notice with the lab numbering is that it appears that this material was assembled from a number of different, is kind of in a number of different courses. So I went through as much of it I could when I finally got it, but I still wasn't able to get a lot of the material until a little while ago. So that I looked through a lot of it, but there are a few places I didn't get to. So.
Yeah, so the challenge was, let's say, to understand what the hell is there and how to make it work.
Yeah, basically.
Okay, thanks.
The part of the issue that we run into a lot with this kind of thing is, some people are kind of surprised to find out the Spark's not running fast, and then they go and they look at their profile and discovery they've got a node they've got a cluster of 6 machines and only 1 machine is running because of a configuration kind of error. So this is one of those things you always worry about having to check to make sure that you're actually utilizing your resources that are actually there. So, thinking configuration. All right, well, are you guys pretty much done with that then? I'm getting the sense based on the question that you are.
We could move on to the next topic.
I think that would be an excellent idea. I'm also kind of constrained by the idea here that I have to ensure that I can tell Nick that we actually did cover all of the material. So what I'm going to do is instead of just going back through slides, what I am going to do, whoops, where am I going here? Hold on. Just give me a moment. I'm just going to all data frame, Spark API production, performance tuning. What we're supposed to look at now is the AI primer, and this is going to take just so I can check off the list. This is actually the part that I really enjoy, but I know it's not of high interest to you guys. So we're just going to step through this fairly quickly. And just in case there's something here that does resonate with you, because I can't assume that nothing in here is going to be of interest to you. But I am going to go at a fairly fast clip, because after this, I want to start talking about Catalyst and optimizations in general. But I want to kind of get this out of the way. Let me see, make sure I'm unmuted. Okay, so does anybody here actually have done any background in AI and machine learning? I should ask that first.
A long time ago.
Long time ago?
I don't think so in Berlin.
No, in Berlin, no.
Manu,
Pardon?
maybe?
Okay. Well, what we'll do is we'll do a terminology overview because it might be useful and at some point, as particularly as we go and look at some of the other things. So we're not going to go deep into it. We'll just do an overview. This is actually one of my areas of specialization. So it's one of the reasons why I like things like Spark, because we can do stuff like this. Okay, so this is AI is generally a number of different topics. One area of specialization is machine learning. Machine learning is fundamentally advanced data analytics, in which you're using in which you're using various kinds of algorithms to tune your data models to reduce the amount of error in the data models. There's a lot of application here to machine learning, and in fact, one of the more interesting applications is applying machine learning to learn about machine learning, which is really kind of interesting. But the idea here is that whereas we're normally doing kind of manual data fitting in traditional data analytics, we're actually trying to find best models to fit data using various kinds of iterative and repetitive algorithms. And the idea is that we generally have a measure. If we've got some, we take a look at some kind of sets of data, and then we define some sort of task that we want to accomplish, and then we look at some probability or success measure, which to say is how well did our results actually match previous experience. Just as a little note. There is a significant scandal brewing right now that just broke. I think it was yesterday, may have been yesterday morning. I think it's yesterday morning. the gentleman who invented Ruby on Rails applied for an Apple credit card with his wife. They believe they live in California, and they have what's called a community asset law, which means that in assessing their credit ratings, their assets are considered together. She got a credit limit that was 1/20th of his. They asked Apple, and they said, well, you know, that's just the algorithm that we're using. He said, yeah, but she makes more than I do, and she has a better credit rating, and she's a citizen and I'm an immigrant, so why do I have a higher credit score? And nobody could give an answer. So we have some interesting things brewing around machine learning. Just point that out. So what we want to do is to get optimal performance. We choose a model that gives optimal performance over the data. Is essentially what machine learning is in a nutshell. There's a variety of kinds of models that we use to fit. The classic example is predicting house prices based on various parameters. There's this AI history. So I got involved in AI in the 1980s. AI got oversold. Simply, we just didn't have the computing power to run in efficient computations. So we're basically doing the same thing now we did in the 80s, but now we've got machines that are powerful enough to actually do it, actually to be able to change big data and stuff like that. So it's basically kind of the same thing. We get some nice scaling as we go up here into the 2000s, where we get more computing capabilities and that sort of thing. So we're not going to get too much into that. Machine learning's everywhere. This is standard kind of sales pitch for for machine learning. You know, it's your recommendation systems on Amazon. It's your credit card fraud systems for American Express and all that sort of thing. The machine learning is a subset of artificial intelligence, which also includes like things like semantic based knowledge bases and human machine interfaces and things like that. And within machine learning, there's a subset called deep learning, which involves using neural networks to do very, very complex multi-stage modeling. Vision, facial recognition is an example of a deep learning application. By basically breaking something down into component patterns, and then identifying the organization of the component patterns, and it can be used to do voice analysis, text analysis, and image analysis. Again, we were using it in the 1980s. We just didn't have the computer power to do it. To do something that runs now for a deep learning algorithm in a couple of seconds used to take us overnight to run in the 1980s, given our computing power. So it was obviously not that effective. So deep learning again has multiple layers, sorts out the raw data into features, and then identifies based on feature analysis what it's actually what actually the raw data is. It's looking for patterns in the raw data, and then it breaks it down into a series of parallel tasks, and then uses the input from each task to do another set of parallel tasks, and then eventually comes up with a conclusion. So we have various kinds of machine learning levels where and again, we don't want to get too far into this, but again, there's different kind of sequences of steps we can take in machine learning, from basically designing the program by hand to doing really automated things like representation learning, which extracts features, models the features, and then uses those for development. The basic kinds of machine learning, there's supervised, where you have a bunch of data with the correct results, like fraud detection with correct results if something's fraud or not. And using that, the various kinds of regression models can be built up, or logistic models. Unsupervised learning is where you're looking for underlying patterns of clustering based on various kinds of distance metrics. In terms of, and you can define those metrics along a number of different kind of feature parameters. So we might cluster people together based on family resemblance. Nobody's wearing a sign that says what family necessarily they belong to, but we can tell that there's enough common features that we can probably group people together into family groups. Both of those have different kinds of algorithms they use. And we have the semi-supervised learning, which it really isn't that much of a thing now, but instead we have more of what we call reinforcement learning, where you give feedback as to how well a decision is being made. It's usually to do scheduling and solving searching problems and other kinds of things. The supervised learning predicts from training data, and like I said, you give it a bunch of inputs with what should be the correct output, and then it basically tunes models to ensure that it produces the correct output given input. And typically the way we do it is we split the training data into two parts. One is the training data we use to build the model, and then we run it against the other half, which is the test data, to see how well the model works. So there's a couple of different models, algorithms we use. One is the standard multivariate or linear regressions, or some other kind of high order regression, which we're basically fitting a curve to data. And that's where we're using some kind of continuous data that we're measuring on. Classification is where we have some kind of discrete, often a yes or no sort of answer, or we're binning data into some kinds of bins based on some prior labeling. So we should be able to make predictions about whether something is a fraud or not based on the model, the logistic model that we create. So there's an example here of supervised learning for given house data, can we predict the price? Given the person's face, can we predict the age? Like I said, we've got two kinds of supervised learning: the regression and the classification. Other examples that we can find for classifications are listed here. OCR, credit card transactions, cell cancers or not, whether email is spam or not. These are all sort of classic machine learning problems. The other thing that we can actually use are decision trees, where we sort of are able to make decisions based on various input data as to what the best outcome is. And by breaking things down to do a series of decisions and measuring something that we call a reduction of entropy. So we kind of group our decisions together so that we wind up given a set of inputs, we make the best possible decision. So decision tree is another kind of example. And it's basically a partitioning exercise. Like I said, we split the data into training and testing sets. This is useful when we actually have training data to work with. So this is basically the idea behind machine learning methodologies, and there are variations on these. Support vector machines. You'll hear these terms thrown around in random forests, but basically they're fitting decision-making models based on looking at how decisions were made statistically on past data and what the outcomes of those decisions should have been. So that's basically what machine learning types are. Supervised is. Unsupervised learning is where you're basically looking, like I said, for groups, cluster analysis. It's where you decide that some feature has got some weight and looking for commonality. So for example, if we decide to group people by nationality in Europe, one of the things that we might decide is a common feature is the language they grew up speaking. And that is probably not too bad. But of course, it's not going to be a really great measure. So we might, combine that with a metric of where they were born, plus the language they're speaking and where they're currently living now is 3 metrics. And those 3 metrics might be enough to kind of cluster people into rough national groupings so we could predict maybe, for example, what immigration laws might apply to them if they're visiting another country. It'd probably be easier just to ask them for their passport, but it's just an example off the top of my head. We also look for anomaly detection, where we notice that things that all tend to work together tend to share certain characteristics. So if something is deviant and outside that nice kind of cluster of characteristics, it's probably defective in some way. Okay, so we do a number of algorithms with that. K-means is a very common one, where we just basically kind of sort data and look for cluster points that reduce the amount of distance from every point to its center of mass. And hidden Markov model is another one looking at state transitions. So basically the idea is this is really a pattern searching routine. A lot of it uses the algorithms that were refined for many years in data mining, going through the data mining process. Example of Google News goes and use various kind of clustering algorithms to sort news stories into various groups. So clustering is, again, grouping. The question is, how do we cluster? We cluster based on some criteria that we set up here. Obviously, there are 2 metrics we're using here: is distance between points and also color. Or if we didn't have color, we could use distance between 2 points as a natural form of clustering. Or even if we interspersed all of these, we could even cluster them based on color. It depends on what we actually choose to cluster around. And the applications that we have there are in things like biology. You have all these different haploid groups that now can be used to track the movement of human populations historically by clustering their genomes. Medicine actually used very nicely for analysis of diagnostic medical imagery. Marketing. Creating, this is what I spent a number of years doing, is doing consumer groupings for various kinds of industries. Web grouping, various kinds of content grouping, image analysis, climatology. That's still a very, very nasty problem to work on. So there's a variety of environments, programming environments that are used for AI. And there are a variety of packages which are usable in these various environments for machine learning and deep learning, which is the modern equivalent of neural nets. Generally, as we look into this, Spark is getting a lot of popularity because it's sitting in here as one of the components of the machine learning paradigm in a distributed big data environment. So that's because of that use case, Spark has really gotten a lot of push in terms of popularity. Spark machine learning runs on top of the Spark platform, which is able to run the various machine learning protocols and tools on top of Spark to take advantage of being able to work with the big data available to it. Amazon Machine Learning, very similar to the Spark ML. So every cloud provider has its own machine learning library now. There's also various specialized libraries like TensorFlow from Google, which specialize in things like deep learning. So the field is exploding. Some of the complaints from people like me who've been in the field for a long time is a lot of people are downloading these toolkits and doing machine learning and not really understanding what it is that they're actually producing. Scalable machine learning, there's a couple of other tools available. Azure Machine Learning Studio, that's the Microsoft offering. H2O. also a machine learning toolkit that works on top of Spark as well. TensorFlow is the Google toolkit that has become very popular. BigDL is another learning library on top of Spark. I see Spark underlies a lot of these sort of toolkits. The amount of computation required has required increasingly large amounts of processing power. So we've graduated in a lot of the machine learning world from CPUs to graphics processing units, and increased our amount of performance. And then we've also gone to the tensor processing units and ASIC, which is the application-specific integrated circuit. So now we're specialized hardware. Ironically, when we first started off doing AI in the 1980s, we had to build specialized hardware like Lisp machines in order to do the work. So we're kind of come full circle again here. It's always this question for more processing. So a tensor processing unit, again, is more sophisticated hardware designed to increase the amount of processing capability. So high volume computings, and you can actually go up into the Google platform and scale up these machines at exorbitant costs. You can get these things available up in the Google Cloud. I not afford it, certainly on my account. Lovely picture of one of their TPUs. And we also have new chips. There is an announcement made by Google, which I'm not too sure how to take with a grain of salt or not, claiming that they have now produced a quantum chip in the early stages. If that's the case, that's a game changer. But I've learned not to trust marketing people too much in terms of these revolutionary announcements that they're making. So, but there is certainly attempts to now redefine chip architecture to take advantage of that. And we're not going to do the lab at this point. You guys can do it later if you want, because we're not doing machine learning on the course. So it's an interesting, but doing the machine learning use cases are interesting to do. So I'll leave that if you guys want to try that later on in the class or even after the class. You know, we can leave the machine up for a few hours. So you want to go and play on it, you can do that. But I think it's probably not something we want to get into that much. Okay. So any questions about that? That was kind of a very high level overview. There's actually a lot more to machine learning than this, but that just introduces some of the basic terminology. Any questions? I don't think there should be any. It's not really a big topic. Okay. All right. So that comes us down to Catalyst. And in order to do that, I am going to, let me see, hold on here. 9.1. So I'm going to actually look up a nice image here. Let's look at Catalyst optimizer. I just wanted to get a nice picture. I know we've got one in the notes as well, but I want to go back and see if we can get that picture. That's the picture I wanted to look at. So we'll grab this one here. And let's see if we can just, there we go. Okay, so how much are you guys familiar with Catalyst at this particular point? Like, what's your understanding of what's going on in Catalyst? Okay, can we just kind of get a general sense of where you're coming from in terms of Catalyst?
Where we can display the plan, but that's all we see. So in the end, we can have a look at the plan, and that's what we in the end see from Catalyst. But we don't really know how to effectively tune Catalyst, except for applying, of course, the performance improvements you just showed us in the previous slide.
Okay, well, and hopefully this will be a fairly useful part of the course. So I'll kind of go over what each step is, and we'll go into a little bit of detail over what's happening at each step. And I'll be taking some notes because I'll be introducing terms, and I will kind of write them all down as I go through. And I've kind of assembled this over a period of time, just from kind of my own investigation into what's going on in the wonderful world of Catalyst, because I think personally this is a really fascinating a project. Okay, so this is the step we saw before. So let's actually figure out what's going on at each step. So again, we have to start with SQL data. This only works on SQL data, which got some kind of structured schema to it. Otherwise, these optimizations can't work. So the idea behind the unresolved logical plan is this is the raw representation of your data. And I'm going to look for another picture here if I can find it. There we go. There we go. This should be a good enough picture here. Oh, I recognize this. This is from one of the presentations. And let's open the image in a new tab. Okay. All right. So when it gets this, I have to be careful here because there's little, that's optimization. Hold on here. I just opened it here. There it is. Okay, so when you get a query coming in, and this would make me I should probably go and see if we can also find a query to do this. But what it does is we'll initially start just some definitions here. It starts with a tree, which represents the sequence of actions it's going to take. In this particular thing, this query is going to read in two tables, table 1 and table 2, is going to join them based on some kind of join, and where table T1 ID equals table T2 ID, table T2 ID on both the tables is the same, and the ID on table 2 is greater than 50,000, and then it's going to basically show column V out of that table. And this is called the this just written in this form here is called the unresolved plan. It's just a layout of the query as you've written it. Now, when it looks at this now, in order to start the optimization, it has to go and get some information about things like table size and get some data about it, which it goes and it gets from the catalog that describes the table. So now it's got a sense of how big the table is, what the table size is, how many columns, what the values are on the columns, what the data types are. And so it resolves this plan. And then it starts to look for various optimizations. So so a couple of the optimizations that it winds up working on, and this would be an example of it, is that it first of all recognizes the fact that the final result is only going to produce the a result displaying column V. That's the only column you're interested in. So there's an optimization that's suggested there is why am I reading in the entire table when I'm just going to throw away most of it and only keep column V at the end. So it says the only columns that are actually necessary for me to read into this set of operations is the key values, and also column B. So what it does is it takes this project and now pushes it down before the join, which is going to be the costly operation. So now what we're doing at this level is we're taking scanning the table in, but we're not keeping all the data. We're only keeping the value column here. So only keeping the T1 value column. We're not keeping any data from T2 here. So the only thing we really need to do is report T2 ID. All right, so now we've significantly improved performance by not reading in a bunch of data that's not going to make any difference. The other thing we'll notice here is that in the original table, we did the join and then we threw away data for all of the T2s that were less than 50,000. So before we do the join, we're going to throw all of those rows away anyway. So now let's just we'll just basically only proceed to the join with the rows that where it's actually 50,000. So we're doing that filter earlier. So what we've actually done here is identified where redundant data has been moving through the system and where we're going to be joining data and then just throwing it away. So now what we've done is we've created a much smaller join, and we're moving much less data through that join. So now we've probably, depending on the size of the original data, what we've actually done is we've really reduced the amount of data that can take, or the amount of operation and data storage required in order to do this. Okay, and then when we finally get to the final projection, which is going to have an operation on it, we've done that particular operation as well. So let's go back actually and see if we can come to that. Okay, that's an actual presentation. Let's see if we can just go from the slides here. So we might be able to take a look at what some of these slides are. Okay, so this is let me see. Okay, I want to see if we can get the, okay, so there is our what we're looking at is the query plan. And what we want to do is get to that optimized query plan we looked at. And that's done through a series of transformations. Let's see. So this was actually the query that we're looking at, the optimizing, which is the select. I'll put a link to this if you guys want. So there we go. So we're going to select some V from, and this breaks it down into a series of operations and predicates that it can analyze. Where it takes a look here, and there's a couple of things it can look at. Let's see if we can look at another page here. So these are the abstractions of the user's expressions, and so they're going to be looking at new values which are computed and attributes. So we'll notice there that under the select you have a 1 plus 2, and then you're going to add those to T1 plus value. Now, before I go too far into that, I'll make a note here. Okay, so for Catalyst, okay, what we're looking at are and I'll make this note here, but it's what we call the expressions. So we have the user expressions. Just make a note here. Okay, so we've got that notion of the user expression, where the user is referring to some operation or some kind of computation or some kind of reference to the underlying data. Okay, so that is the first thing it looks at, and then the next thing it looks at is the abstraction of the user's program, which is where the structure is built up by the actual operations. So there's a where, a join, a select, and a select. And that maps onto that tree that we just looked at. So this first initial unresolved tree here is just this direct mapping of the query structure onto a tree. So so we'll make the note here is that user expressions, computations, and we'll call them data references. And whoops, sorry, and the tree. I want to make sure you get the right terminology. The tree is a representation of the structure of the user operations. The query. Okay, so there's our user operations. Okay, so this is where that first tree of operations is coming from. Now, the logical plan is where we're just looking at this structure without any reference to really the underlying actual data. Okay, so and this is why it's called a logical plan, because we're not looking at how much data there is, how many rows of data. We're not looking at the amounts of data. We're just looking at the structure or the schema of the data and the tree that's generated by the users defined operations. So we wind up looking for a couple of things, like what are the outputs that we're expecting to get out of here, which we can then backtrack to say, okay, well, if we're getting this output, why do we need these inputs here? Notice you can do that on the basis of just analyzing the schema. So I know if I'm going to do a projection, I don't need to know how much data is in the table. All I need to know is how many columns there are. So at this point, in order to be able to figure out what this actually means, is where I go and I resolve this logical plan by looking at the schema to understand where this fits in terms of the larger context. I also look at the various invariants which constrain it. So there's an example of an invariant here, which is basically going to be a filter. And I look in if I got some statistics available, I can look at that. We'll talk about statistics a little bit more when we get into the notion of cost, looking at cost plans, how we cost out a plan, and how using table statistics helps us to develop that. So the idea here is that now we can also look at a number of places where we can make this modification. Now, there are several kinds of mappings that we can use, and there's two kinds of trees, by the way. There is a logical tree, which is what we're looking at right now, and a physical tree, which is going to be associated with various kinds of strategies on how we're actually going to implement the logical tree. So there are two kinds of transformations that are actually used by Catalyst. One is a logical tree that maps to a logical tree. So we're basically reorganizing the tree. Another one is a mapping of an expression to another expression. We're rewriting an expression to make that expression work more effectively. And the other thing we're looking at is we're going to do a mapping from a logical tree to a final physical tree, which will then be used to generate the executable code that will actually execute the query. Okay, so we've got these three notions of a transformation. Okay, so now, what we can do is look at the physical plan And we'll talk. So the physical plan is going to do things like, okay, so we're going to do a join here. And if we have enough data, can we figure out what is the most effective join to actually use? Can we use some kind of merge sort join? Should we use some kind of a hash join? Should we use a broadcast join? What kinds of joins should we use? Now, that's where we're going to actually start using the actual physical characteristics of the data to start to compute the costs of those various kinds of physical strategies. And once we've made that strategy, that's where our logical plan becomes a physical plan, because now we have an actual strategy to implement the original request. Okay, so let's go ahead a little bit further. And so that's what we're actually looking here in terms of the transformations. Oh, there it is. They've got it there too. Physical plan to physical plan. And we have this tree here. I forgot if there was actually that kind of thing as well. And so a transformation that moves a tree to a tree. So what we're looking at here is we take a look at this operation, 1 + 2 plus a value. That's going to be executed for every row. So we can use some kind of evaluation folding here to say, well, let's compute it once and then just get rid of that. So we can, we've got an add steps. We've got literal 1, literal 2, we add it, and we add it to literal 3. Well, these are both literal, so let's just add them once at the beginning and reduce that step here. So depending on how many millions of rows we might have, we've just saved a lot of computation. So this is an expression to expression transform, as we're transforming one expression into a more efficient expression that can actually be used that way. So this is an example of an expression transform. A tree transformation. So so these transformations are what we call partial functions. What a partial function is, that if it's defined on a domain, but it is idempotent for part of that domain. So in other words, it doesn't do anything for a certain subset of the domain. So no matter how many times you apply it to that idempotent subset, it just never changes. And that's one of the things we'll use to figure out that we've optimized that transformation, is because if we continue to apply that transformation, it just doesn't change what we're applying it to. So that's called a fixed point, where the transformation itself no longer can improve what we've got. And so we can iterate this. Now, how this actually is, I don't know if it says it in here. So how this actually works is that this transformation is applied recursively to the tree. So in other words, we take these transformations, we identify which transformations might apply, and then we recursively walk the tree, combining the transformations at each subtree until we reach a fixed point, and then we move up and we continue to do this to reach a fixed point. Now we're guaranteed that these things are going to terminate, because they are partial. They are partial transformations. And one of the things I was concerned about was, can we get involved in some kind of cyclic graph here? But apparently, the way this is designed is that you can't get involved in some kind of cyclic loop. This tends to be very acyclic. So eventually, we're going to reach some kind of termination condition in a finite number of steps, or not a finite number of steps, is not going to, or a very small number of steps is going to terminate. So when we've applied this recursively and the tree can no longer be reduced, we wind up with an application of that transform, and then we look at other transforms that are going to be applied. Now, I know that there is a specific way that transformations are applied, and there's an algorithm, but I have no idea what it actually is. So for example, here, there's multiple rules can be applied. where there's now so the ones we just thought was an expression. This is a tree-to-tree mapping, very famous predicate pushdown, where we're basically taking a filter and pushing it down closer to the data. That was an optimization that's been around. We saw that early in the RDDs. So the idea behind this one, hold on here for a second. I got my microphone tangled up. Okay, so so again, we would now, having applied, for example, perhaps our constant folding, or expression folding, or literal folding, whatever you want to call it, we can now look at applying a predicate pushdown rule. Now, these are all what we call heuristics. In the sense that they are logically make sense that you're going to optimize it, but they are not empirical in the sense that we can't tell you at this point how much better it's going to make the operation. So we're just using a strictly heuristic here. Now, a lot of these heuristics are well known. These heuristics are inspired by both experience from optimizing standard SQL queries in the SQL world, and also from some experimental work that was done in a variety of environments about the query optimization specifically. So this is trying to implement a lot of the best practices and experiences that we already have from this. And so what happens is we have another rule here, which we mentioned before, column pruning, another heuristic where we're pruning out all the columns we're not using in order to introduce the amount of data flowing through the tree, I guess is a good expression. So again, we're putting filters in various places. So we're column pruning down here. We're filtering. We're expression folding, and these are a couple of very simple sort of rules that when you look at it, it makes sense, and that these are obviously the kinds of rules that you would want to do. So when we combine all of these rules together, we apply them in batches, we apply them recursively, and the question that remains in my mind that I cannot answer because I'm still trying to figure it out is if that process of batching and how they're applied is optimized some way, and I'm sure it is, but I can't find any maybe I haven't looked deep enough documentation on what exactly that optimization process is. All I seem to be able to find is an assurance that yes, there is one, and it is always in a continuous state of improvement. Okay, so this combining multiple rules to heuristics was pretty much the way of the world until Spark 2.2. This was one of the big, oh, there it is, batching. So this is the question here, is that I don't know how the rule executor combines the rules into batches, but it does. And then it applies each batch recursively to the tree, the batches of rules, until it reaches that fixed point if it wants high optimization, or sometimes it can just be applied once. And again, there's a criteria there, and I'm not sure exactly what you want to do that, but obviously if you're reaching a fixed point, you just can't optimize that batch of rules anymore. And I'm wondering about the ordering of the batches. I'm sure that's taken into account. So to me, it seems that they probably would look at rules that are sort of dependent on each other and apply those batches continuously, because they may affect each other. So again, I'm not exactly sure how that decision process happens, but I would really love to. And so the transformations are fundamentally these ideas of changing, rewriting expressions so that they're more efficient, taking a logical plan and then applying various kinds of heuristic transformations after analyzing the tree, finding the transformation that would apply, batching them up, and then applying them recursively to the entire tree. So for example, if we go back to our original tree here, we would initially start applying the rules recursively here, and then recursively to this part of the tree, recursively to this part of the tree. So we would basically walk the tree. So we're really trying to get local optimization, and then as we get local optimization, we try to get a higher level of local optimization, and then a higher level of local optimization. And so there is an actual methodology here to trying to walk the tree to apply the operations to that. So obviously, this process will be made a lot easier if we have a well-structured query. And I think generally by a well-structured query, we mean a query that would follow standard SQL query types of practices and best practices, since this is more, since a lot of the optimization rules are inspired by those optimization rules in the SQL world. Okay, so this part continues on until we basically cannot proceed any further. So at that point, I'll say, is there any questions about that part of it so far? Anybody have any questions? Does it make sense? All right. Okay. So now we get to the point of saying, well, so how do we actually implement this optimal logical plan? And so what we wind up doing is applying a set of transformations to take the steps of the logical plan and map it to actual executable operations through a strategy. So each logical plan can actually produce multiple physical plans, which represent the multiple strategies that are actually available in order to implement that. So one of the plans here is to basically go through again recursively and look at all of the different strategies that could implement that particular plan. So if we're doing a join, there's multiple join strategies we could use. So we could basically do an estimate on how much work would be required for each one of these strategies. This is a bit of a blind spot for the original Catalyst, because this is the place where some of the estimates can really get really out of whack, because based on the amount of data coming in and the structure of the data, certain assumptions have to be made if you don't know that. It's a little bit difficult. So for example, if you're doing joining multiple tables, the question is what's going to happen to the effectiveness if you join them in different orders, or if you have a 3-table join, what if you join them in different sequences? How's that going to affect it? The logical plans cannot really give you a good answer to that, because a lot of it's going to depend on the size of the intermediate results that you get from these various operations. So at this particular, so you have to kind of make some generalization assumptions that, well, we're going to have to assume that maybe all of the intermediate steps are going to be fairly equivalent, and they may not be in fact wrong. And that may in fact suggest that the strategy is, oops, that may not be a good strategy. When in fact it's a good strategy when, but you may get a really massive intermediate result if you, say you've got tables A, B, and C and you join them together. And if you join A and B, you might get a massive intermediate result. Then you join it with C and you get a very, very expensive query. But if you joined B and C together from the right, you might have got a very relatively small intermediate result, which would reduce the amount of computation. Well, it's impossible to actually predict this at this particular point, but you can make some general estimates if you assume certain information. Okay, so let's see what else we've got here. Okay, so what we have to do at this point is we have to now at this point we've got the unresolved logical plan. We've got information about the structure, so now we can do that to actually have the logical plan with information about what the components of the plan refer to, the expressions, what the columns are, how many columns the table is, how big the table is, and then we can apply our transformations both on the expressions and the logical plan until we've optimized it based on all the heuristics. And then we start to look at, for all of the steps in the optimized logical plan, what are the possible physical implementations or physical strategies that we can actually implement for each step. And that gives us a series of physical plans. The costing model was a little bit blind here because it had to make a lot of assumptions about the data based on sort of general understanding of how data is often expected to be distributed, and it would produce a selected physical plan. So it's this cost model that tends to be the choking point. So what happened is, and I don't know if it's in this presentation, but we'll, okay, so there's some stuff here. It says analysis transforms unresolved logical plan. We just saw that. Logical optimization, rule executor, transit to an optimized logical plan. Now, the one question in my mind, and I don't have an answer to this one, I'm still trying to figure this one out, is that rule executor is, for me, the big question mark, because while I'm having faith that the rule executor works in an optimal manner, one of the questions that I want to know is that if we apply those batches of rules in different orders, are we deterministically going to wind up with similar optimal plans, or are we going to wind up with different optimal plans, and then how do we decide between them? And to that, I'm afraid I do not have an answer. But at this particular point, I'm just going to defer to the expertise of the people who put this together and say I'm assumed that they have dealt with that question at some point, and if they're and they probably have some heuristic for choosing which, based on structure perhaps, which is the optimal order in which to apply the batches of rules. Because it seems to me that there is some kind of a state change that will take place that might be effective. So there's some decision making mechanism there, which I'm sure that the people who built it know about, but haven't really shared with anybody, or we haven't delved deep enough into the documents. So the logical optimization, and then we go to physical planning, strategies, and rule executor. Which is going to turn it into the physical plan, and then the rule executor then adjusts the physical plan to make it ready for execution by preparing the actual code needed to execute it. Now, there's still a piece here kind of missing, and then we can also do some, oh, this is interesting. Yeah, so you can also use the Catalyst API to put your own planner rules in place. So here's a planner rule, and I actually haven't, I'm not sure what we're going here. There we go. So let's take a look at this, and I want to get into that, looking at that cost model portion in a moment too. So here we'll take a look at this example. So table A is a data set of integers in the range of 1 to big number, and table B is a data set in the range of 1 to another big number. And we want to show the records after the join. And so there's our join on there, group by and count. and show the result. And they're saying that takes 4 to 8 seconds. And what we, now when you explain the planner rule here, it goes and explains the rule that's being used, and it's using a sort merge join here as its choice. And let me see, range steps, it will try to give you an estimate here, and I'm not exactly sure what it's saying there, but let's we'll come back and look at this in a little bit more detail. So it's showing us where the rule is taking place. And but we know from the structure of our data that again, knowing your data, actually, I'll explain this, and then I think what we'll do after the break is explain why this is actually maybe not necessary anymore, but at least to understand how this works. So we understand that based on the data, we're joining 2 intervals. The result is the intersection of the interval. Okay, so now what we can do is come down here and write a planner rule, which basically is going to be applied to when we're trying to join ranges. And so we've got 2 ranges, and we're going to join them. We're going to have some kind of inner join using an equivalence on the field. So there's semantics that are there. And so we're able to actually write a rule that is going to be used to optimize the join on ranges. So in this particular case, now we've got this rule that's going to be applied into the API. And so there's our planner rule. So we can match cases like, and there's, when we've got this overlap here, start 1, end 1, and end 2, and then the planner rule basically rewrites that join as fundamentally an intersection. So what we're doing is we're avoiding the expense of a join by short-circuiting a join of 2 ranges to do that. And that's because we have knowledge of the underlying data structure, and we're actually going to be able to use it. Now, this is what we want to do, is compare this. Go back over here. So here is all of the steps treating that. So this is the physical plan said, okay, it's a join, I have to do a join. So here's my strategy on a join. So I'm going to go through all of these actual strategies. I'm going to do a sort merge join. I'm going to exchange hash partition. I'm going to sort, and I'm going to exchange. And so I've got a series of steps I'm going through. But I've been told, based on the structure of the data, I don't have to do that. In fact, I can go and replace that strategy with this custom strategy that works this way. Okay, does that make sense? Or any questions about that? All right. Okay, so that's sort of, well, I think we've killed that one up here. Okay, so when we come back from our break, I'm going to talk about the cost implementation, and that is a new implementation that actually, in many respects, make that kind of implementation of our own physical planning rule to be a little bit, or our own planning rule to be a little bit redundant. Okay. Any comments on that? Does that make sense to you guys? What did that help clarify a little bit about what's going on in Catalyst?
Yes.
Okay. Do you love Catalyst now?
I don't think love is the appropriate word. Coping, yeah, exactly. Coping with, I think it's a much better way to see things. But, yeah.
Okay. So So my point about Catalyst here is that it's really trying to build on sort of what we understand about optimizations of various kinds of queries in SQL. So it's developing these rules which are replacing a lot of the kind of rules of thumb we were looking before earlier, which is do your filters early. So based on if we're using a data set with or data frames structure, we use some kind of something where we have the ability to use SQL. We're able to automate that through the Catalyst process. However, as I said, there's still some blind spots that Catalyst has. We actually just saw one, which was that a particular join based on the nature of the data, and also we had blind spots in terms of not being able to predict intermediate results, which can cause the Catalyst to burp and produce a less than optimal results. All right. Well, anyway, it's 10 o'clock, so why don't we take a quick break, say about 15 minutes or so. And actually 10 o'clock here, I'm sorry, I'm looking at my clock. It's just 3 minutes after the hour. So let's take about a 15-minute break and then come back here and take a look at the other half of that diagram, which is the cost model, and which is the new innovation. Okay, so see you guys in 15.
Okay, I see you in 15.
Well, are we back, gentlemen?
I'm back, yes.
Okay, good.
Good about Kimberly as well.
Okay, good. Yes. All right. So now I'll go back, and just before we jump into the cost part, I've actually managed to dig up another set of slides we can kind of use to go through that as well. Are there any questions about any of the sort of topics on that first part? Because that's kind of been around for a while. So any questions about any of the optimizations there, or does anybody kind of familiar with that sort of optimization process in the past?
Yeah, so we have similar optimizers also in databases like in Postgres or in Oracle. And there are some optimizer settings that we can use, and mainly maybe on session level or on global level or even on statement level. I wonder whether something similar exists for Catalyst as well.
Okay, let me put that into the hopper and we'll take care of that tomorrow. Okay. All right, so that's actually a really good question. So,
so for example, Oracle has hints you can put into the queries itself.
Yes.
And they also have kind of settings on table level, and on Postgres it's less fine-grained. Yeah, so I wonder whether some kind of tuning exists for this Catalyst.
Yeah, I'm given the cost processing, that's a good point. And what I need to do is to check up I'll need to check up that. I'm sitting here teaching a class, and my 28-year-old daughter is sending me pictures of cheese for some reason. I'm going to have a talk with that woman. All right, just distracted me for a moment. Okay, yeah, it seems to me that you might hints, but on the other hand, when we take a look at what we're doing here, and the reason I'm hesitating on saying that, because given what's done in the cost section, which is from Apache 2.2, I've got to double check and to see what actually you can tune on that idea, and where those kind of hints may or may not be required. So again, we'll go back here. So let's go to, where am I going? I'm going over to here. Okay, I remember, so this introduces this innovation, because that ability to cost out a physical plan has, like I said, blind spots. So the idea here is that this approach is intended to produce optimal physical plans amongst competing physical plans. So I think we've got, this is query plan, minimized, so we've already looked at all this kinds of things. Okay, let's look at this point down here. So here are some of the problems with this. Is that because it doesn't know anything about the size of the data or the structure or the distribution of data values in each column, it doesn't really able to estimate what that operation is going to cost. And it's kind of blind to intermediate results and joins and to other sorts of operations where the final result is not necessarily an indicator of what the intermediate computations are going to be. There's kind of nothing you can do about join order except just kind of accept it as it is, and then kind of use heuristics to try to figure out, how to implement the join. But the problem is that those are still heuristics. What you want are some kind of empirical measurements to actually measure out a cost. So this is the standard data set where you've got a join on, let me see, customer store sales, customer and date. And so this is a multiple join. If you do the join here with 3 billion records and you filter out even 2 million and you join, you get 2.5 billion records here. But this one over here has only 100,000 records. And when you actually do the join here, you wind up with a $500 million record result. And the empirical cost of doing the join this way is the cost of actually processing this intermediate result and then using this and then feeding that into this result. So the question is, if you know these numbers of records, can you actually improve on that join? And so now if we join it the other way around, then we wind up with a $500 million records here, and that reduces the size of the intermediate join. But now when you do the join here, you've got really a smaller operation to take place. You still wind up with the same result, but in terms of an empirical cost, what you've got is a better approach to performing the join. And this cannot be resolved by heuristics. There's no way that you can look at the logic of the join and say anything about how that join is actually going to resolve. So in order to do this, we need to know something about data. So we want to optimize queries like that. So what we need to do is to be able to look at statistics or basically profile the data that's coming in. And so based on the data profiles, then make reasonable estimates that are empirical on what each one of the strategies we're proposing is actually going to cost in terms of computational power. And so this is what's called the cost-based optimizer. Now, the cost-based optimizer is applied after the logical plan has been optimized, after we've done all the heuristics. So now what we're really interested in is looking at maybe even rewriting part of that plan based on cost but also choosing the appropriate strategy to make things work. Okay, so the things that we want to build here are the kinds of data we need in order to do that. And then what really helps us in terms of our actual empirical estimation is to do cardinality estimates based on what we know about the statistics on the table. All right. So in other words, now we're going to get into doing some real measurements. Okay. So let me see what we've got here. So this is the command that is actually going to be used. This is and if we go to, I think I was going to actually start this one with a looking at this command originally, which was where is it here? No. Okay. Well, I thought I'd bookmarked it, but I guess I didn't. So we'll come back and get to that page. We don't need that anymore. We don't need that anymore. We don't need that. So we should be here. There we go. Okay. So now this is now a command that we actually execute after we load a table, which actually does a statistical analysis of the table. This is one of the points where if you have some kind of column column serializable or column ordering that you can use, this operation speeds up tremendously because you're really gathering statistics by column. So so it's a lot easier if you're using like a Parquet, which allows you to do that column-based organization. So this is the type of statistics that are collected. And we have the statistics collected for two basic types of data, and that's saved off in, as it says, into a metastore. So for numeric date time, basically numeric kinds of data, we're taking the max across that column, the minimum, the null count, and particularly notice here we're specifying which columns we're doing this on. We don't necessarily want to do it on all the columns, but we want to analyze some of the columns. The number of nulls that are in that column, the average length of that column, and the maximum length of that column as well, in terms of size. In the string and binary type, distinct counts, nulls, average length, maximum length. So now we have some numbers that we can use to profile the data to be able to optimize or not optimize, but to cost estimate some of the operations that are in place. So the cardinality expressions we're able to give at least so these kinds of expressions, which are operator expressions. You can do kind of an estimate as to what all of the combinations of that are going to be. So you get an idea of cardinality, and we'll take I think we'll take a look at that example in a moment. So the if we take a look at A is less than or equal to B as a value, so what we can do is we can take a look at things like min and max values to determine what would be this cardinality of that resulting expression. So we can do that expression, recompute some statistics that would be appropriate for the output of that result, and this would be the example of generally the kind of logic that would be used to compute the cost. So we're column A and then doing an operator in column B. We can see what kinds of changes need to take place. So here's the minimum of A here. Here's the maximum of column A. And if our operation is column A is less than column B, if the column B is all greater than column A, then filtering factor is 100%. So in other words, if column A is less than column B. I'm actually get this right. Yeah, so we're going to have 100% of column A because it's a lot less than column B. If B is less than A, then obviously we're going to a filtering factor of 0, and now we're going to have to change this because all of column A is greater than 0, so that winds up 0. So we're going to need to change statistics. Now, when it falls in the range, what it does is it assumes an equal distribution across the range here. So it gives an estimate, just kind of interpolation, which is the filtering factor, which does a kind of a scaling median. And we determine on the basis of this, how to compute the new result of that operation. So again, the idea here is that this is made possible through the use of the statistic we've got on the maximum column B or the minimum of column A and the maximum of column A. So now we can look at the results. So. So there's an example of where those statistics are able to get an estimate on the cardinality of the result of that operation. Okay, so the if you have there's some assumptions made here where you're making ideas about kind of the intersection where if column A is over column B, and the data is do some kind of empirical filtering. So we just kind of make an estimate here of the cases where you got selectivity, where you might have some overlap, and we're modifying the estimate to represent that overlap. So notice again that these are not accurate specific measures, but they're giving us of estimates, whereas before we did not have the ability to actually produce numbers and estimates. So when we look at the estimates for the cardinality of a join, there we go. We can work with now the statistics about the maximum number of distinct rows, the number of rows, and you can get an estimate for the number of rows that you're going to get as a result of an inner join by taking the Cartesian product and then factoring out the maximum of the two values of the distinct rows. So there is, again, some underlying assumptions to this, but you can get some cardinality estimates now for how big a particular join is going to be. So you can measure the possible cardinalities of doing the joins different ways, and also looking at those sequences of joins to see which joins will produce lower cardinalities or estimated cardinalities as a result of the output. So there's other things that you don't need it for. For example, project does not change the row count, so we can't do anything about that. There's certain things that we can't do some costing on. So in the aggregate, we can look at the kind of uniqueness of those columns, and we can do other sorts of things with other kinds of operations. The cost estimation is to look at things like for hash joins, you need to have one operand as the build side and then the other one is the probe side. So the decision is, now that I've got statistics about the two sizes of the tables, I can figure out which one is going to be the build and the join. So we want to choose the lower cost child as the build join, so as the build side. So the before the build side was the original table side, so build right. But now, based on the estimated cost of the various operators before the join, you can now realize when time you get to the join, it's going to give you a better option if you choose the other option for the build side. So if you look at the example down there, if you looked at the original size, you would choose T2 as the build side because it looks like it's the smaller table. But when you look at the revised cardinality of the table after the filter, it winds up being the smaller side, and then that will allow you to optimize the join. So there's an example of where the cost estimate is using the estimated cardinality that results from an operation to be able to decide what an optimal choice for performing the next operation is going to be. Okay, and so the example here is what would be the various costs of the various strategies. So a broadcast versus a shuffle in terms of a join. So what would be the appropriate way to do it? So the logical plan says you're going to do an inner join or various kinds of joins. And then the physical plan basically looks at various kinds of options for those. And then what you also want to do is to say, well, maybe we can look at for some kind of broadcast where, but we want to know if the output is going to be small enough to actually be used as a broadcast. So again, the cost goes and looks at the value of the various cardinality outputs and then decides the basis of that. So here's we're starting with 5 billion, 100 million here. And so at this point, if we're just looking at just the overall initial table size, then we're not going to look at a broadcast. But if we now look at the cardinality output of the filter based on our estimates, we can see, oh, now that's actually down to 100 kilobytes. So that would be well appropriate for being able to use as a broadcast join, which would be far more efficient. So the physical plan is being chosen at various points based on what's happened to the data up to this point and what kinds of transformations have taken place in terms of the cardinality of the data that we're likely to get at that particular point. Okay. So so this is the other aspect, multi-way join reorder. And there's a strategy here for looking at how to look at the different possible combinations. So we got A, B, and C. We're going to look at possibilities of A join B join C, A join C join B, B join C join A. And what you do is you look at the cardinality results of each of these pairwise joins. So we get those items, and then we want to look at the results of the three-way joins to look at those results, and then continuing on with larger joins. So you're optimizing sort of at each level of the join to choose the joins that's going to give you the step in the join that's going to give you the most economical intermediate result. Okay, so again, that's being able to be done by the ability to reorder the various joins. Again, that's built on some formula there. So we've got estimates of cardinality, and then this goes and is used as an estimate into cost. So there's a weighting value where you're using estimating the cost of the CPU versus the cost of the I/O, where you're basically using size and cardinality as the CPU. The more rows, the more CPU is going to take, and the basic size is going to be the giving you a cost of the I/O, and the weight is that tuning parameter. I think that's one of the parameters you're looking at that you can tune in order to skew the choice towards either a space or a time sort of optimization. And that's configured by the Spark SQL CBO join reorder cardinality weight, where it's currently at 0.7. So it's now skewing a bit towards the CPU size. So, and of course that can be, that's the tunable parameter that you want to look at. Okay, I don't think I want to take a look at this stuff here. Okay, so various kinds of optimizations that were done. So let me see, if we take a look at this, again, there's this is the performance bottleneck, or these large intermediate results, and by reorganizing the join sequence here, we're getting much better intermediate results. And so the again, as it scales up to this very, very large, so there's a lot of joins that are taking place here. So as we start to look at the cumulative cost of the joins, it starts to become somewhat prohibitive. So we're getting very large intermediate results. So the breakdown of the joins into analyzing all of the different combinations of the joins, you wind up being able to optimize the joins all the way through. Okay, so there's the basic idea behind the optimization joins. Okay, I don't think I'll keep going on all of this stuff. I think this is probably all just all here now. Let me see. I think there's some things on here. So this is in 2.2. So this can be experimented with in Spark 2.2. I don't know, but 2.3 is supposed to be on by default. I'm not sure on the status of that. So the there's some information here, I guess, on that. Okay, so oh, and as I point out, this is a work in progress. The one thing here is that it is underestimating shuffle cost, so there are still some weaknesses on it, and so there. Oh, there it is. So this is what they're currently working on, is also doing sampling from large tables, a hint mechanism, and some statistics. So this is still kind of a work in progress, but it does have some benefits over the existing or the previous catalyst, which was just involved in optimizing the logical plan through heuristics. Okay, so that's kind of a general. Let me see, and I think probably we can actually see. Let me look at Spark SQL. Okay, hold on here. I forgot what I was actually looking up here. There we go. I knew there was something here I wanted to look up, and I'm trying to remember what it. Oh, that's what it is. Of course. I started typing it like. started thinking about something else. Analyze table, there we go. Okay, so this is what I wanted to get to earlier. So here's the key command that actually does, so until these statistics are analyzed, you don't really have an ability to really use this cost-based analyzer. So the analyze table collects the table with the analyze statistics, and you can also do various kinds of the table that can be used by that optimizer, and this only collects the basic statistics. This is where you're analyzing now the column statistics for the columns that you want, that you know are going to be critical for the analysis. So the tip is to collect more statistics so you can find better plans. So any column that appears in a query, you want to take statistics for, so that the optimizer can be used. Cost-based optimizer. Let me see. Okay, so this is probably, let me see, this is what I want to do. Yes. So the cost-based optimizer can collect the statistics, and you can do some, now we're back to the explain command. Explain again to explain what's going on, the actual series of operation that the operational plan has developed for us. And there looks like we've got the hints in here, so I don't see any hints here. I'm going to have to check and see how that hints operates so we can look on that. So it'll be on the agenda for tomorrow. I want to make sure we've got that right. So the thing to look at here is if we're looking at the Spark UI to see the execute plan and accurate statistics, if this is missing, it means that there was probably the statistics were not available, or for some reason it wasn't able to create create an estimate. If in this case we had a good estimate from the cost optimizer, and we actually looked at the original estimate, then this would be a good estimate. And this would be an example of a bad estimate where we're 1,000 times off. That would be an example in which the recommended, the cost optimizer recommended a strategy which was really not that, or the strategy wasn't as, the estimate was not as effective. And you can disable the CBO by enabling, by setting that flag to false. Okay, so there's a kind of a basic idea of the optimizer, and I want to check into that hints for you for tomorrow, make sure that they've got that right. So at this point, any particular questions or comments about our lovely Catalyst optimizer? Do you have a sense now of how that Catalyst optimizer is actually working?
I think so, and I also have a question.
Yeah.
To utilize the power of cost-based optimizations, first we have to analyze the data. So in some cases, for example, where we have to, let's say, count the number of lines, it will actually be it will take longer to analyze first and to optimize the query than comparing to running the query without these cost-based optimizations. Because if we're doing these cost-based optimizations, we have to scan the data first.
Yeah, this is where if you're looking at a column-based storage of the data, that'll speed up that process considerably, But even so, again, it's come down to a matter of knowing knowing your data and whether or not that would work. So, I mean, how much data are you thinking about that would cause this optimization to take longer than the actual or the analysis of the data would be offset by the query optimizations?
Well, I'm not thinking about some specific amounts. I'm just thinking that we have to go through the all data just to analyze the content of it, just to know the max and minimum and stuff.
Yeah, well, you see, this is the trade-off that we've got here.
Yeah.
Is that you know, if we don't have a sense of the size of the data, of you know, its kind of range and its size, we don't have sort of this profile of the data, it's very difficult to estimate what the actual size of the computation that we're going to have is.
So it could be using this cost-based optimization with analytics could be very beneficial if we have to run multiple queries on the same data, but maybe not as beneficial if we have to run just one query for one data set, let's say.
Yeah, that's probably a valid use case in the sense that if you've just got a data set, you're running one query on it and it's got a simple join on it, the heuristics will probably give you a better sequence of operations. But again, if you looked at that kind of last example we were looking at when they were running like 20 or 30, you know, joins, or it looked like that, like 10 joins, very, very complex operations which can have intermediate results that blow up, then the value of the optimization starts to show up considerably. So I would say that there's two things to keep in mind. If scanning the data can be a cost, then it becomes really important that the data be stored in some kind of column order, like something like Parquet or ORC, necessarily, where you can do column operations very quickly. That might speed up that whole process, being able to scan through the data. The other thing to remember is that this is done once, and then that's stored as metadata from the table statistics. And as the operations get more and more complex, you're not rescanning the data, but you are reusing that metadata, updating it so you can kind of track the size of the data as it's going through the transformations. So I think you start to get better payback, as you had indicated, as you're going to have multiple intermediate steps and you're going to be doing multiple things with the data. You're now starting to look at this as finding the optimal path solution. So if you've only got one step, you know, there may not be an optimal path. You know, you may get some optimizations, maybe, for example, in choosing the join strategy. For example, when we figured out a broadcast strategy, a broadcast, you know, hash join instead of you know, like a shuffle join. So you might get some optimizations there, but you know, I think it's going to come down to a matter of if you have a good sense of your data and you think that you can make a good estimate as to what you need to do without this CBO, then, you know, there might be a case for that as well. But again, we have to remember too is that this is a work in progress as well. It's continually improving, so the cost of those things may go down. It's one of those things you just have to keep your eye on. Spark is continuously evolving. So but your use case is that you raise a valid point. You know, and you have to ask yourself the question of do I want to do this or not? And now, if you don't want it, you just disable it. And one of the things that might be interesting is to try it with a sample of the data and see if you can benchmark it both ways and see if you actually do get any particular performance that's measurable with some kind of sample or if you've got a data set that's representative of the kind of data that you're going to be using, use that as kind of a set of test data and see whether or not that gives you enough of a performance that you would want to actually use that optimization later. Is that help?
Yeah, totally. Good point. And my other very practical, let's say, question would be, so we analyze the data and store it in some meta store. Let's say we have one CSV file. What would be the meta store for analyze for statistics data? I mean, where it could be persisted if we are not working with Hive or other stuff.
Well, generally, you're going to have to put this into, this is working through the SQL interface, so you're generally
I meant, is it some kind of separate meta store you can configure separately to store just for statistics, or is it built in file format or whatever?
Well, what it's doing is my understanding of it, and the problem with some of these really new innovations is really hard to get really good detailed information on actually what's going on without reading some of the incredibly dense technical stuff they've got. But my understanding is that what it does is you can think of, and again, this is my understanding of it, is that you can think of that meta store as being like an RDD that is going to be going through a series of transformations, and every time that so it starts with that basic meta store of the data with those statistics, and then it for each of the tables, and then it does an evaluation of the cost, the cardinality of output, and it creates transforms those two basically into a new version of a metastore, which now describes the cardinality statistics and everything of the output of that operation. So it's kind of like a running, working area that so you can kind of follow the change in the statistics of the data as it goes through the process. Does that make sense, or does that answer your question?
Did I get it right? The statistics only exist for one session, one Spark session?
Yeah, I believe that they do. Yeah, for that particular set data.
So you cannot store the statistics alongside with your data somewhere for reusing.
I don't know. I haven't found any reference to that. I'll dig a little bit deeper into that. But I don't know if you can serialize out that statistics and store it as metadata. I think you should be able to do that somewhere. It seems to me you should be able to do it, but I haven't found any reference to that point at this point yet. But that's another good question to look at. All right.
Okay, thank you. Yep.
So we want to look at the implementation of hints, and whether we can persist this metadata in some way so that we don't have to rescan the data every time it comes in. I'm assuming that's the motivation of your question, right?
Yeah, all right.
Yeah, okay. And with large data sets, that would make sense. So I'm assuming there's got to be some facility there. I've just got to find the commands that do it. Remember, this is all relatively recent in terms of Spark. So that's kind of our idea on that. So any other questions on the Catalyst Optimizer? We will return to this topic tomorrow and answer those questions.
I do have one more question, but maybe this is for tomorrow. So in general, I might be interested in influencing this optimizer, right? Because I can imagine situations where maybe the optimizer decides on, I don't know, one particular join implementation, which doesn't perform so well, and I just happen to know that a different one would be better, because I do know the data, and the optimizer does. I mean, it doesn't know better because of the imperfect statistics, right? So how could I influence this? So my understanding is that these hints that Robert brought up might have something to it, and in general, I would be interested in knowing what can I do to make my job run faster with the proper plan. without having to maybe rewrite the job from scratch. So how can I influence or override the decisions that the optimizer is making?
Okay, well, I've got a couple of things to explore that I think the hints may be part of the solution. The other thing I keep seeing is that this notion of data histogram, and I'm trying to figure out where that, if it's possible that part of the analysis, and I don't think it was implemented at the time I was reading the documentation, and sounded like this was something that was kind of in the pipeline, was that giving sort of a histogram of the data, which might kind of fill in that kind of piece of information that you know about the data, because you'll notice a number of points it said assuming a uniform distribution of the data. So if what you're saying, if I'm going to infer from what you're saying, is that you know that that's not a uniform distribution of the data, so you know that the cost optimizer is making a recommendation assuming a uniform distribution of data, and in fact is winding up making the wrong recommendation. So I will check and see. The other aspect that might factor into this is the use of a data histogram. And if you're going to get a histogram of the data, and you also have the capability to save that after a scan, then we have some really powerful tools. Failing that, I think those are probably the two mechanisms that'll be available. And like I said, this is an ongoing project to see what actually is available that you can do. One of the things that might be possible is as kind of a hybrid patchwork solution is to look at the optimizer plan and use that as sort of a template on how to actually structure your own query and inserting your own custom suggestions or your operations at various points. So there's that to me would seem to be a horrible solution, but that may be very possibly the way to do it. Okay, so before I go any further, just give me one moment. I have to reach my pen, so hold on for a sec, guys. Hints: persistent metadata and overriding CBO recommendations. Okay, so those are the three things we're going to touch on tomorrow, along with tungsten. Okay, so I sort of disrupted the overall flow of the course in order to kind of do this dive into this optimizer, particularly since I know that it looks like the materials that we're using are a little bit older, and they don't have any actual reference to the CBO, because I don't even know if it was released at that particular time. Okay, all right. So any other areas you'd like to explore on that, we can put on the list and deal with that tomorrow as well. Anybody?
Yes, Gerald speaking. I have another request. Until now, we mentioned that we are able to put Spark properties on job executions, and we also saw property for the cost-based optimizer and so on. But it would be nice to talk about memory and CPU of executors, these kind of Spark properties, and also shuffle properties. A lot of them are not actually all the Spark properties which are available on the specific version of Spark are defined on the documentation, but I guess most of them are explained. But it's sometimes hard to understand them and also understand the implications of.
Yeah. Okay. Okay. So one of the other things I will mention is now that you've mentioned it. So memory CPU allocation. There's a couple of things we've seen here. So we've got that weighting factor we can do with Catalyst that allows us to kind of, do the final cost analysis weighting towards CPU versus storage. But the one deficiency, and I don't know if it's been addressed yet, we'll have to see what the latest release notes are on this one, is that it is not taking into account shuffle costs. Generally using the heuristics part of Catalyst does reduce the overall shuffle cost tremendously. But what we'll do is we'll sort of get a list of heuristics for reducing shuffle costs. Some shuffles, based on what we're doing, may be absolutely unavoidable. So then the question is, how do we reduce the cost of that? We've looked at some of the heuristics sort of as we've been doing, as we've been going through that. So for example, one of the things is that we want to often, if we are going to do a shuffle, to minimize or to push the shuffle to a point where the amount of data we're shuffling has been reduced in order to reduce the transit time. So maybe what we'll do is take a look at specific strategies to reduce shuffles in addition to Catalyst. The memory issues we'll take a look at tomorrow, specifically when we start talking about tungsten and the sort of related technologies that revolve around that. So, all right, that gets us. Yes.
Sorry, I have to interrupt again. Not sure whether my request was precise enough. I'm more or less not specifically referring to the optimizers. I'm more referring to basic Spark properties like Spark driver memory, Spark executor memory, and those overheads, and what makes sense regarding how many executors per worker node. These kind of basic things and the implication. The job depending on the data I have. Yeah.
So Spark resource allocation.
Yeah, kind of, yeah.
Oh, okay. Yeah, I'm sure that there's got to be some kind of rules of thumb that are out there. I'll double check on that one. I mean, we've been talking about from more of a qualitative point of view, but I think it sounds like you're more interested in, are there sort of like algorithmic guidelines to suggest different kinds of resource allocation strategies? Is that right?
Yes, yes, sounds good.
Okay. Organized maybe by use case?
Sorry, can you repeat this?
Sort of like on a use case basis?
Yeah, I mean, exactly. It also depends on the data you have. When you have, and also it depends on the worker nodes you have. So yeah, obviously when you have a lot of data and so jobs was handling a lot of data, and you have, I don't know, 20 worker nodes with only 20 gigabytes of memory each, then you have to be thoughtful about how to set your executor memory, and also driver memory on the Spark master in order that the Spark master is able to handle and distribute all the jobs to the different workers. Because I experienced somehow in one application that we have in Cryolytics that the amount of workers was slowing down the whole execution just because the master node was not able to handle all those worker nodes and was not able to distribute all the jobs. These kind of things.
Yeah, okay. Well, I'm sure you're not the only person that's experienced that kind of issue. So we'll see what the best practices are in doing that sort of thing. That'll also tie in a little bit to the kind of control we have over memory allocation within the individual worker nodes. Okay, so resource allocation use cases. All right, good. Okay, now for the last bit of the class, I do have to make sure that we cover off some other material in the class, but I wanted to insert this chunk, this sort of 90-minute chunk or so, in order to add the Catalyst material in that I thought we got some indication you guys were interested in. So I hope that met that objective. But did that actually meet your objectives in terms of what you wanted to learn about Catalyst? I just would like to know for my own edification.
Yes, I would say so.
Oh, you say so? Okay, good. That was the objective I really wanted to do. I wanted to I knew that was important for you guys, and I wanted to make sure we got that. Okay, so now we're going to go back to good old mundane, everyday, ordinary, you know, Spark. So we're going to just go through a couple of these. And I think some of this stuff might be very familiar to you, but we just got to do this for a bit of completeness, because again, one of the requirements I always have as an instructor is when I'm doing this for a client, the client always wants to ensure that all the material in the course has been presented at least in a cursory manner, so that there's the commitment is fulfilled, and it's reasonable. I have no problem with it, but I'm going to try not to bore you guys with stuff that you already know. So we might move very quickly through some of it. Okay, so the pipelines. So the machine learning, we've got to take a little look at the machine learning section as well. Again, we'll do that fairly quickly. We did the little AI overview, and there are excuse me, I'm about to cough. So we got to prepare the data for analysis, different ways to model the data, evaluating models, and we've got to be able to continue on doing that. So the machine learning workflow is to pull data from all, and this is not just a machine learning workflow. This is a standard sort of ATL and ETL/data mining /DMCrisp sort of model, where we're pulling the data from multiple sources, pre-processing, feature engineering, and modifying the data in a way that becomes usable, cleaning and structuring the data, and then using some kind of modeling analytical techniques, tuning the data, tuning the parameters of the model, and then do an evaluation. And when we meet our performance criteria levels, then we have then we have completed the process. So the machine learning steps is to gather and collect the data. Again, similar to all these other kinds of operations, cleaning and inspecting it to better understand it, know your data, performing feature engineering, put the data into a form, restructure the data, reorganize the data, rearrange the data, converting data to different formats that are useful, partitioning, repartitioning, using a portion of the data as a training set, and then use this to train the candidate models, which are things like decision trees and cluster analysis and random forest and support vector, all of the buzzwords that are floating around in the machine learning community. We also would feed this in a more familiar setting into a data mining data set and run the various data mining algorithms on it. Again, like k-means analysis and k-cluster cluster analysis, and the similar other kinds of algorithms that we use in that kind of world, which has a kind of a blurry boundary between the worlds of machine learning and data mining. Evaluating, comparing models against the success criteria. How do we know if a model is good enough? Just as a side commentary here, we're doing really bad at that in some cases in machine learning. The city of New York deployed a facial recognition system to one of the tunnels in New York, and it was supposed to identify drivers as they went through the tunnels. after the first field test, it had a 0% success rate, which is about as bad as you can get. While we say that we're evaluating a success criteria, there is a lot of work to be done yet in this area. So machine learning is not doing as well as it could. In fact, one of my projects is right now adapting testing techniques from other industries into software testing in order to develop protocols for testing machine learning models. We basically then basically lines is leverage the insights to basically deploy into the wild. Data collection, collect the data. Again, Spark is being suggested here as a good tool because you can pull in the data from multiple types of data sources: structured, unstructured data, data sets, CVS, JSON. Clean and inspect the data. Cleaning the data, generally the thing we're normally interested in, and this is where some of the data analytics is actually differentiating from the machine learning models. As in the machine learning, we often want to really clean the data to a point where we have no significant outliers, because we're more interested in general trends. So we do noise reduction, noise in terms of signal analysis and things like that. And so we exploratory data analysis tells us sort of the quality of the data, missing data. Is the data systemically skewed in some particular manner? It needs to be skewed back. One of the more common kinds of exploratory things is to notice, if we're working particularly with financial analysis, what was the currency recorded in of multiple currencies, or what the dates, so that we get the appropriate conversion factors. Historical, do we need a baseline for historical analysis, like 1970 euro or 1990 euros versus I never done the years 1990, say even American dollars as a base currency. What year of American dollars? We look at obvious errors, like somebody being reported as being minus 200 years old, and so data cleaning can be done by transformers. So we can use Spark to actually use transformers to clean the data, and then go into what we call feature engineering. Cleaning, I think that should just be cleaning your data set, and then convert it to a form suitable for the algorithm, which generally means restructuring the data in some way that's easy to access. The feature engineering is choosing the features that make the application. One of the consulting firms was selling a resume analysis machine learning system to a client, and which basically would feed it a bunch of resumes, and it would spit out the people most likely to be successful at that firm or in that industry. And when they actually looked at what the algorithm was, one of its main decisions criteria was that the people that would be most successful at that industry had two primary characteristics. Their names were Jared, and they played lacrosse in school. And that seemed to be a little bit of a bad feature engineering right there. Normalizing data, if we're talking about pricing and financials, again, normalizing data to some kind of base value currency. Trying to expose what we call hidden variables, so that we are uncovering hidden dependencies, so that we can work with those, and then manipulating categorical variables. Often we're not interested in individual data points, we're interested in trends. So variables are usually kept as input vectors of doubles, so there's a variety of approaches we can take to do this feature engineering. So there are so it's a variety of machine learning statistical techniques. I don't know why somebody's got a password in there. So we have this data set of historical information that we've now massaged and processed, and then we may label or tag what the expected output should be from our model to give us supervised learning. And then we have defined a particular predictive capability we want from the model. So to decide whether email is spam or not, or to decide whether a transaction looks fraudulent at a bank. Then we run our chosen model against that historical data to see whether or not we can produce some kind of predictive model that will minimize the error when we train it on the training data, so it fits the training data. And then we kind of tune the parameters until we get our least amount of error between our predictions and the actual values. And then once we've minimized that, then we run that on the test data to ensure that it performs on data that it hasn't been trained on to similar levels of error. We want to know that our model is good. So there's a couple of ways that this is done and actually should be done and could be done. One of them is just to split the data into multiple sets and use one for training and one for testing, so that we can see if the model developed on the training set is going to be applicable to the testing set. Another way is to use an n-fold splitting up of the data. And then we train on 1 and then test on 9, and we train on 2, or we have 2 data sets and we alternate them. We train on 1, test on the other, then they switch roles to see if our model is actually any better than that. So this is really a classic problem of what we call also underfitting and overfitting, where our model might work really well for our training data, but when we stick it out in the general population, it just totally sucks. And this is what's happened with facial recognition. What a lot of people don't realize is that facial recognitions, our models are being trained on standardized images, which are all white male faces. So it fits white male faces really well, but when you deploy it out into the field, you tend to find it does very poorly with female faces and faces of non-white males. So in other words, it overtrained and overfit the training set, and so it wasn't effective out in the real world. So this is what we generally tend to do. There's a couple of other tests that should be performed. For example, you can do simple tests to say is my training set representative sample of the population which we're going to be running the model on, and the model and that's our overfitting. Underfitting is where the model doesn't really explain the training set too well, but that's okay because it tends to also work just as well out in the field. So what we want to do is look at tuning the different parameters and compare variations to the model without overfitting to the test set. And so this is where we get the analytics with Spark. So we use the structured APIs to read in the raw data. We use transformers and estimators to pre-process and clean the data, and then estimators and modelers to actually create the modeling techniques. And we use pipelines for cross-validation, and we do the tuning. So what we have so that's the kind of the pipeline flow, and so Spark has the machine learning library on top of this, and so it fills in all of these various gaps. So the structured API refers to reading the data from different sources with fundamental structural types. Transformers, estimators, evaluators, and pipelines, and transformers, as you would expect, convert raw data in some way. They can create new variables, normalize a column, just simply modify the data type, And so we can take string variables like male, female, and convert them into numerical values like 1 and 2, or country names like Germany and Italy, and convert them into standard codes like a DE and IT. So we can take a variety of things. So this is often important in multilingual settings as well, for data from multilingual sources. So we can use transformers and estimators to clean and structure the data. So the transformers pre-process, they take a data frame as an input and produce a new data frame as an output. And you can see this already is starting to have some interesting relationship to various kinds of Scala operations as well. So we have an input and we have an output, and we can transform the various columns on the data frame by applying mapping a transformation across that column. The two kinds of estimators are estimators and evaluators. So an estimator is a transformer initialized with data, so it normalizes to normalize numerical values, initialize the transformation, give it information about the current values in the column, and use that to normalize. So it requires a two-pass to generalize the initialization values, and then second, to actually apply the generated function over the data. So this is a fairly standard operation we're going to see in almost every machine learning application. So the algorithms that train a model from data are called the estimators. So the evaluators allow us to see how a given model performs. So the estimators again are really producing a set of values to apply in the model as well. So the evaluators now, given our kind of model parameters, are going to evaluate how well the model is actually performing using this particular criteria that have been identified as performance evaluation. So then the evaluator says, okay, so given all of these different estimators that you used to create the kinds of model parameters, which one of them actually gave us the best result in terms of the criteria? So we so the steps in the pipeline are transform the data. Estimators are basically able to go and modify the rows. And really what we're doing here is applying some kind of weighted parameters to evaluate the data. And then the evaluation, I don't want to say evaluate because it's evaluators, well, okay, this evaluates the input to a particular computed value, and then the evaluator itself proper takes that computed value and compares it against what's expected to produce some kind of measure of correctness. Okay, so the hyperparameters are the parameters that affect the training process, model architecture, regularization, and they are set. So these are the choices of in the model that are being made by the modeler to produce the particular training process. So for example, if we're doing a linear regression, the parameters, what we're tuning out is the weights to the regression hyperplane. by tuning those parameters, we can make our hyperplane reduce some kind of error measure, often kind of some like a mean squared error. Logistic regression also has a hyperparameter. It determines how much regularization should be performed. So this kind of also prevents overfitting to the data. And what we do is we often will scale different kinds of parameters to see if the data overfits or not. So generally, if we have a data set, we can often find some kind of cubic or quadratic that will fit the data really nicely, but it doesn't extend well into the overall population. It just overfits the data. So we have some parameters that allow us not to get data that's too closely fitted to the test set to guard against overfitting. And then we can compare how these different models actually work on the test set. So the workflow in Spark is to keep track of the is to use the pipeline to keep track of the various steps that we go in machine learning. So we set up this data flow, look at the transformations, have an estimator, and then do an evaluator, and then tune the parameters. And we do this in an iterative manner until we finally realize, decide that our model parameters are our models ready to use. We've kind of reached a fixed point in terms of our error or a minimum point. And there's a variety of techniques that also are used, like gradient descent, to choose our next set of parameters to minimize the cost or the error in the model. So there's the pipeline diagram, and that's basically how we kind of work on the idea. Now, some of the ideas here are probably going to be related very much to what you're doing. So you might want to think about some of the analogies that are there. But again, we just kind of wanted to get through that chunk of material. Now I can say I've done it. Okay, so what I'm going to do is I am going to suggest we've got about half an hour left. And we can have some, I'm going to, by the way, make sure I get all these slides into the appropriate repository and set that up for you today. So what we've done is we've gotten up to about here. And what I'm going to suggest is that I think this one is sort of passé. Out of the following topics, is there any that you specifically would like to take a review of? And I'll put those at the top of the priority list. We'll try to fit some parameters here. So we've got streaming, Spark streaming, Spark Hadoop, NoSQL, Spark UDFs, and case studies. Any particular ones of those that you would like to prioritize to make sure that we cover? What do you guys think?
I would vote for UDFs.
UDFs? Okay.
Yeah.
All right. Okay, good. So that's where we're going to break into that. So we'll make sure we do UDFs. GraphX, I think that was struck off the list, so I don't think we're going to be dealing with that. What about the streaming? Is that of any interest at all?
We don't have much use case for streaming at the moment, and to be fairly honest, like we use a bunch of UDFs, like quite a lot. Okay. And so since maybe not everyone is familiar with what is a UDF, that would be great if we actually can have kind of proper introduction on this, because it's something that's kind of pretty handy for us.
Okay. All right. So at this point, I kind of underestimated or overestimated the amount of time I was going to take. So I'm finished about 25 minutes earlier than I thought I would be. I guess I just talked a lot faster than I thought I would. But what I'll do is I will, tomorrow, the agenda is we're going to take a look at those questions that came up on Catalyst. I'm also going to look at Tungsten and the question that came up about setting parameters for resource allocation. We'll look at Spark, UDFs. Now, is there any other topic that we want to cover on our last session other than the ones I've just mentioned?
So as far as I remember, we weren't able to complete the Hive lab.
Oh, the Hive one. Yes, of course. I'll have to take a look at that too.
I'm not sure if we still want to do this, but yeah.
Okay, if you want,
I would like to do it.
That'd be great to. That'd be great to also be able to do this. Yeah, again, we have some components that use Hive.
Yes.
So you could just get familiar with the Hive command line and just know a little bit how to make it. Although it's not rocket science, but it's
okay. So Hive on there too. Okay.
I mean, it's an underlying thing, right? So it's always good to understand how it works.
All right. Good. Okay. Anything else that you can think of?
Well, I heard that UDFs are screwing up the planner, or basically can't be really estimated by the planner. So I wonder whether there are options for UDFs, or whether it will be covered there, to give hints to the planner on how complicated a UDF is or not.
You're referring to Catalyst as the planner?
Yeah, wherever it gets planned.
Oh, okay.
So basically,
right.
we are using data frames, and there we apply some UDFs, and in the end, a plan is generated in the background.
All right.
And there was a hint in one of the previous sessions that UDFs can't be respected by the planner.
Okay.
Maybe they can.
All right. Okay. All right. Okay. Well, those are the things we want to cover for sure. I think I've actually done enough on the rest of it to satisfy the kind of like standard based content delivery. I'd like to really focus just on the issues that are of interest to you guys for the 4 hours we have tomorrow. Are you guys opposed to ending earlier? Would you like to go on to something else? It's up to you.
I'm fine if we can have like the topic we discussed today, tomorrow, during the 4 hours, and because I think there is then nothing new we can start today anyway. It's like 20 minutes left.
No, because we wouldn't have a whole lot of time. So maybe we can do that. And but I'll leave the machines up again for another hour. So I'll shut the machines down in about an hour or so. Okay, unless anybody wants me to leave theirs up for a little bit longer.
Yeah, we have some questions though.
Yeah, just one small question about yesterday's slides and broadcasting values. So in the example there was a data set which was broadcasted as a value. Am I right, or am I mixing something?
Data set, I think, yeah. As I recall, may have been, yeah.
My question would be, so to kick off execution, you have to ask for an action, like to collect or to something else. So would this broadcasting happen? Would broadcasting value mean kicking execution of it, or it will be delayed?
I just off the top of my head, I don't think it'll kick off execution, but I will double check that because
yeah, just out of curiosity, I don't know how it ended up in my mind, but I'm curious.
No, I mean it's a good question. Now that you've said it, it's bothering me because my first instinct is to say no, it doesn't. And the reason why I say that is because normally execution is kicked off by something that forces some kind of value to be returned. And when you're broadcasting a data set, you're not forcing a value to be returned. So you're not kicking off an execution. That's the first thing that pops into my mind. but you know, there may be some kind of way that it's implemented that in fact it does. So I'll check on that.
It's a bit more complicated than that, because the data sets and the RDD and data frame, they live only in the driver. So you can't broadcast the data set with the plan inside the data set to the executor. What you can broadcast is only the result of
value.
the data set, which is basically the same as doing a dataset.collect. So when you kick this, the laziness is evaluated, and at that moment it kicks off and it's
so it does, okay.
Action, and it's sent basically to the executor, so it broadcasts the value. But to be called, I think to be called, that's not enough to trigger the computation by itself. You still have to have at the end like a write, like a flush, or a collect, or take, or something by itself. So I think it's an action, but it's not evaluated until you call like maybe something that produces, like you use it basically.
Yeah, you see, my kind of general sense is that you don't actually do any computation until you have to return something, because it's at that point that you know what the final output is going to be, has to be, and then you kind of start working backwards through the chain of operations. So it just seems to me logically that a broadcast doesn't give you the necessary trigger to do that, but I will double check to make sure that everything works exactly as it should. Okay.
I mean, a perfect example is that basically when you do a join for data frame, you can broadcast the smaller data frame, so the dimension that you use for the join, for example, with the dimension entries in the join. And join is transformation, it's not an action. So basically the moment you will request the result of this join, you will basically trigger the computation, and then the broadcast will be done. But at the moment where you call the join with the broadcast on the data frame, then nothing happens.
Yeah. Okay. All right.
Can I also ask something maybe about the further topics that we're going to discuss tomorrow? I would be particularly interested, to be honest, in Spark streaming, even though we're saying that we don't have a use case for it. I'd be interested what actually are use cases for it. And
okay.
So yeah, so if I would put this a little bit lower priority than mentioned before. So if we have any time left, I would be happy to see what it's about.
Okay, so we certainly would prioritize UDFs over streaming.
Yeah, but high-level overview and use cases would be very nice.
Yeah.
Okay. All right. Well, okay. That's a good list to kind of summarize things. Now that we've got a little bit more flexibility in terms of the time, we'll start that list tomorrow, and we'll end today about 15 minutes early. So then, if there are no more questions, of course, questions take priority. Any other questions that you might have?
I guess not from Berlin.
No, not from Berlin. Have a good evening, afternoon.
Okay. So you guys go and enjoy the rest of your afternoon then. Have a good one. Okay.
Yeah. Bye.
Bye.
Okay. Bye. Take care, everybody.
Bye.
See you tomorrow. So we've got we've progressed fairly quickly, and I have attempted to find answers to or provide answers to most of the questions that were there. There's a few that I've been able to dig into some documentation, but again, there's a couple of issues. Is that it seems that some of these things haven't made it into the documentation yet, but there's sort of hints there. But there's also another issue of ensuring that we're up to the actual 2.4 release. So we will do what we've got. And before I forget, one of the things I did spend some time looking at, because it was a good question, was about whether we can persist and then restore the metadata for the statistics. And as near as I'm able to determine by going through a number of different sources, you can copy it, you can save it, but there's no way to actually restore the actual metadata pool that's being used. And as I was thinking about it, it said that kind of made sense to me, because that is the kind of working area of the CBO. And
so you can save metadata but cannot restore it?
That's right. So you can save it into files. You can save it. You can save copies of it. You save all of the information. You can display it. You can save it into a variable, and then of course save it out as a file. So you can keep copies of it, but you can't restore it back into the working cache. So it looks like you would have to rescan the data. And my understanding when I'm thinking about it is that because that is constantly being modified as it's going through the optimization process, if you could restore it, it might be possible to overwrite data to critical point, and then your whole process would go down the tubes. At least that's a hypothesis I have. So that it seems to make sense to me. So it appears, if there is a way to do it, I have not been able to find out how to do that. So, but it does look to me as if that can only be generated by Spark itself, and then cannot be cannot be modified except by Spark. So it's like we have read permissions on it, but we don't have write permissions on it. So we'll go back and talk about that a little bit earlier. So that's one of the things that we had. There are a couple places where we can actually give the hints into the CBO, and we'll take a look at some of the docs on that as well. And there's a couple of, let me see, override CBO. And can we override the CBO recommendations? I think that's probably done through the hints, but I did actually discover what I'd been looking for earlier, which was the documentation on the rules that are applied. And we can enable and disable certain rules if we don't want the rules to be applied. So we'll take a look at that as well. All right, so those are kind of some of the things that we're going to take a look at. I didn't actually have a lot of time. I'm actually teaching a class in the evening and in the afternoon, so I kind of worked on that quite quickly. So I may have missed something, but okay. But what we wanted to do is also to cover off some of the. Anyway, what I was going to say is that we are maybe finished a bit early today. That's because you guys have been actually quite quick on the uptake. So we may have some slack time at the end, and then we can discuss it then at what we want to do with that slack time, since it's your class. And I'd also like to get a little bit of feedback also before we begin. So just how has it been going so far for you in the class? Has it been useful? Has it been a good experience for you? This is our last session. Is there anything other than sort of answering the questions and covering off the last of the material that that might be of use or value to you? So maybe we'll see what Robert, what's your take on it all? I'll put you on this one. I'm going in reverse alphabetical order here.
Yeah. So we actually asked for an advanced Spark training when we scheduled this training. And I think at the beginning we had many basics that I didn't assume to be part of the advanced training. I don't know if it's because you had to jump in as a trainer and was given these materials. So I was very happy about the last 1 or 2 days where we were deep diving more into the performance tuning and the background stuff, even with the additional material you showed yesterday. So that was really helpful for me at least, because I already had the background.
Okay, good. All right, thank you. Yeah, I was sort of working with the materials that were available. So Michael, how about you?
So from my point of view, since I've been starting not from a position where I did a lot of with Spark, I sort of enjoyed the more introductory days. They sort of helped me get up and running. But what I would say, and maybe others could disagree, I would appreciate maybe a little bit faster pace. So the material was sort of driving home the same idea from 5 different angles. And I think I got it the second time.
Okay. All right.
So that would be my only sort of point where I sort of got it the first, maybe the second time, but it was sort of on very simple, even simplistic examples. It was trying to sort of illustrate some.
Yeah, I get your point. Good point.
That said, maybe it would be worthwhile to sort of drive it home from a different angle on a more complicated example, because all of the examples we have worked with within the material were very simplistic. And what I sort of always like to do is, okay, maybe a simple example first, but maybe then something more involved, engaging, right?
Yeah.
And I was sort of maybe missing that. So we always talked about something in sort of a generic terms, then looked at some maybe applications of it. But what I would sort of, well, let me give you an example of what I would like to see. I don't know if today, but what I would like to see is sort of have a relatively complicated query, let's say. And so let's say we have 5 tables, we need to join them all together. There's filters everywhere. There could be CTEs. I don't know what. So a complicated query that does not perform well given a relatively big size data set. And how do we take that and sort of deconstruct why it's not performing well? And then what can we do to make it perform well?
Yeah.
So not just simple, but like I said, a few tables all joining together and all that kind of stuff.
Okay.
That's what I would like to see.
Okay, good. Thank you. Let me see. Gerald, how about you?
Yeah. So regarding the point that Robert was bringing up, I was kind of thinking the same. As this is called advanced, but I guess due to the diversity of the group that you are teaching here, it's quite useful. And also, yeah, I was kind of, when I was coming into Spark, I was jumping into a complex system, and for me it was also worth seeing the basics again in a more structured way. But yeah, in the last two days there were some really interesting and interesting points regarding optimization. So I really like that. Maybe one more point. So sometimes I was missing the detail about which version of Spark is doing certain things automatically, because in Spark 2 there are certain things happening by default. I mean, yesterday we mentioned it for the cost based optimizer that it is set to false for 2.2, but then it's automatically switched on for 2.3. And in the last couple of days there were other examples. I think that the hash partitioner was also some example that was which is automatically somehow switched on for a more recent version of Spark. So sometimes I missed the precision in terms of which version is doing what automatically, and gives you these kind of optimizations by default.
Okay, good. Thank you. Yeah, all right. That's good feedback. And Berlin, I'm just going to let you kind of say who you are and organize yourselves there.
I think it's Evgeny, and I think I'm on the same page with guys, especially Robert. And especially because I quite recently went through Spark course, and I just saw all the same basics, and I had very fresh memory on it, and it was just 3 days were just not as entertaining, let's say, as past 2.
Okay. Well, I will try and be entertaining today as well.
Yeah,
Right.
would be nice.
Okay.
Also, I like Mike's idea about having very kind of complex query and exploring and digging inside.
Okay, I think I like that idea too. So the reason I'm collecting this information because I try to make recommendations as to how to do this course better. This is the first time I've taught this course with this material, so yeah, I'm resonating with some of your comments here. So this is where you've got some good suggestions. I really like that, working through a very complicated example. Okay, thanks. Next one up in Berlin.
Yeah, it's Gregory. So I would say in general, the pace for me was like a little bit too slow as well.
Okay.
I mean, I would have liked more hands-on, like small hands-on instead of like 30 minutes 30 minutes like workshop where we are basically not left on our own, but like everyone is like experimenting things, but rather something incremental where basically we could just start like a chapter, having our development environment, and then you basically go through the slide, and in some slide we just stop, and it's kind of interactive with what we see at the screen, and not like we have to go get instructions, do the stuff by ourselves.
Okay.
Yeah, and second stuff is regarding the Spark Labs. Yeah, most of the time it's just copy paste, and there is much explanation about it, and it would be maybe nice to just have some like shorter introductions, because after all, copy paste shouldn't take more than 10 minutes in most of the case, and some like exercises where we are kind of like put into a real or not real situation, but let's say where we can explore by ourselves and not just copy paste.
Okay.
So like giving the chance to test more or less what we learned previously.
Okay. All right. Thank you. Is there next one up there?
So it's Roman speaking. Basically, not much to add to what the guy said before. Actually, maybe I have the less knowledge about Spark in the group because I was also attending this Coursera course. Okay. So I was also attending this Coursera course, but I didn't have time to finish it, unfortunately. So some of the basic concepts were not clear for me initially, and it's really good that we went through all the basics. So yeah.
Okay.
Well, maybe the pace that we're having right now is because of me and the other guy. Anyway, about the course content itself, I find it pretty interesting. However, for the Spark labs, I have to agree with the guys that some of the labs, unfortunately, I don't find usable for me. Specifically this lab that we were doing lately yesterday.
Okay.
That was about the JVM tools. So I really haven't found any clear instructions on how to use them to our benefit.
Okay.
Yeah.
All right. Anybody else? Is there anybody else in Berlin?
Yeah, there's other people.
Oh, okay.
Yeah. Okay, so Manu here. Again, nothing much to add. So I would just double down on faster pace at some point. I also enjoyed, let's say, going through the fundamentals, but again, maybe that part could have been a bit faster. But again, I do have some experience with Spark, and other people don't. Yeah. So I mean, a different perspective there. And then I enjoyed, let's say, whenever we were talking about any feature really. So there is the aspect of the API and, let's say, what's happening functionally, right? But I really enjoyed when, let's say, we were touching on, okay, so what are the implications? So what's really happening under the hood? So data is being moved from here to here. So there is this serialization that we have to take into account. So, I mean, those looks into the inner workings of the system. Those are the kind of insights that I appreciate the most. So in the sense that they they give you a better understanding of how this machinery is working, right? And then also touching with what Mike mentioned, so maybe this practical perspective, so coming up with some hypothetical scenario and how do we approach it, that's something very interesting as well. So just to complete the more theoretical, let's say, perspective. So yeah.
Okay.
That's it. Yeah.
Good. Is there anyone else, sir?
It's Yorgos. I'm the last one. So for me, I think I'm the least experienced guy here. I pretty much enjoyed the course. But I would agree with Gregory and Roman regarding the labs that we could use some incremental approach. Yeah, especially the part with all these Java utility tools. I don't think it helped anyone.
Okay. All right. Good. Well, thank you all very much, because I want to make those recommendations. Like I said, the first time I've used these materials in this course, and I didn't get really a chance to look at the labs, but I think you've given me some really good ideas onto improving this. And I'm thinking that what I really want to approach here now is actually maybe sit down and develop a Spark internals course, and specifically for people like you guys, because having heard your feedback, it kind of makes me kind of want to do this, because that's the kind of thing I like doing. Okay, thank you all very much. Appreciate that. And we'll get to it. So we're going to now, keeping in mind the pacing issue, we shall very quickly pace through ourselves through this the streaming, just simply because some people raised some interest in that yesterday, and we'll see if particularly since you are in a streaming environment, I know there are a couple of guys who are not fully sparked in, or you're kind of starting off. So we'll do kind of hope address that for them, and also review for some of the other people. So we'll do this quickly, so we've got this done. Then what I want to do is I want to go and take a look at a deep dive into Tungsten. I'm going to be going to use some of the slides from one of the developers of Tungsten, but we'll kind of deep dive into that, and we'll see what's going on, actually going on in the world of Tungsten. And then we'll go back and take a look at some of the issues on CBO optimizing, and whatever other grab bag of issues that we have. Okay. All right. So let's move this over here. Okay. So streaming. Okay. All right. So the streaming concept here, very simple, is we're getting data in on a continuous basis, and we're usually doing some kind of visioning on it, so we don't have to review the history particularly, but the use case is particular with IoT and continuous data capture and that sort of thing. Obviously, we're getting considerable emphasis on the ability to be able to work with streaming data in near real time. One of the sort of cases that a lot of people that I work with or deal with is actually analyzing IoT type of information in terms of feedback analysis, fault detection. So there's a wide range of applications out there in which timeliness is an extremely important concern, the ability to process data in a very, very timely manner. So we're talking in this context, real time is in milliseconds, near real time is in seconds, and we also have issues called hard real time, in which we're talking about microseconds, and this is generally in very compact systems in some kind of closed environment, where you need very, very fast response times. streaming concepts, we use event-based, in which we're dealing with every event in the stream as an individual event, or a micro batch where we're bundling up a few of them at a time and processing the bundles. We have the concept of a processing guarantee, where each event is processed at least once, or it's processed at most once, or it's processed exactly once. And each one of those is a particular use case. We want to take a look at the state management. Then we have to talk about the difference between event time, when the actual event occurred, versus when we receive it. So there's a gap there. Window operations, we're often interested in looking at the change of something over a particular window of time, and also back pressure adjustment when we get various kinds of bursts of data and other kinds of things coming in. So the event-based is where we're processing them individually, and so that generally gives us low latency, and there are a number of frameworks that support that. Again, I find myself sometimes getting a framework overload. There's so many frameworks in so many different areas I'm working on. It's sometimes hard to remember which one is which even. So there's the Storm, Flink, Nifi, and Samza framework. Microbatch. So this is events arriving within a frame are a particular time interval batched together, and that introduces a latency factor. And so what Spark streaming allows that to happen. So there's the event versus batched, fairly simple concept, fairly simple graphic. The processing guarantees in the model say that at most once ensures that there's no duplicate processing, but you are not guaranteed processing. So the example for the use case there is web requests. If the web server is busy, requests are dropped, but you want to have the same request not processed more than once, at least once. That guarantees no dropped events, but the guarantee of processing them at least once may require or may result in a situation where you're processing more than once. And so these are generally going to need some kind of opportunity to do a replay or to reset or a resubmit, which requires some kind of durable buffer. So the idea is that in some use cases there's idempotent operations, so it doesn't matter if you do process it more than once. It's not going to make any difference to the final outcome. The at least once does not allow you to count, because you may get overcount as you reprocess the particular events, and that is considered to be the most common implementation. That's interesting. Exactly once, no dropped events, no duplicate processing. You need both a buffer and a state tracking system in order to do that effectively. So if you are going to not do any duplicate counting, one of the things you have to make sure is that you're only counting each thing once, so we get the appropriate count. So each one of those has its appropriate use case. Couple of other examples: GPS routing at most once. We don't want to give the same instruction twice and have people drive into a river. Credit card transaction processing exactly once. The vendor does not want us to drop the event. The customer does not want us to process it more than once. And sending emails at least once. We don't want to miss any emails, but if we get the same email twice, then who cares? State management is the process of remembering what state is associated with the events. Per event processing, we don't need states, because we're generally only interested in the instantaneous event and what happens. We're not interested in tracking trends, but when we're actually doing complex operations, we do require a state. Aggregations, counting, averaging, all those kinds of operations. So the idea we cannot answer the question, what's the maximum temperature or today everybody's asking what's the minimum temperature reported in the last hour. If we're processing on an event level, we can't answer that. We need to process in a batch over that hour window to see what actually is. We'd have to remember what happens. So over a period of time. So SQL analogy, select doesn't need state because you are only interested in each individual item as a unique event, whereas group by requires you to be able to access a number of events simultaneously. So, and this framework support that in different ways. So it's a couple of different ways to store state in memory, which means that we do have a very low latency, but of course we do run the risk of losing state. Store it in an external store so that it can be accessed across multiple nodes. And the other way is to create a bundle which contains the event along with the state, so that it is not going to be lost because it's in some kind of disconnected area. But the effect is that it increases the I/O because now we're increasing the size of the event. And there's the example of the two of them, of the three methods in states in memory, states in an external store, and stored with events. Window operations, again, if we're only interested in some aspect or parameter or property of that individual event, we don't need to worry about other events. So for example, if you are looking at a credit card, querying the current balance doesn't need to know anything about state if that event returns a single value. Some operations require a bunch of messages in a time window. One of my credit card purchases I've made today, now I have a time window to look at that. So what's the current value of a stock does not require a window, but what is the rate of change of the stock over 10 minutes does. And that's fairly obvious. Window-based operations, we chunk them up in time. And we'll see in a little bit how that actually works in something like Spark, how that's actually built up. Event time, when did it happen? Arrival time, when did we get here? And we are no guarantee that our arrival time is going to equal to, or the sequence of arrival is necessarily the sequence of events. Some events, based on the architecture of the system and the method of transportation, may wind up being delayed in receipt, particularly if they're coming from different systems. There may be latency issues and other kinds of things that affect the event time and the arrival time. And I'm not even sure the point of this graphic, to tell you the truth. So this is the event time, and this is the arrival time. I think the idea is that the event time is supposed to be 1, 2, 3, 4, 5, 6, 7. So guess that's what that means. Sometimes I have to guess what these graphics mean. Sometime back pressure. Sometimes processing lags behind because we get some kind of activity in the system which is slowing our system down itself, or the back pressure is external, in which we're getting sudden bursts of activity. So, for example, in the United States today, they are starting the impeachment hearings of President Trump at 10 o'clock, and I will guarantee that the amount of tweets and everything is just going to explode. So that's one of the things that people on Twitter are going to have to deal with in terms of back pressure, but I'm sure they're used to doing that. So the possible downside to this is that we may have so much back pressure that we have things being dropped out, buffers are basically overflowing. We can't manage the velocity of the and volume together, and that often is going to produce various kinds of unacceptable situations. So for example, my order didn't get through. the couple of solutions that are generally applied to this is to have the upstream processor slow down, or have a more a longer stay in the buffer, or increased buffer time. Sometimes we use elastic buffers, which allow us to expand to a certain point to take some of the peak. So so one of the things that we can do is basically buffer or throttle the upstream source of the events through some kind of, sometimes we look at the idea of queuing strategies and other sorts of ideas. Or what we do is we reduce the source of the events in some way. If, for example, if we're taking orders coming into a system, we may actually reach a particular point where when somebody tries to place an order into the system, they get a message saying, the system is busy right now, we can't take your order, please try again in 5 minutes, or something to that effect. But you can think of examples of conceptually how that works. So what we really want to do is manage the incoming flow of events if we cannot scale up in order to meet an unexpected demand. One example that comes to mind, I used to work in New York, in down around the stock exchange, and I was working in New York in September of 2001. And I just left town to come back to Ottawa when the 9/11 attack happened. And of course, I had a lot of my colleagues and my employees at that time were traveling into Manhattan in order to go to work. And so we were, of course, very concerned about where they were. So I started trying to call them. And so many people were doing that. There were so many events coming into the cell phone system that literally the entire cell phone system just collapsed under the weight of it. So this is kind of one of the things that in our architectures we always think about is, what's our reasonable peak that we have to think about. So that just was an example that came to mind of when we can actually see literally overwhelming a system with too much data coming in. Streaming architecture. Oh, by the way, my other point on that was shortly after that they got it back up, and then they sent out a message to everybody, said, please do not phone. Please, we cannot handle the volume of phone calls. So everybody, let the first responders use the phone, and the people that actually need to use it just don't. And they were trying to throttle again the kind of events coming in. So we're modeling it after just common sense, really. So the streaming architecture is generally our input data is going into some kind of data bucket, and then the data is moving through a processor, which is putting into data storage. So the bucket is the buffer. It's where we're normalizing the flow of data, and it also is where if we do have some kind of downtime on the processor side, we're not going to wind up losing data. And there's a couple of choices here on buckets, Kinesis, Kafka, MQ, and various other tools that are out there that provide this kind of bucketing. So the processing engine pulls this data from the bucket and then processes it, multiple opportunities, Storm, Spark, Nefi, Flink. I don't even know if I'm saying some of those words correctly. So they all have different kinds of models, and I'm not going to go through comparing each of them, but you can see there's multiple combinations of features that are supported by these various frameworks. So the data store is where the processed data arrives, and this is where we come back to looking at basically the Lambda architecture, which is where the real-time store and the archival store are operating in tandem. So the real-time store is going to be the place where you absorb that real-time data coming in that's going to be accessible. Common usage is some kind of NoSQL storage. Cassandra various kinds of other the temporary repositories. And that is not intended to be a massive amount of store. That's more of a kind of my immediate history, where I can otherwise it doesn't count as real-time storage. Archival store is generally where we've got massive amounts of data being supported, and this is where we start to get into the distributed file systems and large data architectures, and that's where we're generally batch processing the data, because now it's data at rest instead of data in motion. There's that Lambda architecture again. So the new data is coming in. It's being accessible at a speed layer. Particularly interested in if we're trying to monitor things in close to real time. In the 1980s, I was involved in doing a lot of the programming as a kind of a junior programmer for some of the automation of the early automation projects on the stock exchanges, particularly the Sydney Commodities Exchange in Australia. And one of the challenges we had was that we originally designed these systems to handle manual trading systems where people sat at terminals and did trades. And then what happened was automatic trading systems came in and sped up by many, many orders of magnitude the amount of trading that we had. And the problem that we ran into was we had various kinds of stop trade rules that if we started to see the market swing too far one way or the other, we would automatically lock down trading because you get into these panic modes when you're trading, and you can wipe out a market just on sheer panic. And the problem we ran into was that this was after I left the project, is that with these automated trading systems, they were operating so fast, it never got the stop rules a chance to get in. So they had to redesign that to work in a layer where the speed layer become incredibly important in order to be able to deal with the rapid swings in trading. And the kinds of tolerances we were looking at there were again, we often had to pick this stuff up within milliseconds to identify trends. So there are some real challenges to actually being able to look at the kind of overall trends of the overall trends of the market, which would have been something we would have kept in the batch layer, so people could review, what's the historical trend of the market versus what's going on in real time right now. So you can come up with use cases for this, but you eventually have to integrate this data into the master data set, which is why we've got that dual pathway going along. So you guys are probably familiar with that sort of idea. So rather than move from one to the other, we basically duplicate it with the idea that the last amount of data being put into the batch system is generally corresponding to what was in the speed system, and there might be a little bit of a disconnect there, but eventually everything in the speed system is also in the batch system, even if it's not there at the same time. So we generally have a serving layer, which is responsible for serving the queries. The speed layers does real-time queries, and the query layer does the queries using batch and real-time views. Okay, so this comes into play when we've got a Kafka cluster, for example, which is grabbing a bunch of stuff. It's running through Spark streaming, which is now sending something into NoSQL for the real-time queries. And it's also doing I think that should be HDFS, running it into Hadoop at the same time to allow larger scale queries and more linear time queries, or greater depth time queries. So the streaming stack is Kafka, MQ, Amazon Kinesis into the data bucket. Spark is one of the frameworks we provide here for the processing. And then, of course, we sit on top of one of the standard big data storage elements. And we're not going to spend too much time comparing all the different streaming frameworks because, of course, you guys are using Spark. So we'll just mention them. We'll give them each their 10 seconds of fame. So Storm is basically a Twitter product. And Trident is another product that sits on top of Storm. So Storms comes out of the Twitter world. Spark is the Spark Streaming is the module that sits on top of Spark. So there's it tightly integrated into Spark. Flink is developed by a consortium of German universities. I have no ideas which ones or what its distribution is. I'm not actually totally unfamiliar with it. So it's another framework. NIFI is one which comes out of the NSA, which was kind of interesting, and it was open sourced by them. And looks like Onvia was looks probably like a Databricks type of operation. Seems to have been acquired by the Hortonworks, which is now Cloudera. So it comes from a different source. SAMSA is coming out of LinkedIn with tight integration. So all of these frameworks tend to look like they've been started as projects within certain organizations that deal with large amounts of data. You can see the NSA probably deals with massive amounts of data, and all wind up doing a lot of the same basic sort of operations because they're all multiple solutions for the same problem. Okay, so there's our quick view of kind of a streaming architecture and some of the streaming concepts. And we'll finish this off with the quick look at the Spark streaming, and then we'll go into some interesting memory management here.
Excuse me, maybe
yes.
you're wrong. Guys, correct me if I'm wrong, but we would be more interested in Spark streaming overview instead of streaming architecture in general.
Okay.
Because I'm not sure if we need it.
Yeah. Well, again, I thought that was something that somebody indicated yesterday they wanted to see. So we're in the Spark streaming now. Okay.
Or are we interested in streaming in general as well?
I was interested in particularly in Spark streaming.
Yeah.
Yeah, I thought I had detected some interest in both of those topics yesterday, which is why I put them both up there. So hopefully we'll meet everybody's needs this way. Okay. So Spark streaming, okay, streaming, we jump into Spark streaming overview. Spark streaming sits on top of Spark core. Hold on here, there we go. So it's processing live data streams, a boundless data set, which means basically exactly what it sounds like. We process streams in near real time. So it's not a hard real-time system. Excuse me. And we're pulling the data from multiple sources. And a list there of some of the forces we get into it. The importance from us from a Spark point of view is that it's completely and tightly integrated into Spark, so that there's no latency in terms of moving data from one system to another. We're getting high throughput, excellent scaling and fault tolerance, and more importantly, what we can do is utilize the Spark core in order to work with the streaming data. Okay, a couple of use cases there. So let's take a look now at the architecture. There's the standard model we've just looked at. Okay, so here's where it starts to really kind of get interesting. And it structures the streaming computations as small stateless deterministic batch jobs. Not batch jobs, these streams, and it divides live stream into batches of interval seconds, and that is something you can configure. And each batch now becomes an RDD, and this is processed via RDD operations. So what we're doing is getting input stream coming in, it's being turned into batches of input data, and then it's being passed into the Spark engine, which is working on them as resilient data, distributed data sets. So a D stream is a sequence of RDDs representing the input data, and a transformation takes a D stream object it takes a DStream and RDD and turns it into another RDD. So we're transforming the data for computation. And so we have various kinds of transformations that we can perform on it. Then we have an output operation where once we've done this processing of the data, we send it to an external entity. And that can either be into some storage or as input into another process. Okay, so the DStream is the sequence of the RDDs, as we mentioned before. So data streams in, it's broken down into micro batches and then processed. So the operations, again, it seems to be a repetition here, modifying the data. So supports most standard RDD operations and provides stateful operations. Now that means, of course, is the windowed operations where we're tracking this state over a period of time. So the example down at the bottom, we've got a DStream coming in, and we have RDD at time 1, which represents a window of data, RDD at time 2, which is another window of data, and similar for all of the data. So we're getting these chunks of window data coming in. So the receivers are pumping the data in. So the receiver is the tasks that are running in the executors that are collecting the data and actually converting it into the RDDs. So these are the long-running tasks. The idea is that they're sort of perpetual event listeners in a certain sense. And we have as many receivers as we need to collect the data sources. Each receiver uses one CPU core, and then so as it said here, if we're running locally, do not use local ones. It will use one CPU in the core, and then have no cores left for the processing data. So you want to use the other notation down there. So local N, we have N receivers, so the DStream architecture is we have a batch interval which is specified. It could be half a second, a second. Looks like the minimum interval is half a second. At the end of that interval, the events that have accumulated in that interval are then closed, result in a closure of the batch, and then each batch now becomes an RDD. So the processing is distributed like normal RDDs. So at that point, we have regular RDD type processing. So the streaming can continue. So once the batch is closed, we can start working on it while we're continuing to stream and create more RDDs. Now we can integrate this with non-DStream RDDs. Now that we've got our batch RDD, we can actually integrate it with other RDDs. Input batch becomes the new RDD. As the batch interval passes, new RDDs are continuously generated based again on the fact that we've got data coming in containing the stream data captured in that interval. And of course, depending on the density of the items coming in, the RDDs are not necessarily going to be the same size, and we can again apply all the RDD operations to it. So the DStream is an emitter of RDDs, which either batches the live data through the collectors or receivers into an initial RDD, or generates a new RDD by applying the standard model of an RDD transformation that we looked at earlier. So we have a couple of transformation types. Transformations that are stateless, and those are the ones that we're used to from map, filter, count by value, reduce by key, where you don't really need to know anything about any other items in order to be able to do any processing. So you don't need to know anything about state in order to apply a map operation. stateful uses results from previous batches to compute windows, to compute the current batch. And we have sliding windows that track state across time. And examples here is, again, anytime you're looking at any kind of calculation that's monitoring the change of some event. So the percent price increase per trade for a given stock on NASDAQ is an example of that, where you need to be able to window that. So the stateless transformations is where we got a bunch of batches coming in, and we can apply we get our RDDs coming in, and then we can apply some kind of stateless transformation, and we get our nice modified stream without having to reference any of the other batches in the stream. In a stateful transition, we're going to have our batches coming in. So we have a batch interval that was previously set, which is going to determine the time span of the individual batch. But then what we need to do is create a window, and we have to have a window duration, which is how many batches of data need to be used to compute the result, and then the slide duration, which is how often do you compute it. So in the model we're looking at here, our original D stream is creating a series of batches at time 1, time 2, time 3, time 4. We have a duration of 3. So as you can see with the ovals that are here, our window duration. So when we're computing our values here, we're having to take into account the window for 3 here. For computing window time 3, we're computing the stuff that's in the in this window. So our window refers to the number of prior batches that are going to be used in order to do the computation. We might be looking at minute by minute changes in some pricing. So we're going to be looking at trades on this minute versus the minute before versus the minute before, and now we're going to see some kind of trending taking place. The duration says how long, at how many, after how many batches do I actually produce my result. So since this has a duration of 2, I've got something that's produced here from previous computation, and then I wait 1, 2, and I produce my operation. But because of the window, I'm actually looking back over 3, but now I again wait, 1, 2. There's my duration, produce the new one, but now I'm overlapping here. Because we have a different sized window and duration, this particular guy, time 3, is being used in both this window computation and in this window computation. So there is an overlap over there, which is fairly common in working with this kind of streaming data. Okay. Okay, so the batch interval controls how that's the original. So the batch interval is the original parameter which controls over what time period the events are batched, and clearly the larger the batch interval, the higher the latency of the application, because you've just got to wait longer to get the batches through the system, plus the batches will be a bit bigger. Window intervals, again, specifies the ordering of the batches because we're interested in trending over time. So the sliding interval is how often window calculations are done. We just saw that earlier. The default is the batch interval, but it does allow sampling of the data to see what's going on. So best practices. Spark streaming runs in 24/7 mode, even if a worker or drivers fail. The checkpoint periodically, manage memory wisely. That seems to be a very generic sort of best practice. Replicating data. Excuse me, my headphones just set off. Spark replicates input data in memory across 2 nodes, kind of a fairly standard, data replication redundancy model. And again, this is what we were looking at earlier as memory 2. So we have a single worker failure, and the thing about it is that it's only the raw input data that's replicated in memory, not the transformed data, because again, rebuilding the data is something that you can do if you've got the raw input data. So a Spark memory manager called block memory keeps the replicated data as long as it's required. And at some point, you're going to be able to release that data. The best practice is checkpointing. So we're saving the RDD state to a reliable file system. So the file systems that are mentioned there are the HDFS and S3, and of course, we don't even need to go into describe any of that. That's all pretty common stuff. So why do we do it? Is that we could have very large lineages. So this dependency chain can keep growing. So what we want to do is avoid risking it all in cluttering up memory, and just get it out to checkpoint at various times, put it into the file system. If there is some kind of failure in redundancy, at least we can recover to the checkpoint. So it's just basically ensuring that we can maintain consistency. One of the problems that we often ran into when doing various kinds of projects working with real-time streaming data is that we often would, if we did not have a way to, if our processing went down and we couldn't recover and move back to a checkpoint, we often would get skewed results for various kinds of analyses, and it would really have a negative effect. So again, the idea is to try to maintain the consistency of the lineage because certain critical calculations may be dependent on that. Checkpoint intervals are typically 5 to 10 times the sliding interval. Again, that's going to give you your trade-off on time and space. Again, and you can checkpoint it using the checkpoint command into the system. Memory tuning. Amount of memory used consideration, how much memory is used by the objects, some overhead and garbage collection, and then one of the things to recommend here is to take a look at what each RDD is taking in storage by the web UI. One of the things to keep in mind here is that, again, depending on the kind of streaming data we're working with, we may get a variation in size. So it's probably useful to look at kind of RDDs that are generated at various different kinds of operational, different kind of operational windows when your performance is going up and down. Get an idea of how big versus how small these things can be. Often working with some kind of average is useful then. How to reduce memory consumption, be mindful of caching, and then the idea is also tune the garbage collection. We'll be getting into the more of those memory issues after we finish up this section. So minimizing garbage collection, don't give enough memory. What happens is that the thresholds for garbage collection are going to be triggered consistently if you don't have enough memory and you constantly have to be garbage collecting memory, and try not to use too many temporary variables. Whoa, sorry about that. There we go. Programming. So this is going to be basically looking at it from a programmer's perspective. So we'll quickly go over a couple of this, and it's just a matter of setting up the dependencies. So for SBT, for example, where we just had the Spark streaming dependencies. If we're being Java, we had the Maven dependencies, and let me see. Here we go. And so we have an example of a typical program. Oh yes, this is good. So let's just find Scala lines. We've got some streaming context where Scala lines are coming in. We've got a window of 10 seconds there, batch window. We create a variable from the text stream, and then what we do is we wind up with the lines, and then we get our excuse me for a second, and then we get the lines with Scala. Is we apply filter to our lines. So whatever lines are in that set, now we get a new RDD that comes out, and we can print that out. And then once we've got that defined as the main, we can start our SEC, and then we can start that program, and then we just now await termination. All right, so because we're using RDDs and the standard Spark core, the actual code is not looking significantly different in structure and form than what we were looking at earlier. So Spark is in its own packages. So again, we're not going to go too deep into that. Everybody knows how to import packages. Initializing context, and so that's our streaming context is the entry point, just like every other context. So what we can do is set up a standard configuration object, but we now are also adding the batch duration into there as well. So in our example, we're creating a new Spark configuration object. We're setting our master to be local 2. To use the 2 cores, we're setting the app name to be my app, and we're creating a batch duration of 1. And now we create a new streaming context with our configuration and a batch duration, and we're set to go. If we're getting a text stream, we can use a socket text stream receiver, which is specifying on what port we're actually getting our stream from, and we're filtering through from that. We're filtering through that port. So the let's go back over here. Starting the streaming starts the computation, and stops the computation manually. Await termination, waits for the computation to start. We can basically run processing until termination. Again, running it all. You can again submit this the same way we were submitting batch jobs before, and emulating some kind of. No, just hold on here for 1 second. My mic cord keeps getting tangled. Okay, there we go. So apologies. So again, we can use a utility across the network to emulate a data source. And when we look at the results, so the over here there's doing a netcat, and so we waited, typed some more, so that we're getting kind of a lumpy stream of data, so to speak, and the results of typing and then typing in a little bit more give us some processing times. So the output came in several batches. So we see several batches being printed out. So there's the sort of I guess kind of a really simplistic demo of the processing in real time. So the idea here is that you're we're basically batching it into streams. So lines from 0 to 1 are coming in, and they're being filtered into the data set there, which is what we were just looking at earlier. And that kind of gets us to this lab. So do you guys want to jump in and play around with some streaming in the lab here? Take a few minutes to do a bit of experimenting.
Not really, I guess.
Pardon?
Not really.
Okay, is that the general consensus?
Yes.
Okay.
I do have a question though.
Yes.
I agree. So like this program is so simple, it's not really that enlightening.
Yeah.
But I am interested in Spark streaming with Kafka. So two options are at least the delivery guarantees. So the two options are at least once and exactly once. What is required for exactly once again? I did not quite get that. Because that's the most difficult one, right? I mean,
yeah.
At least once is easy. At most once is easy. Exactly once is difficult. So are there any special things that we need to do to get exactly once?
Well, remember if you're okay, so if you're doing at least once, then okay, hold on, I have to get it right in my head too. If you're doing at most once, you want to avoid multiple processings. You want to make sure that you're keeping track of it. If you want to do at least once, you have to have the resilient buffer. So what you need, one's got state and one's got buffer. So really, the exactly once is a combination of the two. So with the overhead that you need for the at least once and the exactly once. So it's kind of at least once plus at most once in whatever sort of overhead you had for each of those. You now have both of those in the exactly once. Okay, did that make sense?
No, I'm familiar with the concept. I am interested in what is required to accomplish exactly once. Because, well, we're already using Kafka in a lot of places. We're even using it to do some of our processing, but we're not using streaming, Spark processing, but we're not using streaming. What we're doing is manually constructing a consumer and looking at Kafka messages, but those Kafka messages are just notifications about new batches to be processed. So imagine we get a 100 megabyte file, we get a Kafka event that is being processed. So that's what we're doing right now. The thing is, we need well, at least once, but ideally exactly once delivery for these types of messages. And if I wanted to turn this into Kafka streaming somehow, details not important, I am sort of interested in getting exactly once. And the example that we got didn't work with Kafka at all. It worked with simple network streaming. That's fine for illustration purposes. What I'm interested in is if there are some special, I don't know, configuration parameters or some special something that I need to do to get exactly once in combination with Kafka with Spark streaming. Because Kafka natively, as far as I know, does at least once. The recent versions claim to do exactly once. But given that I know how Kafka works, that's a difficult feat. So I'm wondering if Spark needs any additional configuration, does any additional guarantees? That's my question.
Okay, that's a good question, and I don't have an answer off the top of my head in terms of the configuration. But if I have a moment, I think I know where to look, and I'll see if I can find you an answer, okay?
That would be perfect, thanks.
Yeah, no guarantees on that because, you know, I'm not always the smartest guy in the room, but I try to know where the smartest guys in the room put their stuff. Okay? All right. Any other questions? Okay. Structured streaming. Okay. Structured streaming. Okay, guys, I'm going to hold here for like 2 minutes. I have a. It's really cold here, but there's an issue. I think that the wind may have blown something. So I'm just going to go into the other room for a moment. I'll be right back. It'll be just about 2 minutes. So just please hold on for a second. I just got to check this out.
By the way, do we want to continue on streaming, guys?
I would be interested.
Yeah, let's finish the structure stream.
There's Kafka in there. At the
exactly. Let's go to down to this.
Okay.
I mean, it's fast-paced right now.
So. Yeah, exactly. It's quite fast and still informative and still pretty useful. Like there's still some pretty useful concepts. So it would be a shame to miss this. It's my opinion. I don't know what you guys think, but yeah, if it goes that fast, we can afford, I think, to continue.
Built on top of data frames, again, an unbounded table. This time, just like we were using RDDs before in the previous section, processing the data coming in as RDDs. Now we're processing it in a way that allows the APIs for data frames. And then also, of course, that can feed into with Optimizer and exactly once guarantee with checkpointing and write-ahead logs. This is, it says 2.2, so it's probably there right now in 2.4. So in this case, the data is being treated as an unbounded table. New streaming data gets appended to the table. This actually might be an interesting solution to a potential solution here to that exactly once. Thinking about it. So we're adding stuff to the end of the table okay, there we go. So data stream, unbounded table, and now we can do this kind of I'm trying to figure out what it says under there. A trigger. Okay, I don't know, but we're able to actually run queries at various time intervals with a complete output mode. So we've got the data, but by actually combining the data, prior data, plus the current live data, so Lambda kind of architecture. So that would be an interesting approach. And I'm just trying to think if even that alone gives a programming solution to an exactly once kind of situation, although there should be an easier way to do it. We can take it from files, sockets, Kafka, and rate source, which is our testing platform. Sinks, file, memory, console, in other words, places we can dump it for each Kafka. There are the, hold on. So the various options here are writing to the various sinks, using Kafka, using it, for example, for instance, the Parquet files, writing it to a directory, writing it to a file. Second one is Kafka, writing it to Kafka server. The second one's writing, the third one's the console, and the fourth one is doing an in-memory sort of operation. The structured streaming output is complete, append, and update. So this is kind of, again, maps up to our Lambda model. Complete, so we're looking at the entire updated table, so that's the entire accumulation. Append, only the rows that were appended in the result table. It's only on queries where existing rows are not expected to change, so it's immutable. And then an update was we may have to go and go back and incorporate updated rows. So we're also looking at the updated rows that have been changed as a result of the recent data. Example is there's our Scala example, structured streaming. We create a Spark session, then we create a Spark read stream from a socket, a local host, and then we load it. Then we print the schema that we're using, or the print schema, and then we're querying or running the query on the we're creating the query from the write stream using an append mode, which is the one that we were looking at over here. So reading data from a socket, we only have one attribute, which is value. So each line represents a value, and we just wind up simply printing out the values, and await termination just ensures it keeps running. So there's the simple example. And so I'm assuming too that there is no particular interest in running a structured streaming app. Anybody interested in that? I feel like I'm at an auction.
Not this one, but I looked ahead and there's a Kafka example, and I would be interested in that one.
Okay, so let's take a look at that one then. Okay, so this is the okay, continuous streaming. Okay, so this is the low latency end-to-end, supports at least once guarantee. This looks like this has been updated recently, and so at the least once guarantee, I'm not seeing anything. Well, anyway, at most once. I don't know. I'm just trying to solve the problem in my head. Supported sources, syncs, both Kafka on both sides, memory and console, basically for debugging. So here's the example. We're reading the stream from Kafka. We're subscribing to topic 1, we're loading it, and then we're having an expression here, cast valid, converting our data into the appropriate formats we want. We're writing it to Kafka, and we're getting a continuous trigger 1 second. So they continue. So we're going to check up on our query every second to see what the results on that are. Okay, so this is Kafka, and this is the one of those lovely LinkedIn issuances. So we basically have a Kafka cluster, which is selecting stuff from a number of producers and then forwarding it to a number of consumers. So the producers are storing all of this. So you guys know Kafka, so you're probably familiar with all of this stuff. So this is just a little bit of fluff. So the producers write data to brokers, and then consumers read data from brokers. So it's a lovely distributed fault-tolerant subscription system with data stored in topics. So it works out very nicely, and does the appropriate kind of mapping of inputs into the appropriate topics, and then allows for selection of outputs. So. 2 ways of receiving data from Kafka was the direct approach or structured streaming. So since receiver approach seems to be obsolete, direct approach achieves 0 data loss, and structured streaming is the new high-level approach. And I'm really not up on that one. So here's our direct example. Let me see, that's the one that we want to look at. There's the direct, in which we're setting up our Kafka parameters, our topics, and then creating the stream subscribing to the topics, and then we're printing out the stream as it comes in. So we're extracting the values and starting the process. Similarly here, we're now using the API, and of course the difference here is we're using the select expression. So we're a key is string, value is string, integer long. So we're giving it some values, and then creating our schema out of that. And then we run the query on the topic from Kafka, or we run from the query. Sorry, we're running the query from the constructing the query, and then running it and awaiting termination. Okay, so there's the approach. So I think this is the one you were looking at. You wanted to think was interesting.
Quick question. The lab for the structured streaming requires Kafka, right, to be installed and up and running, which is in another lab, which takes up to 40 minutes.
Sorry, I was muted there. Do you think it would actually take 40 minutes though?
No, not just the streaming lab, but to do the streaming lab, we need Kafka.
No, that's what I'm saying. And you're saying the lab says it would take up to 40 minutes to install Kafka. Do you really think it would?
No, but that's
what it says.
Yeah, exactly. It says 30 to 40 minutes to set up Kafka.
Yeah, so, but you guys have been doing 20, like the ones where it says 20 to 30 minutes, you've been doing them in 10 to 12 minutes, So I'm going to suggest if you want to, why don't you give that a try? And if it looks like it is going to take long, then let me know. But I'm just okay. Thinking the option might be is that that might be a really wild overestimate based for people who are still trying to figure out what a command line is. Okay.
Okay, great. We're going to give it a try. Thanks.
Yeah, give it a try and let me know how it goes. Okay.
Okay.
Just checking in to see how you guys are coming along.
I think from Berlin, everyone is more or less done.
Okay.
So, yeah, I think we can carry on. I don't know the other guys if they're good as well.
Okay. So, did you
let's go.
Yeah. Okay. So, there was one follow-up, which I guess builds on this one. Let me hold on. Where am I here? Everything is cold today. Hold on. Let me close this off. And there we go. Okay. So, I think you guys just did this one, Kafka direct streaming, right? Okay, so this is going to be a quick overview, so we'll keep things moving quickly. Okay, so transformations, again, basically the transformations as RDTs also apply to streams, to the D streams. Stateless transformation, again, that's going to be a very simple example. So that's no conceptual difference here. And the interesting thing we can do this, of course, is we can combine multiple streams using joins and other sorts of other operations and union. So we can have the similar kinds of operations that we're used to having with the other approaches, or with the other kinds of sourced RDDs. And so here's a joining 2D streams produced by MapReduce. So the map transforms the IP to a pair with the IP address and content size, reduced by key, computes the total bytes, and then we join the request count per IP. So the IP stream, we're accessing the access logs of the stream. We're doing a map, converting an entry to the entry with the IP address and the content size. We're creating the bytes, the number of bytes that we've got, reducing it by key, which is what we're talking about there, number 2, and then we're able to actually join the 2 streams and create a new D stream. So similar sorts of operations as with the normal RDDs. So the stateful transformation basically is to take a window of data, and so the duration, slide duration, as before, both have to be multiples of the batch, and then doing a word count in a window in a sliding window. So the okay, so and then we have a map with state, which is maintains the state information. That's one of the models we looked at. Map with state API. We can build a stateful stream processing pipeline with the, what are called cumulative calculations. So we have an operator signature map with state, and it produces the state spec, and has the map with state D stream with the appropriate values. So the map with state creates a map with state D stream, and the state spec describes the spec of the map with state and how the state should work and maintain the state. So let me see, go on here. So there's the word count with non-windowing. That was the example we looked before. Now with a windowed version, takes through the in the streaming context. Here's the windowing. Create a pair window, and then we do a word count on the windows, reducing by key. So basically, the idea is that we're able to have the operations work on the stateful windowing version of working with the streaming input data. Okay, so let me see. I mentioned that A persists, so here over 3, because our window duration is 3, so we're continuing to see the A count over the window duration, and of course it vanishes in the last one here. So there's our stream, and our windows are being updated accordingly. Reduce by key and window allows us to reduce by key, but within a particular windowing context. So it does get the same result as what was looked at before, but now it's utilizing this particular operation. Both operations utilize the full window of data in order to do that. Count by window, number of counts. So we're seeing basically operations count by value and window. So we're extending a lot of the basic operations that already exist and are familiar in the core SQL, sorry, core Spark into a windowing environment. So we're just adding this other notion of performing these kind of progressively on the windows as they're coming through. The streaming listener interface is able to listen to the ongoing calculation and respond to the state of the receiver. Then we can listen to the so we've listener attach that to a streaming context. Output operations, again, fairly straightforward. Printing, a num prints a first number of elements from a batch. Print alone takes 10. Saving to a directory, save as a Hadoop file. For each RDD, apply a function. so we can apply functions in our batch mode. I think we've gone all of this input sources. We've done that, and if anybody wants, it's time for a break. But if you want to do this before the break, or you want to do this after the break, or skip this one completely, it's up to you. Consensus?
I don't know, like everyone seems to be pretty skeptical about this one, though.
Okay.
At least I haven't seen that much smile in the guys' faces. No.
Okay. Well,
let's just keep it then.
Yeah.
Where do you think Robert and Mike and Jarl?
Well, I'm looking for UDFs.
Yeah, I guess everyone is kind of like waiting for this though.
Yeah, I haven't been able to find a whole lot of stuff on UDFs, to tell you the truth. There's not an awful lot in that slide, and I was pretty disappointed. So, I mean, we can take a quick look at that. Oops, it's no longer there. All right, I just put it somewhere else then. UDFs. So, it looks like when this came out, it was not a particularly, whoever was working on this, I guess, didn't really finish it off. So in terms of a UDF here, we're using the standard idea, and there's a small reference to it also in the documentation. It's transforming values to columns to produce a corresponding output value, row value. It gives the standard use cases, which I'm assuming you're probably going to be familiar with. And in the Spark UDF, it basically create a UDF and then register it, so it can be used in the code. And that's about all that is in here. I was going to go and try and prepare some material if I had time on UDFs in general, but I couldn't come up with, I didn't have enough time to come up with something else. So one caveat I do have on here is that the UDFs generally tend to not be null aware. So anything where there's nulls, we often get into difficult situations. And I'll reference over to the documentation on that one. But the Python is here, so this seems to be focused on Python as well. So. Unfortunately, I didn't know that there wasn't that much in there, because I hadn't actually checked the slide out until yesterday. But were there any specific questions about the UDFs that you did have?
Maybe but it was maybe more about an introduction and
okay.
Hands-on as well, because
I was looking. I was looking for try to find a good quick hands-on we could do, but I think what I do have is at least what I was able to pull up a little bit was okay. So I did manage to find one interesting reference here on user-defined functions in it looks like Jace Kalakowski's reference, which is being my kind of go-to reference here. So the idea behind a UDF is to define column-based functions for transforming data sets. So recommendation here is important. It says use higher level standard functions with dataset operators before reverting to developing user-defined functions, since they are a black box for Spark and it cannot even try to optimize them. And that's one of the points that did come out quickly. Is that once you, it was the same problem we had with RDDs, is that once you kind of insert a UDF in there, you have something that is just basically an unknown quantity in terms of all of the underlying mechanisms of Spark. So the recommendation at the top is, you know, use them if you have to, but maybe not a particularly good idea. If you're really concerned about various kinds of optimization. The comment there is so this is the comment here is I'll kind of cover UDFs for a bit. So there wasn't anything in the material, as you saw. So we'll kind of go over this, and we'll also look at the sort of the two caveats that go along with using UDFs. So the standard approach to a UDF is that we're basically, and this is the example that's being used here, which is kind of like a standard example, is I have this lovely little data set, which is 2 rows consisting, each row is a string hello world, and I'm converting that into so I've got this lovely little data set that works that way. And I start with all my UDFs by designing first a function that performs the appropriate operation, and we go through the due diligence of testing and making sure our function works, so we're not going to break our Spark when we insert it there. And once we've got our function well defined, in this particular case, it's going to operate on all of the rows. In this particular case, all of the columns only got 1 column, so it's going to take that notion. I'll show you another example I pulled up from Medium as well. But now that we've got that function defined, we want to make it available to Spark, so we wrap it into a UDF wrapper, which is exactly what's going on here. So now we've got our upper UDF. So now it's in a wrapper that can be used. And the standard use of what we normally would do is we're often just computing some value across the row, and then appending that computed value to our row. So here we've got a data set with column upper, and then what we do is so we're adding a column called upper, and we are uppercasing the column text in order to do that. So we've specified what column we're passing here, and of course our result comes out appropriately. We can register our UDFs. So if we take a look at in the catalog, you've got both the function and the UDF, but you also have sort of multiple ways to actually define UDFs. You know, they still wind up getting the same sort of operation. So it says you could have defined it this way, or you can define it this way. So there's multiple ways to actually have done this. So the idea now, I'm going over jump over to here. And this is wow, this is really big. I'm going to scale this down a little bit so it's easier to see. There we go. And again, this is the just to give you a different example. This is the idea here. We've got this lovely data set of people. And we have got a data field that's all over one field is all over the map in terms of entries. We want to normalize that. So this is a nice little use case. So we take somewhat unrealistically all possible spellings of USA. And by the way, I was one of my little consulting contracts was to work on a database of treaty actions for the Canadian Department of External Affairs, in which I looked at all the different ways that people had been spelling these countries, and I came across things like the Untitled States of America, the Equatorial Republic of Finland, which I thought was really interesting, and also the People's Republic of Wisconsin. So there's all kinds of really interesting things. But one of the things I was doing was actually doing this kind of normalization. So what we can do is define our function, which goes and basically returns some kind of the normalized version of all of those possible inputs. It's registered, so registering the UDF as possible. And now what we want to do is when we actually apply our UDF, we wind up with this normalized country column. And this part is going to be fairly important because we want to make sure that we do have a value that comes off here or things might break. In this particular case, we have an unidentified input and we're putting some kind of unknown value in there. And just like we said before, there's multiple ways to actually register the UDFs. So there's multiple syntaxes and multiple approaches. Now, and again, you can list all the UDFs using the show user functions, and you can get the results of the, here we go, normalized country, clean country. So you can find the list of the UDF that way. Here are the two caveats. Of course, and we can also, number one is that because we've introduced a black box, it says when we use UDFs, we end up losing all the optimization Spark does on our data frame and data set. I'm not sure you lose it all, but I do know that I think instead it would probably be better to say that what it does is it blocks certain kinds of optimizations. So, for example, it certainly wouldn't block a projection optimization. I don't think so. And so they have an example here of going through here. This is going to interfere with one of the filters. So one of the steps in the optimization. So one of the things to keep in mind here is that there may be an alternate way to do this instead of using a user-defined function. So depending on what kind of data you're using, there might be some kind of alternate way to actually approach this. It's going to depend, of course, on the structure of the data and what you want things to do as well. The other caveat is that it doesn't handle nulls really well, so that you have the example that we've got here is this camel casing, which is going to go and do the camel casing of a text, and we're going to error out here because we're going to get this error, fail to execute user-defined function, and so this is why we always want to have some kind of output that in the case that there is a potential for a null being returned, or some kind of null case, we have some kind of data similar or data isomorphic return value that we can look at instead of doing something with null. Okay, so there's the idea behind that. I had another thing here. So the recommendation here is that they're fairly easy to use. Basically, again, you're taking some column or combination of columns, performing an operation on it, and then appending that as a column to the existing data. But the caveats here. Now, like I said, I'm not sure exactly how much of the optimization is going to get disrupted, but there seems to be kind of like a devil's choice here between a rock and a hard place in terms of you can't have both. So the example here that Klaskowski also points out is again, we're getting a problem with the optimization once we introduce the UDF. So he goes through a fairly example here, where a good example to show where the optimization is going to have a bit more of an issue. So and let me see, this is in this particular case, it's going to also interfere with, there's also problems involved with certain other kinds of structured data. So there is now when you guys are using UDFs, is this something you use a lot?
Yes, but we are not filtering, of course.
Pardon?
We're doing lots of mappings. Because that's super ugly if you have to do it in plain Spark.
Yeah, like basically for some like data that we are processing, we basically get sort of like not ideas, but abbreviation of string, or so for example, for some status like A means active, P means paused, and stuff like that.
Yeah.
And we have to denormalize these, and then well, of course we can use another data frame, do a join, and basically sort out the values, but that would forces us to have a dependency to process these data. Yeah. Whereas for small mapping, like for example, this status is a good example, like AP, D means disable, and so on. We basically have like an enum, and the UDF uses the enum basically to just unwrap the value and replace the A with active, D with disabled, and P with paused, for example.
Yeah.
And stuff like that. And we couldn't find a cleaner way or more programmatic way to do it than using these, because of course you can use Spark SQL, write a query, but that's where we came from when we moved some of our Ruby components. So we were like, well, that's not very elegant. And the UDF is basically just a function that you register, where the logic is much neat and easy to exchange. So that's what we use. And so far we've been using it quite a lot. Like another good example, for example, is you receive a country code. Yeah, usually you receive a 2-letter country code, but sometimes you don't know, you can receive garbage. That happens to us not long ago. So you have to validate that first the country code is part of this ISO 396 specification. It exists. And for example, for like Great Britain, because this like Brits, they never do like stuff like everyone. They have UK and GB. Which one do you use? Like you have to normalize this kind of little stuff, and that also comes very handy to handle such a scenario.
Yeah. Okay. I'm again, one of the things to remember about this is that the Spark continues to be able to, adding all these features on an ongoing basis. So I would say that if you have not noticed a disruption on your optimizations, then it may not be as big an issue with that. But the only thing is that it's very easy to use. It is an elegant solution from a programming API point of view, and there is something kind of unelegant about actually doing a join, because again, when you're processing lots of data, you want to try maybe to avoid all that kind of overhead, but you might want to try just on a sample set, run an optimization without using a UDF and running an optimization with the UDF, and see if you get similar kinds of results. And then decide, if there is a performance hit, whether it's an acceptable performance hit in terms of the ease of actually being able to process the data from a interface perspective or not. like there's all these dire warnings about, oh no, you know, if you use it, all your optimizations will be lost. And I'm a bit skeptical of that. That's all I'm saying, is that you know, there may not be an issue on that. So, or it's big an issue because that CBO is continuing to improve all of the time. So, you know, that may have been an issue, you know, with 2.2, but maybe by 2.4, you know, things have kind of resolved themselves to the point where you kind of work around that. So I don't know. It's probably just something to benchmark and see how it works.
Yeah, I mean, also on one hand, I can understand why the Spark community and developers encourage people not to use them, because it defeats the purpose of having a transformation built into Spark. So if everyone starts to use their own transformation, why just putting effort into having these sort of like libraries of transformation that they already provide? Yeah. On the other hand, it's also very hard, like for us, to evaluate the performance cost. Because, for example, when we do even integration tests, we have a very low sample of data, and it's mostly run on a single machine that is at the moment used only for running tests. So once the Spark context is started, it's a matter of sometimes of a few milliseconds, sometimes maybe half a second, but it can also be due to the laptop being like running on the battery, or we don't know. So to evaluate this kind of like edge case would be basically that we would have to run extensive testing on very large amount of sample of data, and so far we never basically did that. So that's also one of the kind of questions, like up to what points we can keep like UDF, up to which like is there a rule of thumb about the amount of data, about the type of transformation where UDF does not make sense anymore and we should write SQL, Spark SQL, or I don't know, like this kind of stuff. If you have any experience or advices, I mean,
the only thing I can say is that okay, so first of all, on the testing issue, one of the problems with the testing issue is that small discrepancies in the sample size with and without may not be detectable at the test level, but become significant when you scale up the amount of data to significant volumes. That's one of the challenges we always have. So one of the things is that if it's possible at some point just to do one stress test, you know, and satisfy yourselves. The second thing is that you know, as to there being a point at which that using a UDF is going to start to, in terms of data, in which the the UDF is going to start to have a negative effect. I wouldn't honestly know, because again, the way that the optimizer is being continually updated, and the other factors and the other variables that might be in place are, I think at this point is kind of an open question. So, I mean, does it matter about, you know, the kind of the actual complexity of the UDF, or does it matter about, you know, the size of the actual tables? Are there some other issues that are involved? And at this point, I don't know if anybody actually has any guidelines on this, because I don't know if anybody's actually explored that particular question, although it is a question that probably needs to be explored. Okay, does that help? You're kind of on the cutting edge there in a certain sense.
I have a question probably more to Gregory. So if there is a possibility to, if let's say you want to translate one column according to the map to a different value, why do you want to consider joining a table actually? So what is the actual reason for that? I mean, if we consider the performance hit, then probably it's not an issue, because as far as I am hearing, this user-defined function can cure the performance hit as well. So what is your actual concern about joining tables?
The problem is like the joining tables doesn't cover all the use case, all the edge case that we have. So imagine that if you want to join on the, so you want to join basically based on the input data. The problem is like to join on the input data, they have to be normalized and you have to know what you get. Yeah. For some type of data, we simply cannot say for sure that we will always receive data that will be within the data frame we will join on. For example, like recently we had to tackle a piece of software, so tracking, import some tracking data. And the tracking data basically had this country column. The country is supposed to be a number, but sometimes it's a string, which is garbage data. And the UDF basically can handle that because you can specify more or less what you want for like a generic scenario. Whereas if you would join, you would have to basically, on the data frame, you would have to basically think ahead of this edge case, and every time you would miss something, you would add it. With the UDF gives us this possibility to kind of basically skip the actual execution of what is within the UDF, because it's very dumb. But UDF basically takes a column, extract the value, and apply a transformation on top of it if it can. Assuming you have null like NULL, your UDF basically can be kind of skipped at that moment if you want to. For example, when you would do a join, you have the possibility to keep the null or remove them. But what if you want to treat the null as a non-valid value in this kind of case? You have to handle it like specifically. And so replace null by whatever kind of like an empty string or whatever. And all of these scenarios, we kind of run into them, and that was the best option to do that. So I don't think we ever kind of considered that we could join the data even once because we basically took all queries and we translated it into kind of Spark processing. And whenever we arrive in this query where you might know where there is this case and if P replaced with that, blah, blah, it was already in the query itself hard-coded. So we just extracted the logic, put it into UDF. So we never really thought about getting this data, this value from somewhere else.
But is there a kind of concept of database constraints or any other kind of constraints on the data so that you can apply a join, and then if you see that if it doesn't result in whatever you want, then the constraint is just...
We have, it's not really what we have, but we have a similarly kind of constraint processing, but that's only for the data warehouse, which is basically the latest step. But beforehand, we do other transformations, and for this, usually this data is not meant to be queried. It's just meant to produce a result. So the idea is to act on the garbage data as soon as possible, so we can remove this constraint check later down, because otherwise we will have to reprocess everything. So, but assuming that all the data that comes in will go directly to our data warehouse after a single component, we could run this kind of like constraint processor on the data that's produced, or the moment we do the join, and of course discard some of the stuff. But not all the data also require that amount of like granularity check. Mm-hmm. So it's a trade-off between consistency and availability at that moment. But in theory, that could be possible.
It may be worth exploring both options and looking for them in terms of what gives you a performance optimal solution.
I mean, yeah, because like at the end of the day, what you can also do is just to create, because these value that we use mostly for UDF, you can basically create data frame and broadcast them. And since the component is kind of running forever, it will stay in memory. So you will basically gain from having them broadcasted all the time. Mm-hmm. Okay. But on the long-term scenario, is it worth broadcasting a data frame with 4 values or just running the UDF? I don't really know. I mean, I don't even know if this UDF computation isn't like kept somewhere in the JVM and reused, because it might be because we use, for example, enum, which is a singleton, which basically stays in the JVM. So maybe every time you access, it's not that much. So the UDF is just a reference to a transformation, and that basically pings the singleton. So it's not also much memories. I have no clue about that. I would love to run like
stuff,
but I have no time.
Okay, I think you're accurate in terms of actually using the UDF is not increasing significantly. Massive overheads, incurring overheads. It's that one caveat in terms of how it affects the optimization. That's really the one issue that needs to be resolved in order to make that decision as to whether to use it or not. Because if it has no impact on performance, then it seems to be a clean and elegant solution. But if it has an impact on performance, then and you're only going to figure that out by doing some benchmarking. Then you're going to want to look at an alternative solution and see if that in fact does give you a performance. But as you've already indicated, with testing on small samples of data, the difference between the two may not be big enough to be actually noticeably at a significant level and may not be representative of what you see when you scale up. So you may need to actually run the test in a controlled environment with a fairly significant amount of data just to see what happens. And the question may just resolve itself at that particular point. That makes sense?
Yes.
Yeah. Okay, so that's our UDFs, and I want to get into the other thing we want to mention today. There's two.
I'd like to ask about UDFs.
Pardon?
One last question. I'd like to verify my impression about UDFs.
I'm sorry?
From what I saw, it feels like UDFs are basically a way to organize your code, and you can achieve same results doing basically transformations or some other operations, and you can avoid them at all. It may be ugly, it may be repetitive, but it is possible.
Yeah, I've seen one of the things that was occurring to me as you were talking is that one of the constraints you're often looking at is, when you get this column coming in that needs to be normalized, the question is it necessary to always maintain the original data, or can the original data be overwritten in order to clean it up? Those are the other kinds of constraints that make the decision here. So there are multiple tools here you can use to sort of solve that problem. And then a lot of those use cases are going to depend on kind of those additional constraints like the one I just mentioned that may be imposed by the nature of the problem. So I don't know if that kind of answers your question a bit, but.
So is the use case which is solvable only using UDFs?
I'm trying to think of what that might be solvable. Is the only one that I can come up with is where you have a restriction that you're working with data of record, and you are not allowed to alter the data of record anyway, but you have to append more information to the data of record, and it may be something that you can't run as a. That there may be another reason why you can't develop some kind of alternate model, and you maybe even just time, or maybe even have to do some standard kinds of standardized queries or something. So you wind up seeing it as the only solution. So I think for most of the problems, there's generally going to be more than one solution. I'm trying to come up with a use case where UDF is the only solution, and I think I can't really think of anyone that just rules out every other possible solution, including pre-processing data and stuff like that.
Okay, thanks.
Yeah. I used to have a developer working on my team, and the whole team we'd be battling with these. We're doing research projects, and we'd be battling our heads on a problem, and he would stand up and he'd say, "Well, I guess there's no solution at all," and we'd say, "Agree," and he would say, "Except this one," and he'd always come up with a solution none of us had thought of. So that's why I'm reluctant to say that there is a case where there's the only solution, because there may be other ways to do it. Okay, so that's kind of that initially. I want to while we have some time here left, go into a little bit about tungsten. the Tungsten project had a lot of publicity, a lot of documents and everything initially in 2015 when it was first kicked off. And a lot of that stuff seems to have just been recycled a lot. And I've been trying to find a lot of updates on sort of what other interesting features are into Tungsten. And I'm seeing a couple of things here and there which are kind of minor tuning things. So I'm sure that there must be things going on in Tungsten, but they just do not at this point seem to be have been shared publicly, or at least shared in a place that's easy to find. But we will go through what Tungsten is here. Now, we have to remember is that there's two aspects to memory management in Spark. One is how we choose to allocate out memory, and how we manage the memory from a traditional memory management perspective, which is, for example, in Spark, you've got if you're working with a JVM stack, you've got a chunk of the JVM stack that is reserved for data, a chunk that's reserved for execution, and a chunk that's reserved, that's a spillover. And you get to allocate the two main chunks between execution and data based on a weighting that you give it. And I think, I can't remember, it's 0.7, I think, believe towards, anyway, we saw that formula earlier. And the problem a lot of and tuning that parameter is that if you can allocate more memory, for example, to execution, but if you're trying to put data into memory, you may wind up spilling the data onto the disk. And if you wind up giving too much to memory, too much to data, then you might wind up paging out your operation again, spilling it onto disk, and that's when you incur high levels of the only suggested recommendation for tuning those values is to use the Spark UI and look and see what sort of performance hits what performance measures the various kinds of balances or the various kinds of weightings give you, because a lot of the weighting that you're going to choose is going to depend on both the complexity of the operations that you're performing, as well as the amount of data that you've got, the amount of data you're broadcasting, and all the kinds of other chunks of stuff that you're going to be storing in memory. So you may want to have to tune that particular parameter up a little bit. Okay, but Tungsten, on the other hand, it says, okay, so you've got the memory all allocated. So here's the second part of the equation, which is how do we use that memory? And so this is where Tungsten starts to come into play here. I've got to find those little arrow buttons here. There we go. I think we can just do it this way. There we go. Hold on. I had it before. Okay. Oh, I'll just do it this way. I'm not a Windows person. Okay, so so that's about Databricks. Okay, so there are a couple of problems with traditional memory management, which is what Tungsten's about. This is the interesting. This was the motivating factor for Tungsten, was that the biggest bottleneck to performance was actually the CPU bounding. And I mentioned this the other day, is that one of the big bottlenecks was actually moving data from memory into the CPU, and moving data from disk into memory tends to be really useful, really accelerated with things like Parquet and ORC types of file formats, so you can create very efficient, compressed, serialized file formats that speed up that process. so we want to try to think about in tungsten. The approach was to say, well, can we do a similar kind of thing with memory? So in this particular case, the answer is that the other problem is that there's a lot more hardware processing, CPU power, memory that's been improved. So it's still the problem of the serialization and the kind of hashing stuff that's done to move stuff around in memory that really becomes part of the problem. So what tungsten does is operate at a couple of levels. It first of all takes direct control over the memory to work with memory in a far more effective manner, and then it also excuse me. It also is aware of where things are in memory, so that you can have more effect. So you can exploit the cache type memory, the different kinds of memories that are there, in addition to the regular memory, in order to stage the data so that it can be moved into the CPU more efficiently. And it also bypasses a lot of the translational sorts of issues by using the Genino compiler in order to be able to produce a code that operates directly on the binary data without having to do some kind of deserialization on it. So the problem, first of all, is the actual representation of Java memory, or Java, the actual Java representation of objects and memory. Java manages memory through the use of having everything be an object. And so we have the string ABCD, 4 bytes with UTF-8 encoding, seems really compact, but Java goes and puts an object header, it's a 12-byte object header, 20 bytes overhead because it stores it in a UTF-16 format. So now it's adding 2 bytes per character, and then it's adding various kinds of hash codes with another 8-byte hash code, and you've got a big chunk of memory being used to store that particular value. Not only that, extracting the value tends to be a little bit of a challenge, because now if you want to get the first entry of the string, you have to actually find it in this memory. And so that really works nicely when you're working in a nice program environment, but it takes a performance hit. And that's always been one of the criticisms of the way Java does, is it's safe, but it's slow. And garbage collection works on deciding where to clean up the garbage based on the residency length of the objects. So we have, as you can see, it's divided up into a fairly standard model with the Eden, which is, there's nothing there yet. Then we wind up with survivor spaces. Then things have been for a while, they get tenured, and then they get to move into permanent. And these are things which tend to have been around for a while and referenced a lot. So there's a number of algorithms that Java uses, the JVM uses in order to do this. And these are all predicated on the principle that we're running memory as an adjunct to primarily computational tasks. However, the big data workloads create objects that really don't fit into that paradigm of how we think about memory. And what we do is we, Tungsten takes advantage of the idea of being able to bypass this whole mechanism and use the unsafe memory. Now, the term unsafe here doesn't mean that the memory itself is unsafe. It just means that we're bypassing all of the sandbox checks and values that JVM imposes on memory management and managing it directly. So it's like using malloc in C, or actually working with the raw memory. We talk about off-heap memory. Off-heap memory is a memory that is not directly controlled by the JVM, and so therefore it's subject to things like garbage collection. On-heap memory is memory that is controlled by Java garbage collection, and it's still usable, but we can optimize various parameters to minimize the garbage collection and do other kinds of things to make it a little bit optimal. But the off-heap memory, the unsafe memory, is really where we get the best idea. Now, we also want to be able to try to avoid having Java actually do any kind of representation into memory, simply because it imposes an extra layer of structure. So we have got a triple here of 1, 2, 3 in Databricks, and what happens is each there's a number of layers. There's 5 objects, so each one of these objects winds up being into put into a Java type box, and that's put into an array box, and that's put inside a raw. So again, a row box. So we've got layers of depth that we have to go through to get the actual first value out, and these are all contributing to the high overhead of the access. So what Tungsten does is it goes and collapses all of this down into what's called an unsafe row format, which is broken down into a couple of standardized chunks. The first one is a null bit, which basically is set to track null values. The other thing is that there is a set of values with 8 bytes per field, which are the small values which are inlined. So every column in the fixed length region, every column appears in the fixed length values region, and it'll either fit in here fully, or it'll have an offset into this other chunk of memory, which is the variable length, to indicate where that actually is. So rows are always 8-byte word aligned. That allows for efficiencies in working with the data, because now we're aligned, word aligned, which of course allows us to move data around much faster. So we're going to lose a little bit of memory here and there, but it's absolutely insignificant compared to the efficiency we get in processing. So if you've done any C programming, this looks really familiar, because what we're doing is we're basically trying to maintain fixed lengths of our fixed fields in our row, or fixed lengths, so that we can do zero time access, or not zero time, constant time access, because we can just work with offsets into where things are. So the other thing too is that once we've pulled away all that structure that's imposed by the JVM when it stores things into memory, we can actually now access the underlying values directly, because we know where they are in memory in terms of their size and their offset. So so what we wind up doing is being able to say, okay, we want to get the value of column 2. What we know is that, first of all, okay, this is not null, so it's column 2. So we know that we can immediately go jump. So it's 8 bytes a field. So we jump. We do an offset into there, and then either if it's small enough, it's in line directly, we've got the value, or we do one more hop into the if it's a pointer, so we do one more hop into here. So we've got 2 very fast operations in order to retrieve that data, which is a orders of magnitude speed up over what was going on in the Java format. So here's an example of an unsafe row, taking that same representation. So it's not null. 1, 2, 3 can be streamlined directly, or inlined directly. So it's at that first field, it'll fit there, so it's inlined. The second one is is a string, so it's got a variable length. So it now is pointing to this chunk over here, so we can access that directly. And the second one is brick, so it's got a pointer now into here. It's giving us the length. So now we've got so this is giving us an offset, and one of the first things we look at is the extent from that offset. So now if we want to grab bricks off of this unsafe row, we'll say, okay, we know it's the third in, so we offset here to the second. We do an offset of +2 from the 0 position. And now we say, okay, now that's one hop. Second hop, it takes us to the start of the string, and now we can just read the next six fields, and we've got the value. Okay, so this is the idea of creating a much more efficient memory structure. Now, one of the reasons that we talked about in the first part of the class is what data sets do is data sets type things, type our data so that we can actually utilize this kind of efficiency. This is where we get that big efficiency, because if we've got an RDD which has type data in it, which we can infer lengths of things and we can infer how much room things are going to take up, then suddenly we're able to use tungsten to start optimizing the storage of that, as opposed to the older versions of the RDDs. So also, in order to find things into memory, things are offset into pages. So the off heap memory are just raw memory pointers, so that's incredibly efficient. And the on heap are addresses where we go to a base object and then use some kind of offset pairs, and able to move things very effectively in the on heap memory. There's a page offsets where when you want to look at an item, you know what page it's on, what data page it's on, and you also know how far into that page to jump. So again, this memory model has been around since the 1960s. It's basically the very high-speed memory model that's used in most of the systems that are out there. So here's a hash map. And the hash map has got a lot of overhead because there's multiple indirect references. So if you want to go and get the value of a particular key, you've got to get to the array, take the array into the key pointer value pair linked list, and then pull up the pointer to the key, check the key, pull up the value to the pointer. So there are also what we call poor memory locality, in which all of these different parts can be stored in random, not random, but in fragmented parts of memory. It's hard to estimate how big this thing is because it's got so much overhead and it's so diffuse. It also takes a little while to actually go and utilize this. And one of the interesting things, a couple people were talking about, they were programming in Go. Go uses does not use this kind of model. What Go does is Go actually uses an underlying hash table so that it actually goes and allocates chunks of contiguous memory, and does the same thing for arrays. It only allocates chunks of contiguous memory to avoid this kind of fragmentation issue, which is acceptable from a Java perspective, but not acceptable from our perspective. So in this case, what Tungsten does is it maintains pointers. It creates a memory page, and it loads the hash map into that memory page in a contiguous manner, so that it's got memory locality, and it's easy to scan. It's easy to find stuff. And we maintain or Tungsten maintains a table that allows it to go right into that location. Again, very high performance on Tungsten. Now, once that we've established that sort of structure in memory, it's now able to bypass a lot of the other overheads that actually cause slowdowns in memory accessing. So the expression logic evaluating on JVM, it's expensive. Remember, Java was designed to allow lots of programmer freedom and flexibility, but to do a lot of safety. So behind the scenes, there's things like virtual function calls, expression type branching, object creation, boxing. So you have to take a primitive and box it to store it, so you've got a lot of overhead stuff. So if you actually go and if you use the Java interpreter, you wind up with a significant performance there using doing select A plus A plus A. The query time is significantly high because of all of this overhead that's going on. If you write the bytecode by hand to bypass all of that, then you get a really significant performance if you want to access the bytes directly. And similarly, if you do a code generation something like Janino, you also able, now Janino doesn't compile the whole program, it just compiles bits, and it allows us to create code that we can operate on quite quickly. So the idea here is that if we want to do code generation, we also want to avoid this kind of bottleneck. So this was the introduction.
Can I ask a question?
Sure.
So it is my understanding that this code generation can only work as long as we use an API like SQL, for example. So where we just provide one expression, which is just text, and therefore Spark can parse and understand this expression and therefore compile it.
Yeah,
but it cannot work if, let's say, we compute this A plus A plus A as part of a Scala function, right? So Spark cannot look into a Scala function and recompile this, so understand and recompile this. Is this correct? Or
that's a good question. My understanding is that that's not a limitation, but that's just been an assumption that I've made. But I think what happens is if we look at these things, I think the way that it's structured, if we go back and look at this, at how the catalyst works, where again, we're also using Janino, excuse me, just for a second. Apologize for that. It's invoked in kind of the final stage of any kind of optimization. So I think what happens is that stuff has been generally migrated into a form that can be used in this optimization. So I don't know if in just kind of like a plain Scala environment, how things would actually work in terms of performance and improvement. But again, with Tungsten, I think that's what's happening is that the operation here is that it's working sort of below the level of Scala, so it probably doesn't matter where that code has come from, whether it's Java or Scala. I think by the time it gets to where we're actually doing the compilation, it's in a form that can be used. So I'm just kind of taking it on faith at this point that shouldn't be an issue. Is that what you were talking about, or did I miss the point of your question?
Yeah, exactly. So that's exactly the question. But yeah, so at this point it is still sort of unclear exactly what's happening under the hood. So yeah, I guess it's one of those cases where you just have to test it and see what happens.
Yeah, and I think the point is that it's really coming back to this issue that was on the previous slide here, I think, is that if we get to a point where we want to kind of write some code that's going to work directly with moving stuff in and out of memory, is that because of all of the overheads of the standard Java compiler, it creates all this crud and cruft And if we were to actually write the bytecode that just did the job without all of the extra Java sort of infrastructure, we would get a performance improvement. And my understanding has always been that basically what Janino does is sort of the same thing of the as with hand coding, because it doesn't compile a whole sort of Java function or anything like that. It just takes a chunk of code and just compiles that local chunk of code. So it can be a block or a couple of things. So it could be something, I don't even know what the smallest unit is that the Janino compiler compiles. I know it's been around for many, many years, but I think it can take little snippets of code that maybe come out of some of these processes like the CPO, and compile those directly without invoking all the rest of the overhead. Now, I do recall that the Janino compiler was actually originally intended to be compiled Java code to run in embedded systems, where you wanted to write basically take small snippets of Java code and write them right into the memory, so they could be executed without all of the Java overhead. So I think in this particular case, kind of come back to answer your question, is that we're basically instead of going through like 10 steps that the Java compiler would go through, we're basically ignoring the first 9 steps and just taking the 10th step, and generating just that local bytecode that's necessary to perform that operation. Does that make sense to you?
Yeah, it actually does. Thanks.
Okay, good. All right. So the example here that they give, and this is again, these slides are one of the guys who invented it, is here is the aggregation optimized. I was going to say aggregation optimization in data frames in Spark SQL. So we've got an input row, a grouping key, and we convert it to an unsafe row. We wind up doing this now. I'm not sure. Okay, so he went through a little example he had there of how this was done. So and it was just kind of a detailed integration, but a detailed explanation. But one of the things here that should stand out is that we're winding up with a number of excuse me, we're winding up with a number of these unsafe rows as we do this conversion. So an input row is projection, and then we do this conversion to the unsafe row. So we're actually translating a lot of this data into these highly effective memory optimization structures. It does a number of optimizations. So I believe Spark held until recently, it may still hold it, that sort record. I think there may have been another somebody else may have won it in 2019, but again, still it had the record. So the idea is that if you're going to sort, if you're going to do some kind of general sort in the naive layout or the conceptual layout, you've got a pointer to a record, but you have to access the sort key on the record in order to do the sort. And so you're always doing some kind of lookups, which are really unnecessary. So in order to cache this properly, the key prefix that's being sorted is moved into the pointer. So we got now this a hybrid object of the key prefix in the pointer. So now we can sort without ever having to actually look up the record. So this kind of pre-organizing the data so that it makes sort operations very efficient, it starts to become very effective, because of course we can just do this kind of cache-friendly organization once, and then utilize that optimization over and over again in the in the various operations that come along that follow. So the idea that we're working with here is that laying it out in memory produces significant performance benefits in that. So here's the the aggregation query. So data set size is roughly doubling here every time, and the runtime seconds. So using a standard, using just a standard JVM memory management model, the red line peaks out because that's basically where the whole thing crashed. Improving this with using the Genino type code generation or other similar code generation tools, we don't crash, but we do still get a crash eventually because we're running into problems with being overwhelmed by memory management. But it's happening considerably later than before, so that the code generation alone is producing significant performance. So if you now bring in Tungsten, and Tungsten's managing the on-heap memory, you wind up even getting a better performance, but you even can improve that by moving a lot of the data and using Tungsten off-heap performance. So the idea here is that each one of these elements of Tungsten, number one is the use of the code generation, gives you an important it gives you an improvement. The direct management of the Java heap memory and bypassing a lot of the Java cruft gives you a performance improvement because of the layout of the data. And the other one is the off heap, gives you even more performance because you're bypassing everything. So this is the approach here. Now, when they run this again in a similar kind of performance for an aggregate query, the performance are even more precise when you look at the average garbage collection time per nodes. So in other words, here, there's the runtime. Now we're looking at the garbage collection. Java JVM garbage collection just breaks down very, very quickly. The code generation does give you better performance until you hit kind of a tipping point because you've still got garbage collection issues. Although you minimize them to a certain point with the code generation. Tungsten on heap bypasses a lot of the garbage collection issues, but you still wind up with garbage collection. And of course, the off heap, because there's no garbage collection, shows just a minimal garbage collection increase. And that's how the performance improvements comes along. So that there was the roadmap for Project Tungsten. I'm assuming it's all been I'm assuming that it's all been implemented at this point. I've been trying to find the actual current internals descriptions of Tungsten, and I get a lot of nice comment about Tungstens and how wonderful Tungsten is, and the same ideas of off-heap memory, on-heap memory, you know, the same basic ideas, but you know, getting down to the real kind of stuff. We'll go back to Joe, to that internals book again and take a little look at that and see some of the options that we've got there. So the idea is that almost everybody at this point can utilize Spark. That's Spark 1.5, so we're not really 1.4, not too much interested in that. Okay, so that is what Tungsten does. So in terms of whether you can optimize what Tungsten does, generally the answer is no. Because it's already working at such a low level and using such low level optimizations that it's basically just using it is the optimization. One of the reasons why I'm saying you can't really, I don't think you can really improve on what Tungsten does is because I grew up, or not I grew up, but I started my programming back in the 70s, but when we got into the early 80s and we were working a lot with Unix systems and production systems, all of these techniques were actually used. to manage memory really efficiently, because remember, we had really, really slow memory and we had really, really slow processors. So these particular techniques that Tungsten is using have got a lineage that goes back to the 1970s at least, and even in the 1960s when we look at how these were hand-coded in Unix. So what's happened is we've had multiple generations of operating systems engineers and systems engineers who have optimized a lot of these kinds of techniques, and also these techniques have influenced how memory is actually built at a hardware level. So Tungsten is actually a very smart initiative by going back and utilizing techniques that are similar to the same techniques that have been used over decades to work with memory, but also are the techniques that have influenced how people design memory. So there's a little just kind of a caveat to throw in there as well. Okay, any questions or comments about what we've just been talking about here on Spark? Not Spark, in Tungsten. Okay. All right. So now let me see where we're going to head here. Tungsten execution back end. There we go. So this is the most current kind of docs that we've got on Tungsten. At least it seems to be the most current. This is really just is the same thing that we were talking about before. So there are some interesting other points here, is that Spark runs on a number of these other features as well. So we just looked at the row format feature, cache locality, code generation, and again, this is sort of a rehash. So again, with the off-heap memory, what it's done. And this is really where we come into that comment about why are we using data sets now. Remember, we had RDDs and we had data frames, and then we had data sets. And data sets in many cases look like RDDs, but you know, they're saying, well, what's the difference? The underlying difference is that I mentioned in the first day, they're typed. And because they're typed and they have that known schema because of the typing, which basically tells us where things line up, then it enables Tungsten to actually optimize the storage of those objects. So let me see. So there's again pretty much the same issues here. So
I ask a question. Sorry.
Yes, go ahead.
As far as I understand, when we were looking at different mapping techniques, or the different mapping techniques, how you can map data to some data structure, there were two techniques that I remember. First one was iterating over the data and making an RDD of case classes, right? The second one was setting up a schema on data set or data frame. Was it data frame? I guess it was data frame.
Yeah.
And those approaches, somebody said that those approaches are basically more or less equivalent. In terms of Tungsten optimization, so which one is better then?
Okay, now describe the two to me again.
So the first approach was iterating over the data and mapping each data row to case class and creating an RDD out of that.
Okay.
Right. The second approach was setting up a schema beforehand and then loading the data using the schema that we have set up.
Okay.
Which approach is better in terms of Tungsten optimization?
Okay, I can't give you a definitive answer, but my suspicion is that it may be the first, it may be the second one. Because if we're, as we're loading the data, we have a schema which is typing the data. that information can be used directly by Tungsten to set up its unsafe row formats. Now, whether or not it actually occurs in the first one, it may actually be going under the hood, but I don't know. But I can certainly, if that's not happening, then I would suggest the second one, where you predefine the schema. So as you're reading it in, you have a template that tells Tungsten, you know, what the layout of that is in terms of types, so that it can do the appropriate allocation. Does that make sense?
Yeah, so it seems like the second option is like 100% safe in the terms. Whereas in the first option, this might happen under the hood, but we're not sure.
Yeah, and I wouldn't be surprised if it is happening under the hood, which is why I kind of hedged on that. But, you know, on the off chance it isn't, and it may be in some cases it's not, if you're using some kind of, you know, in order to be backward compatible with some legacy sorts of issues, which is one of the reasons why I think it might not be compatible, then you might not be getting exactly what you think you're getting. So I would go opt with the second one.
Okay, thanks.
Yeah. Okay, so there's a lot of kind of more detail about the kinds of actual internal structure here, and you can explore it using this internal row, and you can. So, for example, here there's creating a class, and there's a lot of low-level stuff in here. So there's examples here of how these things are encoded. So this is a you know, I tell you how boring my life is. I find this actually a fairly interesting section. So there's various modifications that can be done here, and we're going to sort of like a lot of how they iterate over unsafe rows. Now, most of this stuff is not going to be stuff that you are going to have to deal with in terms of the normal Spark code that you're writing, because this is all being managed by Spark itself. But I believe that this is really intended in this section more for people who are going to be writing or contributing to Spark itself, and need to be able to ensure that they are able to do stuff that works along with the underlying Tungsten format. Okay, now I'm going to just take a pause here for just 2 minutes, and then I'm going to come back and take any other questions, and also take a look at, go back and revisit Catalyst for a minute. So just give me one moment here, folks.
So to come back to the Roman question, your approach doesn't work if you don't know the data. So you can infer the schema beforehand, but you have to know which data you're receiving. If you don't, you have to let Spark basically. So what you said is basically like using a case class for dataset. So yes. These like are very soft, but in the essence that you don't know the schema, that's where Tungsten like can help you. It's basically infers the data for you. And run some optimization on like data format and other stuff. But if you specify the schema beforehand, I'm not even sure that Tungsten is very helpful, and I'm not even sure it does any optimization.
Sorry about that. We'll just officially call it an old man's break. Okay. So questions? Any other questions about Tungsten?
Yeah, we were discussing my question with Gregory. So the Gregory's point here is that if we specify the schema in advance, this is an explicit way of telling Tungsten how to optimize, right? Whereas if we use the first approach, which is being composing RDD out of case classes, right? Then we don't know the data. And I kind of understand this point, however.
No, well, actually no, because if you use case class for your data, then your case class have to match the data, so you specify it before.
Yeah, right.
What I was saying is like both cases I think are kind of handled pretty well by either. It's like, I guess on one hand tungsten and probably also Catalyst will be used, I think, because depending on the data type and what you request, it might run some optimization. What I was saying is that you're constrained by the input data, that you have to know your data, you have to know which data you have in advance to be able to map it kind of properly. And also that's
applies in both cases, right?
Yeah, in both cases it's the same. Yeah, exactly.
Yeah.
But you have to, basically one is equivalent to the other.
Yeah.
Okay.
Because the Spark data frame, I think it uses the reflect from Scala to get a case class, and from a case class it basically derive a schema, a struct type schema from there.
Yeah, but that's the same case with our.
And that's the same case class that we would use for the encoder in the dataset.
Yeah, I mean, that was my point. So Scala is statically typed, so it can derive types actually.
Yeah, exactly.
Even if you
the only thing that where tungsten runs into a problem with, if you can't defer it from some kind of explicit statement because it's not implicit, is going to be the Python case.
Yeah, that part I understand here.
Yeah, and so the two places that tungsten is probably not going to be able to do things if you're using really an unstructured RDD, which is basically a long string of text, which is no inferable structure. Then what can tungsten do with that? And again, and the reason that you have to remember here is that the guys who are writing and maintaining Spark and Tungsten are always looking to ensure that if there is a way to infer structure from some aspect of the data, that they're going to leverage that in order to put it into Tungsten. But a lot of that is going to be happening implicitly, so you may not see it actually happening. But that the big boost we got in terms of performance and being able to use the CBU optimizer and Tungsten is when we kind of really were able to work with the data that can be typed. Then we get real good in performance. The data sets, data frame, unified interface gives us that. So it's generally at this point, unless you're using some kind of really retro kind of application and retro data, you're probably not going to run into too many cases where tungsten is going to be blocked from using anyway. So it's probably just one of those things that is just continuing to be able to adapt. Any other questions about tungsten there? Okay. Let me see. We've got distribution of executors. There we go. All right. Now there are, and I tried to make sure I had this here. I'll just got a few minutes to just kind of discuss the cost-based optimization again. And I think this is where I think this is where I was, there we go. And there was someone I thought I had, okay. That's the equal heights containers. I had bookmarked one of these in order to follow up with the discussion we had yesterday. General log. Oh, that's probably the one I want. Okay, so looking at the optimizer, I had found here that there is when you're submitting, that you can submit hints in the same way, but that the hints are a little bit more limited, or it seems to be limited. Here are some of the things we were looking at that I was talking about yesterday. So the optimizer defines default batch rules, and I said one of the things that I was always wondering about was how those batches were being defined, but then it's confirmed what I thought, but I wasn't clear about it, is that we are actually able to do some optimization and suggesting rules that can be omitted or including new rules. And we remember we talked about fixed point rules, and that can terminate because they become idempotent at some point. And there's certain other rules that just don't become idempotent, so you kind of want to use them only once, so they're batched. here's the different batches of rules that are used, and this is what I was actually looking for before. So here's, for example, pull-up correlation expressions. We use that once, and there's the actual rule that's being used. Here's a replace operators. This is a fixed point, so we're going to run these rules recursively on the tree until this batch stabilizes. Aggregate again is a remove literal from group expressions, remove repetition from group expressions, and this will continue to apply recursively. And there's a number of other sorts of ideas. So there are these kinds of rules are well defined. There are also other rules here. Now, I think what I wanted to do here was also we can also define optimization rules at an extension point. So we can allows us to define additional rules for a particular branch, and this is so there are extension points, and there are ways to actually tweak some of the rules. Let me take a look here. So this is where we're using the query planner, which converts the logical plan to the physical plan. And again, we've got the execution planning strategies. So we can just take a quick look in that tab. So there's my planning strategies that can be used. It looks like it may actually be the same one. So there's actually this Spark Planner instance that's created, which has I don't want to say strategy because we're talking about strategy, which has the overall plan for optimizing the strategies. So we can also add extra planning strategies, and we can also prune bad physical plans. So there's ways to go and prune them. I was trying to find a reference to point out a really easy way to do this without having to do something that's fairly complex. So this tells us what we can do here. Let's take a look, for example, at extra planning strategies. Although it just takes me back down here. So there are extension points. Now, I'm under the impression that these are not intended to be used by people who are just using Spark in a production environment. But I have a suspicion this is more intended for people who want to be able to experimentally introduce certain kinds of strategies. So there does seem to be a way to actually do this. But it looks like it's going to require significant amount of programming to do. Where are we here in terms? We're now at. So there is this underlying interface that allows us to develop these particular strategies. Okay, and this is where I was hunting through here, and there are, if you go back and look at the queries section on Spark SQL queries, I believe there is a tungsten execution subqueries. There is an ability to actually do some hints here. Maybe just paging on a little bit further. So there we go. So we have a hint framework, and we can actually specify hints, which was one of the questions that came up yesterday. And so that you can apply a hint, give it a my name, and give it some kind of parameters for doing the hinting. So there are, you can provide hints for coalescing and repartition, hints to broadcast. So you have a number of hints that can be used when you're actually setting this up. Now, it's unclear to me how those hints are actually propagated, or if they, or I'm assuming some of them must be propagated from the Catalyst logical plan into the physical plans, and then are used to help in the pruning of the physical plan process. But I couldn't find a definitive statement as to how exactly that process works. But to me, it makes sense that if you're making a hint about broadcasting, that's got to make it all the way into the physical planning. So that seems to me to be the process for doing that, or that the process would tend to logically go that way. So that's sort of the impression certainly that I got from here. So let me see here. So that we can work again with the hints, and hopefully if you do that, you'll see the hints come up. That might take a little bit of experimentation. I'd actually wished I'd had a bit more time. I would have tried to do a little experiment to see if we could demonstrate something there. So the query hints do allow the annotating of a query and to hint out or optimize the logical plans. And again, the question in my mind was how can we
Hey Rod, we don't hear you anymore.
Probably you hit Alt-A.
No, what happened was I unplugged my mic accidentally. Sorry about that. So apologize. So the hints themselves are intended to help fill in the gaps where there may be some ambiguity between what the optimal decisions are. But it does seem to be that most of the hints are going to be directed towards the logical plan optimizer. But like I was saying, I'm sure that these hints also must be propagated through in the appropriate cases to the physical planner. But I am not sure exactly if there's a way to actually make hints to the physical planner itself directly, unless it's propagated through there. So that's sort of the assessment that I have of that. So that kind of brings me to basically the end of that sort of answer to that question that was raised the other day. Those are the questions I had a chance to look at. So we've got about 20 minutes left. So is there anything else we'd like to go back over, or any other questions or any further discussion on any of these topics, or delve a little bit deeper into anything else?
Mike, what about your question about seeing some example?
About what?
The start of today, Mike proposed that we could see some complex query and how it could be optimized, but I'm not sure if we have enough time.
That may not be possible. Okay. So what was the scenario you wanted to set up?
I didn't have anything concrete in mind. I just had like this rough idea of what we could do, but I sort of expected that we don't have anything ready offhand. So
no, that's why I'm saying we would take a bit of time to set up. Well, why don't we just describe kind of what the rough idea is, and maybe we'll just kind of, see what we might propose is happening in that scenario.
Like I said, I don't even like the rough idea was that we have a complex query. I didn't have anything.
Oh, I see. Oh, I see what you're saying. I see. I thought you were mentioning.
So that was the rough idea. I don't even have a concrete or anything like that in mind.
Okay. Oh, I see what you're saying. Yes. I thought you were talking about. You said complex. I thought you said conflict, and I was thinking, okay, there's a conflicting query, so I can think of a couple of things that could mean. So, yeah. Okay, so that's not really. I'm kind of dry at this particular point. So, any topics of discussion we want to open up, or revisit, or discuss, or hypothesize about?
Just wanted to remember one more time that we were going to have this Hive lab, but yeah, I'm not sure if anything was.
Oh, I didn't have a chance. I'm sorry to look at that. I just ran out of time. I was teaching all afternoon and actually until 11 o'clock last night. So I only was able to get about 2 hours to look at this stuff, and that was at the bottom of the list. So I do apologize. I wanted to get this stuff prioritized first, you know, kind of the internal stuff. All right. Anything else?
Maybe I can suggest something.
Sure.
So I experienced this problem in the past, and I know that there might be some techniques to address it, but I didn't really look into them. So in case you know about it, so there is this problem of skewed data, right? So you might have I don't know, a join on some column which has very low cardinality, and therefore the partitioning is very uneven, right? So can we maybe talk a little bit about how to approach optimizing or rewriting queries to avoid this data skewness?
Okay, so one of the the two data sets are very different in cardinality. Just explain the situation to me so I get a clear picture of it.
Yeah, so maybe in general terms. So let's say that they are both mid-size, right? So let's say that we could potentially perform a join with a reasonable sized cluster, and there are no more opportunities to optimize in terms of broadcasting the small table or anything like this. In the end, we just have two mid-sized tables, and we want to join them based on a column which has only, I don't know, 2, 3, 4 distinct values. So it is my understanding that Spark might decide, I mean, if it doesn't know better, it might decide to assign one partition for each different value of this join column, right? Kind of like a reduce by key kind of thing. So each key goes to a different partition. So we might end up only with these 2, 3, 4 partitions, right? So only those 2, 3, 4 workers are doing any work at all. And then the remaining workers on our cluster, they are just idle. So, and only because the fact that we only have these 2, 3, 4 distinct values there. If we have, I don't know, 100 distinct values, then no problem because it's more even distribution, but it is this data skewness that causes the job to be not to fully utilize the cluster. Does that make sense?
Yeah. Okay. Okay. So yeah. So there's all right. Well, one. Let me see. So joining on keys is can we assume just for the sake of argument it's an inner join at this point?
Yeah.
Okay. So one of the techniques that we've used, not in Spark, but to deal with that in kind of data modeling in the past, is to introduce a binning key or a sorting key, which is just basically having a combination of the key value plus some other column which has a better distribution. Okay, so let's suppose that we've got, say, five key values that are going to be cardinality of keys. So very often what we can do is kind of create kind of a composite key, which gives you more of a distribution that you can use to then bin the data more effectively. that may or may not work in their particular situation, but I'm trying to just envision what this data would look like. So oh, the data has, how many keys are in the data itself? I mean, in each row, how many multiple keys do you have?
So I mean, just to say something specific, let's imagine we have two tables with 1 million rows each.
Yep.
With only two columns. Let's call them key and value.
Okay.
Right. And in the key, we only have, let's say, only two different values. So we have 1 and 2 repeated, I don't know, 500,000 times.
I see what you're saying. Okay. Go ahead.
And then we want to join by this key, right? So in the end, it's just like, if we think of a sort of reduce by key scenario, then we end up with two reducers, right? One for key with value 1, and the other one for key equals 2. And if I have a cluster with 100 nodes, then yeah, so 98 will be doing nothing, and 2 of them will be busy processing a join of 500,000 rows each.
Okay, so
but I mean, in this case, what you said before sort of makes sense. So let's assume that instead of this key and value, we have yet another key inside, which is not relevant for the join, but we have it there. And that other key has, let's say, more values, not just 1 and 2, but a lot of them. And let's assume there's an even distribution. So what you were saying before is that we could, let's say, repartition both tables based on the combination of the key we want to join by plus this other key that gives us the entropy somehow. Yeah. And then we have a better distribution, and then we can do the join.
Yeah, and so you know, yeah, the idea is that what you want to do is you want to kind of change the distribution, and so you will throw in some kind of piece of, you know, a salt or some kind of other value, and you don't want to start adding things to the table. So generally, you pick some other you know, kind of candidate key. And to give you a larger sort of a better distribution, and then distribute it on that, and then you're able to distribute the load a little bit better across the nodes. That's the only suggestion that immediately pops into my mind, is to use this kind of sorting key technique. But you would probably want to maybe profile what else is there to figure out which column is going to be, or combination of columns is going to give you a nice distribution, and distribute it that way. That's the only thing that immediately comes to mind.
Okay, thanks.
Yeah. Okay. Well, we're down to the last 10 minutes, so I think what I'll do is just turn the floor over to you guys for the last 10 minutes and say any final thoughts or comments that you'd like to make.
Maybe one last general question. So
sure.
What will be, let's say that, okay, so after this course, we have some level that we can operate on, but we wanted to look further into more details, or let's say just continue learning more about Spark. What would be an interesting resource for us to look at? So I'm checking this sort of book or blog or whatever from this Polish guy.
Just read the book. Read the whole book. There's two books.
Which book do you mean?
So there is this ebook, and there's the other one is on my desk. It is basically this advanced Spark, and this book, each book actually, this one, and everything is explained. Like, I don't know, the guy knows
Spark is good.
Everything about Spark, like not only Spark SQL, but like this mastering Apache Spark, and there's another one also for introduction. This guy, like, both of his Git books are just really good, and he now added some kind of Java doc inside. And for most of the case, you have an example and you explain how it works and why. And yeah, to be fairly honest, I don't think there is a better resource than this one. The only better approach, if you like, the paper is the one I have on my desk, which is kind of a copy-paste of this.
Okay. Right. Yeah. So this one looks quite detailed and getting into the inner workings, which I like. And I guess the next more detailed resource will be the source code itself. So I think this one is quite interesting.
Can I also ask to send us the slides about tungsten?
The slides are in that repository I gave you the GitHub for. So